My name is Alexander Jensenius. I'm director of RITMO here at the University of Oslo, and would like to welcome you to Norway, to Oslo, to the University of Oslo, and to RITMO. And just a few quick words about, yeah, is there something wrong? Is that better?
Check.
Is that better? That's better. Cool. So I'm going to very quickly introduce you to RITMO, since you are here and know where you are. So we are a Norwegian Center of Excellence, funded for 10 years, and it's our aim is to understand more about how rhythm acts as a fundamental property of human life. So everything is kind of centered around rhythm in different ways. We are a very interdisciplinary center. It's a collaboration between the Department of Psychology, where we are currently in the same building. We also have members from the Department of Informatics, and finally a large group also of researchers from the Department of Musicology. And we study then rhythm in different ways, and we like to say that we study this from kind of the softest soft to the hardest hard, working with very many different methods, starting from the arts and humanities of different kinds, and also moving our way to different types of behavioral methods, pupillometry, motion capture, different types of brain imagery. We're doing even some life science studies, biology studies, machine learning, and robotics. So it's a large variety of different methods and approaches that we have here at RITMO, and that you'll probably also see parts of during some of the presentations today, and also during some of the demos and other things that we are doing here. Now, we are a sizable group now, or a center, with up to around 60 researchers working here. Anne Danielsen and I are directing this, and we also have a wonderful group of PIs, and many of them are also sitting here in the room today, so we can interact with them. And also internally we are organized in 4 different clusters, so that we have different approaches to how we are studying rhythm, but of course also trying to foster as much interdisciplinarity as possible. And with that, that's a very short introduction with also some kind of fun pictures from behind the scenes of RITMO. And with that, I would like to welcome you here and hand it over to Dana to introduce the workshop. Thank you.
Thank you, Alexander. Dear in-person audience, thank you for traveling to RITMO. We are so pleased to welcome you to our beloved Center of Excellence. Dear remote audience, thank you so much for joining us from around the world today. We ask the live audience, please turn your phones to silent, and remote audience, please respect presentations by keeping your microphones muted until question and answer periods. All presenters have 12-minute presentations, and the session chair will give presenters a 2-minute warning before the end of the presentation with a strong peace sign or with a chat message in the chat. The question and answer period will last for 5 minutes. You may either raise your hand and we'll bring you a microphone, or you can ask in the YouTube chat, which we will also be monitoring, as well as in the Zoom chat. Attendees in remote presentations can raise their virtual hands and ask questions with your microphone when the session chair calls on you, or you can ask in the chat. If you have any logistical questions, you can find a helper in a RITMO t-shirt. Check the web page, which is updated, and our frequently asked questions section, or you can send an email to the Entrainment Workshop Planning Committee at entrainment@ritmo.uio.no. During the breaks, the in-person audience is invited to enjoy coffee and snacks here in Forsamlingssalen, or you can check out the RITMO kitchen area downstairs and enjoy the sun on the RITMO lawn. When you hear this bell that you heard earlier, that is your cue to go back to your seats. And for the next session, or head to the next session. During remote breaks, we encourage you, remote audience, to enter one of the breakout rooms. One breakout room will be for general socializing, and there will be one for each presentation in case you want to discuss a particular presentation with the presenter or the audience members further. Presenters are kindly asked to come to this stage 15 minutes before your session to test your presentation on your computer or USB drive and your videos and sound. Remote presenters should do the same in the breakout room devoted to testing their microphone and video with a RITMO representative. As in-person and remote guests at RITMO, we hope that you will support upholding our code of conduct, which you can find on our webpage and on the wall in the coffee room. Our goal is to create an inclusive and respectful work environment for students, employees, and visitors. Thank you for working with us to create an inspiring entrainment workshop. Let the workshop begin. I'd now like to invite the first presenter up.
Hello.
Try to talk more.
I'm Ajay. Test.
This is Mig 1. Do you want to try talking as if you're presenting? Or say the title?
Yeah, I'm going to talk about modeling rhythm perception and temporal adaptation. Yeah.
There you go. So just maybe adjust a bit.
Can I do this? Yeah. Hello. I'm excited to be the first presenter. So, I'm Ajay Kaya. I work with Molly Henry, and today I will talk about our recent study, which is a computational modeling study of rhythm perception and temporal adaptation. So, one main research question in timing literature is how do we perceive and adapt to rhythms? And in entrainment or dynamic attending theory approach holds that we do so by synchronization between internal and external rhythms. So for example, here the oscillations, the internal oscillator adapts to the speech regularities in the speech, and when it gets faster, then it adapts to this new rate. And the aim of our study is to estimate properties of this underlying oscillator, and we focused on its eigenfrequency, which is its preferred rate, how it adapts to different rates, its flexibility, and whether the oscillations are sustained versus decayed. But first, let me talk a bit about how oscillators work in general. So here's an illustration of an oscillation, and the time it takes to complete one circle, one oscillation, is period, and it has a phase at each time t. And according to dynamic attending theory, at the peaks of this oscillation, we expect is the expected timing. And the model we used here from Macaulay, in this unit circle is divided in half, and when a stimulus is on time, then the phase of the oscillation is 0. When it's early, then it's smaller than 0, and when it's late, it's bigger than 0. And when synchronizing to a stimulus, the period of the oscillator before the stimulus is its preferred rate, which we call P0 here. And when the stimulus onset is earlier than expected, the oscillator thinks I should delay my phase, which is called phase correction. And when the stimulus interval is, for example, shorter than its period, then it's contracts its period, which is period correction. And after the stimulus, two things can happen. The oscillator can either go back to its P0, which is called entrainment decay, or alternatively, it can continue oscillating at the same entrained frequency, which is sustained oscillations. So how can we test the oscillator behavior in a certain conditions? And we can do that by fitting the oscillator model to the empirical data. And here, in the study, empirical data came from a perceptual experiment. The stimulus, it was a duration discrimination paradigm, so the stimulus is isochronous, 5-click sequence, and then there's silence, and there's the comparison interval. And the task is to say whether this comparison was shorter or longer than the standard intervals. And the study had a unique design that challenged individuals and the model's temporal adaptation abilities. So the set intervals were, in one trial, for example, they were fast, and then they were slow, and then they were fast again, and then slow again. And the rate change was balanced over the entire experiment. In one session, the random order session, which is temporally challenging, and in the other session, the linear order session, it increased or decreased at a fixed level. So it slowly increased, got slower half of the experiment, and then it got faster on the other half. And we recruited 27 participants who completed the 2 session types. But how does this model works in this particular experiment? So beginning of each trial, the model takes 2 inputs, initial period and initial phase, and at each interval, it makes this calculation of a C value, which is the temporal contrast between the model state and the stimulus. And in each interval, it does the calculations and adapts space and period, and at the last interval, it gives a response based on this value. And the parameters of the model are the initial phase and period, and phase correction weight, period correction weight, and to account, to quantify the decay that might happen within this silent gap between standard and comparison stimulus, we added decay within, which was a weighted average between the calculated period and the model's P0 preferred rate. And similarly, between 2 trials, the base model, Macaulay's model, assumes that the oscillator starts each trial with its preferred rate. But to account for decay that might happen there between trials, we also added decay between parameter. And so instead of P0, it continues or from a weighted average in terms of period. And so the base model assumes that sustain happens here, so the oscillator continues at the same frequency, and complete decay happens here, so it's kind of incompatible. And what we assume is that it should be somewhere in between. And the parameter space for the weight parameters range from 0 to 1. And the model fitting procedure consisted of simulating model response given the parameters, comparing them to the participant response, and finding the parameters that gave the minimum difference between the responses and predictions. So I will focus on 2 main findings today. First was that we found out the oscillator decays back to its preferred rate to some extent, rather than sustaining oscillations within the trial, and rather than decaying completely between trials, as the base model proposes. And the second finding was that the oscillator's behavior is top-down modulated depending on the temporal context, which was the session here. So the first finding came from model comparison. So this means that a model fits good and a bigger value means that it fits bad. And the base model had this phase and period correction parameters and the P0. And we added decay within and decay between separately to the two variants. And then variant 3 had both of them. And the model comparison results showed that variant 3 accounts for the data better than the other models, showing that the decayed scenario was more likely. And moreover, the two decay parameters were positively correlated in the random order session, as you can see here, which means that participants who decayed within trials also decayed between trials to the similar extent. And then we focused on parameter differences between the sessions, and we found an interaction between session type and correction type, in that phase correction was smaller in random order, the temporally challenging session, than the linear order session, and period correction was bigger in this session. And the complementary roles of phase and period correction supported this finding. So we found a negative correlation between them. And finally, we looked at the predictors of task accuracy. And in a model that explained 90% of the variance, so it's a good model of accuracy that predicts accuracy based on the parameters, showed that contributions of period correction and between trials decay on accuracy differed between temporal contexts. So in the random order session, the prediction pattern of these parameters were opposite of the linear order session. And to summarize, we found that the oscillator decays back to its preferred rate to some extent, rather than sustaining oscillation within trials and decaying completely between trials, as the model with both decay parameters fit better. And we found a positive correlation between the decay parameters, showing that there was a common source for this decay. And the other finding was that oscillators' behavior was top-down modulated by depending on the temporal context, which was the session. And we saw that by the phase and versus period correction depending on session type, and negative correlation between phase and period correction, and finally contrasting predictions of period correction and between trial decay in these different session types. And the general findings were like that from this study. And yeah, I would like to thank Molly Henry and our research group for their help and support. And thank you for your attention. And if you're interested in the details of the experiment, it's in SciArchive here, or you can always email me and for further inquiries and questions. And now I can take your questions. Thank you.
Thank you so much for a wonderful presentation. Are there any questions from the audience already? Not all at once now. Okay, wonderful. Maya, what is your question?
Thank you so much. Really, really interesting presentation and study that you've done. I'm really interested in what you show about these top-down kind of effects on these oscillatory effects, and whether you think it's like, can it be kind of related also then to some kind of top-down attentional processing, do you think, or like what are your thoughts on that?
Yeah, I thank you for the good question. I do think it is related to, I mean, because we're kind of assessing the attending, so the theory that we base on is the dynamic attending theory, and then it shows that the attention is modulated by the temporal context, and we also see that in neuroscience. So the neural oscillations also are top-down modulated by task difficulty and task specifics. And I think they might be related, or yeah.
Thank you. I'm very interested in the. I will read.
Take
a look at it. Yeah.
Yes, thank you for the talk. Very clear, impressive to explain all of that so clear. And two maybe very detailed questions, but the first one was in the formulas that you showed integers. And my question was, you're actually talking about continuous oscillators and not discrete corrections, and if so, what the actual intervals were that you used? And secondly, in the model fits, like if you add parameters, of course, fits will improve. Like the more parameters that you add, that you can tune to actually improve the model fit, it will always help the model fitting. How, like, I think you showed the slide where you showed the comparison between the model fits, that they actually improved significantly. Could you elaborate on that, on how well they improved?
Yeah, thank you for the questions. The second question about model fits, so we used, I only showed the AIC comparison, and we also did BIC, and in the BIC, the fits, because you cannot average these values, especially BIC, and in the BIC analysis, which also penalizes for the number of parameters that the model has, both measures do that, and there we compared how many participants, for how many participants the model was the best fitting model, and the frequency showed that the variant 3 was the best, and AIC is kind of aggregated from different participants, this particular calculation of it, and it also penalizes for the number of parameters. So especially for the random order session, it does make a difference. Especially for the green one, the random order session, it makes a great difference. And for the linear order session, it generally fits better. So maybe the variant 2 might be also a good model for that session. But to make them comparable, we took the best fitting one. Okay. And the first question was about
the temporal steps that you.
So the model is linearized oscillator model, and Macaulay does that by dividing the unit circle in two. And if you assume the stimulus intensity as the same as the sampling frequencies between stimulus and the model, then it kind of can be translated to linear domain. But it kind of creates a challenge as the interpretability, because everything happens at the end of the interval rather than at every phase value. But yeah, I mean, the original model uses intervals.
Okay. Thank you. Another clear explanation. Thank you very much.
Thank you.
I'll just quickly check the YouTube chat as well to see if there's anybody there. But that was, wonderful responses to those very particular questions from Bavo. So thank you so much. Let's give her another round of applause.
Thank you.
And feel free to talk amongst yourselves while Pedro and I set up.
Yeah.
Please just continue talking.
Hello, hello.
Okay, I'll do mic 2. Do you want to keep talking? I'm going to put
Hello.
this in your pocket here. There you go. So talk as if you're talking to the crowd.
Okay. Yeah.
All right, welcome Pedro Lucas with Sonic Explorations for 3D Swarmolators.
Okay. Hello, everyone. My name is Pedro, PhD student at RITMO. I'm going to present this topic, sonic exploration for 3D swarmolators. So, what are the swarmolators? Well, the swarmolators, they are oscillators whose phase dynamics and spatial dynamics are coupled. So you can imagine an object, for example, and this object internally has an oscillator or some internal states. And this object can move in a space and can work in its state. So basically, you can think about in many of these objects that are related with each other in a kind of swarm. So the thing is that because this is a swarm of these objects, this swarmolator take the name from that. It's a swarm plus oscillators that works internally. So basically, the movement of these objects and also the phase of these oscillators depend of the position and also the phase of the other agents. So this swarmolator model can be found in this paper here, oscillators that syn and swarm. So this is the general model. So basically what we have here is delta position and a delta phase. So a change in position and a change in phase. As you can see here, for a specific agent I, the change in position depends from both the position and the phase of the other agent. So this is a contribution of all the agents for this change in position as well as the change in phase. So an instance of this generic model is this other model that is inspired in the Kuramoto model for coupled oscillators. So basically, we are reduced this to just the tweaking these two parameters, J and K. So J is the extent to which the phase similarity enhances spatial attraction. So this parameter J allows to see or to model how these agents, the set of agents can be closer or far from each other. And the K is the phase coupling strength. So how fast we can reach some kind of phase state like synchronization or any other kind of behavior. So if we manipulate these two parameters, J and K, we can have different specific patterns. If you think about that the phase is related with a specific color, we can say that if all of the agents in this group of swarmolators are synchronized, all will be with the same color. So as in this case, if you can see, there are a lot of these objects, and this state is called the static syn if we have these two values of J and K, 0.1 and 1. It's a static because the agents are not moving, so they are just synchronized in phase. By the other hand, we have this other state in which all of them are static also, but they are unsynchronized, so the phase are different. Also, depending of other values, we can have several nice patterns. For example, we have these patterns in which all the agents are static, but there is, you will see that later in a demo, we have a wave, a phase wave that is going around. So that means that all the agents are changing the phase in time. Also, we can have this kind of clusters of phases in which the phases are separated in these patterns. And finally, this other pattern is when now the agents are moving around, and apart from that, they are changing in phase. So the thing that I want you to understand is like the movement and the phase depend of position and phase from the other ones. That's the key thing here. So now, the thing that I'm exploring is how can we map some parameters from these surmolators of this set of objects to generate sound. So we have to design a kind of mapping strategy for doing that. So I'm going to present two of them today because we have several or many, almost infinity options to do this. One of these is mapping with a melody or pitch sounds. So basically what I'm using is the two main properties like phase and position from a surmolator. The phase, I'm taking the phase like as it is, but for the dynamics of the spatial parameter, I'm taking this angle that is basically the angle between the center of all the agents that are here, of this right vector regarding the vector from the center to a specific agent I. So as you can see here, we can have different angles depending on the location of the agents, and that is the parameter that I'm using here. So the phase I'm mapping with a frequency. It is direct, like in a range of values, or in discrete values, like in a musical scale. So this will be the frequency for a sine oscillator. This angle I'm mapping with the phase of a low frequency oscillator, the amplitude, so that I can modulate this sound oscillator in amplitude with this parameter. Yeah, that is one. The other one is something that you will see that is a little bit more logical to the purpose of the surmolators. I'm using the phase for actually the phase of when you are playing a hit sound. So this is basically the delay in which you can play the sound. Also, I'm using the phase just for giving a little bit of differences in the dynamic for the hit sound. I'm manipulating a little bit the pitch of the hit. So I generated this hit sound. Apart from that, I'm using this for triggering rhythm patterns, specifically Euclidean rhythm patterns. So you will see or you will hear that it's not just a hit, but it's a trigger for a specific pattern, a set of events in time. Yeah, okay, so I'm gonna show you in real time the demo. So yeah. Okay, so this is a simulation of the surmolators in a 3D space. We have now three that are unsynchronized, so we can actually add more of them. So in this specific pattern, we have full synchronization, as you can see. Yeah. So if I put the state of the phase wave, moving phase wave, it will be like something like this. Yeah. As you can see, it's a kind of nice pattern in which you have several of these elements that are going around, and you can notice that there is a kind of wave that's going around. So how it sounds? For the range of frequency, it sounds like this. Yeah. So I can change the state of this, for example, to something more static. This is the static phase wave, or synchronized, and they are synchronized. So if I add more of these agents, they are randomly assigned a random position and also a random phase. So they are going to be influenced by the other ones, and they are going to synchronize. Yeah. But what if I map this with something more, let's say, more pleasant? And for example, I'm mapping not this to a specific range of frequency, but I'm mapping this with a frequency from a musical scale. So I can change that. And then I can provide some movement to the sound. So this is one of the examples that we can map this thing nicely with sounds. But what if we use the hits pattern? So if everything is synchronized, as you can see, it's like everything is in sync. Then I can change this. Yeah. And what if I use some patterns? So now this is not just triggering one sound, but it's triggering a set of sounds, set of patterns. So I can play with this and have these changes in dynamics regarding the sound. Also, apart from this, I add something else. Like we can have, for example, manual objects that we can manipulate, and we can have some kind of interaction. In this case, this is, let's say, a manual formulator. This is not influenced by the other ones, but the other ones are influenced by this one. So if I want to synchronize, for instance, I synchronize everything. Eventually, because this is not influenced by the other ones, they will take the same phase of this one. If I change the phase, for example, to this color, and they're going to follow. Even like if I move this in a space, they are influenced by this. And if I add other randomly, sorry, yeah, we can have like a kind of, I would suppose, averaging the phase of all of these manuals, because they are not coupling with the other ones. Yeah. So this is a way in which we can interact with this one. So imagine these cubes that could be a human, performer that is interacting with these agents. So yeah. Okay. So in conclusion, yeah, okay, you can see that we have mappings that could be aesthetically appealing, but that depends, it's subjective. We can experiment with this formulator. It's useful for automatic synchronization. And we have several possibilities for human interaction. And of course, it can be applied to other fields. Because you are working with the concept of entrainment, you can use this for your research. So the idea of this is like trying to use this for implementing human soar interactive music systems in my PhD project, and exploring other kind of mappings, and try to work with decentralized objects, and maybe scale this to other physical agents like robots or things like that. Yeah. Any question?
Thank you so much, Pedro. That was amazing. And so cool to see it in real time and how you can actually use it and play music with it. For those of you that can't see, there's actually a keyboard up here, and he was playing on a MIDI keyboard. So I'm going to show that. Yeah, amazing. Are there any questions? Oh, wonderful.
That was very nice. Thanks very much. I was just wondering if you've experimented with the decision as to what Euclidean rhythm the rhythm section will use. You know, have you set various different relationships between the conditions and the choice of Euclidean rhythm?
Sorry, can you repeat it? The last
How do you decide which Euclidean rhythm to use when there's a multiple?
Oh yeah, okay. No, actually, this is like random patterns that are generated every time one of these sound agent is generated. So the thing is that they are distributed in one specific range of time, and then there is a Euclidean rhythm generator. So it randomly generates a pattern depending on some specific parameters. So if you start again the program, you will have a different pattern. So I'm not actually deciding per se. I have some parameters, and then it generates randomly. But still, because it's within the frame of a clear rhythm, that's why it sounds like something that makes sense, I would say. Yeah.
Thanks for this really cool presentation.
Thank you.
I have a question about mapping to sound, the phase, and you talked about phase and angle.
Yeah.
Phase, and so the phase isn't the phase also kind of the the sign of angle. So is they're kind of the same thing, but in the circular plane?
No.
Or is
Yeah,
it the...
because, yeah, maybe it's not clear here, but yeah, remember this, there is two parts, like the oscillator and the octet, the dynamics of the octet, the spatial dynamics, like the position. So the phase is the phase of the oscillator. Okay. Yeah, so you can separate that, the oscillator and the position of the thing. So the phase is the phase of the oscillator, and this angle is a spatial angle. Like you have the object, and you calculate the center, and you have the angle between this vector and this. So this is a spatial parameter. Okay. So the two are different. Yeah.
Yeah, I thought it's just the same oscillator and the unit circle.
Yeah.
Okay,
No, that's separate. Yeah. Okay. Very cool.
Thank you. I just checked the YouTube chat. There were no questions. But I was wondering, like, what is your vision for the next step, Pedro? What, like, when you've finished your PhD, what's like, are you planning an installation, like 3D sound? Like, how will you apply this that will in your PhD in the future?
Yeah, basically, I'm exploring this for the synchronization part of my PhD, because my PhD is related with human sound interactive music systems. So basically, you can have several levels of this. I will target to the level in which you can make music with artificial entities. So if you can have something congruent, you need a strategy for synchronizing rhythm, synchronizing music, and everything sounds, let's say, nicely. And so yeah, I'm exploring Stormulator so that I can have a tool to manage and approach this synchronization in this kind of system. Yeah.
Amazing. Thank you so much. Thank you again to Pedro.
Thank you.
So now we're going to switch. We're actually going to have a remote presentation. So pause it once it's... So next up, we have a control systems perspective on entrainment by Roger K. Moore. And Roger will join us for a Zoom question answer afterwards. So there's sound in this video, but it's not putting sound out. How do I do that here?
language. Hello, my name is Roger Moore and I'm Professor of Spoken Language Processing in the Computer Science Department at the University of Sheffield in the UK. And over a large number of years, I've worked on many different aspects of speech processing, particularly speech technology. And one of the areas that interests me greatly, especially at the moment, is interactivity and how it is that human beings are able to engage in spoken language interaction with each other and also with machines. And part of my interest here is on how we model this, and in particular how we view this as a potential form of entrainment between interlocutors. So that's what I'm going to be talking about, and I'm going to introduce a particularly different way of thinking about this, which is from a control systems perspective. So obviously, collective behavior has been very well studied, and I'm sure we're hearing a lot about that at this workshop. Whether it's shoals, swarms, flocks, or crowds, this kind of interactive behavior has already been very well studied and modeled. I'm particularly interested, as I say, in speech and therefore in vocal entrainment, vocal synchrony. And it's not just human beings that do this, of course. Many animals and insects will interact in this way using sound. Hello, my name is Roger Moore and I'm Professor of Spoken interaction between humans. Here's some Inuit throat. That's two individuals very, very carefully entrained with each other. So I want to now distinguish between the different models and mechanisms for tackling this. So the models are typically based on coupled oscillators. Again, we'll be hearing a lot about that at this workshop. It's essentially based on dynamical systems and has an attractor space with some rhythmic aspects. There are some control variables which are kind of implicit. It's very much targeted at mechanical systems, rooted in maths, and is typically described by dynamical systems theory. But I want to contrast that with interacting control systems, which are also dynamical systems and also create an attractor space. But there are differences. So here they are. The control variables in control systems are explicit. And the argument is that this is much more suited to living systems. This is rooted in cybernetics, and indeed leads to a particular form of control theory, which is known as perceptual control theory, or PCT. So control systems have been used in collective behavior modeling, and the most famous is by Reynolds, his Boyd's arrangement for modeling swarms. And you can see the rules of his system on the left there. I say rules, but they're not discrete, they're continuous because they're control structures, and they basically allow continuous control of the steering of each individual agent. And that leads to some very interesting emergent entrained behaviors. So what is a control system? If you haven't seen one before, this is what it looks like in Control Systems 101. There's a reference input, which is what is desired on the left. The top line there is how that's actuated then into the real world by some mechanism. But the key thing is that there's a feedback, and that feedback is basically sensing the outcomes of the actions, comparing that with the intentions, and that generates an error signal. And it's the error signal that actually drives the behavior. So if there is no error, then nothing happens. But if there's a huge error, then something needs to change in order to for the system to regulate. So this is a very old-fashioned idea. This is Watt's steam engine, and you can see the thing with the balls in the middle is Watt's governor or regulator, which was a way of controlling this amazing piece of apparatus. The modern day equivalent is, of course, the thermostat, and the thermostat is a very neat mechanism which allows us to maintain the temperature, climate control, a room in a very straightforward way. And the reason these things are very efficient and work very well is because you're using what's called closed loop negative feedback control. In a living system, this would be called homeostasis. It's basically stabilizing an arrangement. This has been taken by Bill Powers quite some time ago now to be the basis of all interesting behavior in living systems. And his famous book, Behavior, the Control of Perception, essentially was an anti-behaviorist stance. I don't have time to go into that, but this is an interesting aspect of why I'm talking about this particular approach. So here are some research questions. What happens when two or more control systems interact? What are the variables and how do they actually influence the emergent behavior? And how is the emergent behavior also influenced by the topology of the network? In other words, how the agents are connected. These are very important questions when it comes to what's likely to happen from an entrainment perspective. So I programmed this in a simulation environment in a language called Pure Data, which is a precursor to Max MSP, which is the professional version that you'll find in most music labs. What you're seeing on the screen here is an agent with various sliders and controls. It's a vocalizing and listening agent. In other words, it can make sound and it can listen to sounds. Here are the inputs. It can be audio or it could just be a beat. It has outputs, which can be audio or a beat. And then the slider, so there are two embedded control structures. One is to do with maintaining synchrony with other agents. And there's a slider here, which you're able to set the amount of effort, or the attention that this agent pays to another agent. And the second control loop is essentially the same kind of idea. It's another attention mechanism or effort, which is now paying attention to its own rhythm. How much effort does it place on maintaining its own rhythm? These are very interesting variables. You can also change the vocalization. It can beep, it can make human noises, or a cicada or a bird, and you can switch the whole thing on or off. There are various parameters that are delivered as it's running. There's the period, the synchrony error, and the signal-to-noise ratio. So here's what it looks like in the simulation environment. And here you can see two agents which are connected to each other. So the one on the left is the leader, and the one on the right is the follower. And that's because there's a one-way connection between the output of one and the input of the other. The environment has various controls up here, and then there are displays of the beats and the degree of entrainment. It's currently set up to beep, and this is what it's like. And what you're noticing is the follower is now in sync with the leader. Here's another arrangement. This time we've got a chain of 9 agents. So there's a leader at the front and then all the way down the chain. And here's a vocalizing a staccato. And a convergence from the control loop takes place. So we get more and more synchrony. Here's a different configuration. So we have 1 leader and 8 followers. So this is not a chain. This means that there's a more immediate possibility. And I've set this up for human vocalization. There's a caller saying oi. And the followers are saying And then the final demonstration is where we've got interacting agents. So this is mutual entrainment. So we've got connections running both ways, backwards and forwards between these two. And what happens here, notice that they're both self-centered at the moment, so they're independent of each other. The slider has just changed. They're now listening to each other. And they're also paying attention to themselves, so they're both slowing down and trained. And there they're going to watch the slider has now changed. They're only interested in each other, not paying attention to themselves. If you look at the period and listen, you'll notice that it's getting faster, faster and faster. In other words, it's rushing, which is another classic behavior, emergent behavior. So I don't have time to go into all the experimental results. Simply draw attention to one in the middle, which shows that if you have a stimulus response chain, you get delays accumulating. But if with feedback control, you have very little synchronization error, but you have a lot more variance as you get down the end of the chain, because the agents at the end of the chain are, they're losing track a bit of what's going on, because in other words, noise is propagating down the chain. So in this short talk, I've demonstrated that interacting closed-loop negative feedback control systems is an interestingly different way of looking at modeling entrainment, precisely because it gives insights into how the different control variables and the connections, the topology of the connections influences the behaviors. There are lots of other possibilities that could be approached here. I'm very interested in turn-taking, not as a stimulus response behavior, but as an emergent entrainment behavior. And this environment would allow me to investigate that. Cooperation versus competitive vocalizations, and indeed how communicative behavior emerges from interaction in the first place. If you want to find out a bit more about this, then you can go to my website, or there are a couple of papers listed here, Finding Rhythm in Speech, which is a response to a talk by Fred Cummins, and more recently, vocal interactivity in crowds, flocks, and swarms, which pretty much describes the environment that I was just demonstrating. And that's it, and I look forward to hearing any questions. Thank you very much.
Hello, Roger. Can you hear me?
I can hear you, yes. Hello, everybody.
Welcome. And I believe you can now see the audience. So I will come around and ask, does anyone have questions already? Oh, thank you, Molly.
Hi, thanks for a really fascinating talk. I'm feeding back a little bit.
Yes,
Okay.
I'm getting...
Okay, I think it's tolerable. I have a question about there are two parameters in the model, one for self-centeredness and one for other-centeredness. And those are separate. So sort of cognitively, attentionally, I guess I would think those would trade in some way. I can sort of put attention on myself or other, but maybe not both maximally all the time. But I guess on the model, they're completely independent, so you can do whatever you want with them. So I'm just curious whether there are sort of behavioral consequences for keeping those positively correlated instead of trading them, that would be something that you wouldn't see with humans.
Oh, that's very interesting you say that. This is where I'm very sad that I'm not there with you to discuss more about that over coffee. Because from my perspective and using the model, it would be perfectly feasible to have maximum attention applied to both at the same time in a sort of a dominance relation, really competing to interact with somebody else, but insisting on one's own behaviors getting through at the same time. So I'd certainly like to discuss more about why you think those would be traded rather than independently controlled. Or indeed, if you can point me at any literature which would suggest that, that would be very interesting.
Okay, I can do that offline, or we can chat offline.
Brilliant, thank you.
Thank you. Great question, Molly. Thanks. Are there any other questions from the audience here? Martin.
Thanks very much. That was a brilliant presentation. So I'm kind of thinking through how the model you've presented here might apply in the context of an ensemble musical performance. And it strikes me that within this architecture, one of the things that would be going on would be the participants or the musicians in that situation, where they would be getting feedback would be, does the whole sound like the whole should sound, as it were? So in a way, the attention might not be so much on self or other, the attention might be on the total outcome, and then on, you know, how does my part have to change or not change in order to maintain the outcome sounding like it should do? I just wonder if you had any thoughts about that.
Well, the total outcome, of course, is the ensemble activity of the individuals. So in that sense, it's perfectly feasible within the simulation to have an agent which is listening to all of the other agents. So actually the last presentation was kind of very closely connected with what I was talking about, it turns out. So you can easily imagine how the agent, an individual agent, has to take into account its position with respect to whatever it's hearing, and that, whether that is the nearest neighbor, only one other individual, paying attention to the conductor, or to the totality of the behaviors that are taking place. All of those are possibilities. This is why I raised earlier in the talk the importance of the topology of the network of connections, again, which is very much addressed in the last talk.
Thanks a lot. Again, I wish you were here to discuss this more over coffee, but hopefully we can connect.
Unfortunately, heading to Dublin almost immediately for another meeting.
Well, thank you so much, Roger. Thank you for joining us. I'm just going to say that we're 5 minutes late, but I hope you don't mind if I cut your coffee break short by 5 minutes, and it's a 10-minute break, and we'll be back here again at 10:15. Thank you so much, and have a wonderful day, Roger.
Thank you. I will be joining.
Vinicius Carvalho, and he's a postdoc at RITMO, University of Oslo. Go ahead, Vinicius.
Okay, thank you, Maya. Thank you, everyone. So I'm going to present also on entrainment, but on a slight shift from cognitive to clinical. Starting to talk about epilepsy. It's a neurological disease that affects around 1% of the world population, more in developing countries. Its main hallmarks are epileptic seizures. And the main line of treatment are epileptic drugs, and they work in roughly 70% of the cases in which patients can lead relatively normal lives and when the seizures are controlled. But the worrying fact is that for many, many years, this figure of 30% of patients that don't have their seizures controlled, this number hasn't changed, even with the development and the increasing arsenal of anti-epileptic drugs. So it's still an advance that we have more drugs and more options of treatment, but this 30% figure of refractory epilepsy, in which the seizures don't respond to medication, still hasn't decreased. And in these patients, one option of treatment is surgery. So there's surgical removal or resection of the brain regions that are responsible for generating and maintaining the seizures. And as you can imagine, it's not a trivial task. So it's not a trivial surgery to perform it or to identify which region should be, brain region should be eliminated. And the non-invasive tools, non-invasive brain imaging tools that we have today are many times insufficient. So EEG or PET scans or CT scans, MRI, they don't work in some cases. And in these cases, the one resort is to the invasive monitoring. So that is the surgery that is performed to place electrodes deep in the brain. So this can be either in the form of grids that are placed on the surface of the brain, as in ECOG or electrical corticography, or with electrodes that are placed deep within the brain that are, you can see, okay. So this is one example of such electrodes that it has contacts along its length. So each one of these contacts is a point that measures electroactivity that's related to neuronal activity in the neighborhood. And based on some prior hypotheses or where the seizures are originating from, there's a planning of, okay, how many electrodes and where are they going to be placed. And the patients stay from 1 to up to 3 weeks, depending on the case and the hospital, with 24/7 monitoring, where their behavior, their brain activity is monitored. And in the neighborings, so for capturing abnormal activity before, during, and after seizures, so that the clinical team can pinpoint what's the course of action, which brain region should or should not be resected or removed. And this is, we believe there's room for improving this. So this is not an easy task for the patient, for the clinical team. So this involves a long monitoring. Many times it involves sleep deprivation of the patients. So we are aiming to have better tools for assessing and identifying epileptogenic regions. And we believe that one way to achieve this, to support this, is through active probing paradigms that have been used a lot in neuroscience and epilepsy. That's basically the idea that you get more information out of a system by stimulating and getting a response than you get by just passively observing it. So it's basically a way of getting brain responses as a way to highlight abnormal activity. And so we turn to the auditory steady-state response that has shown promise as a diagnostic tool for some neurological conditions. And that's basically entrainment by a rhythmic auditory stimulus. And this rhythmic stimulus can be in the form of sequence of clicks, of amplitude modulated tones, or tone pulses that are presented basically in a rhythmic way. And this entrains neuronal activity in the brain throughout the auditory pathway and maybe sometimes secondary brain structures, also in a rhythmic way. So it's a really useful way of tagging or of inserting an oscillation in the signal in the brain, and this makes it easier to analyze what type of brain activity that we want. So this is opposed to what many of you are also used to, that of auditory evoked potential, of transient auditory evoked potentials, in which stimuli are given, and there's an evoked potential, and as soon as you wait for the transient or the evoked potential to die, to take its course, and then you present it again. So this kind of steady-state response is a continuous and rhythmic stimuli, just to be clear. And this has shown promise as a diagnostic tool for schizophrenia, for bipolar disorder, for dyslexia, in which patients have impaired or abnormal responses. Also on Dravet syndrome, a very serious form of epilepsy. And also in epilepsy, a 2019 study showed that normally we have this asymmetry of response of monoaural stimulation. That is, if I stimulate with a sound on the right side, on right here, I get a bigger response on the left hemisphere. And the same if I present a response only to the left side, I have this bigger response on the right side. However, with patients that have a left epileptic focus, that is, the seizures are originating from the left hemisphere, when they presented this stimuli on the right, the responses didn't have this asymmetry. And the same happened on the patients with the right ectogenic focus. And that's not due to increase on one side, but to the decrease in the contralateral side. On the other hand, we had work from my previous group that showed on a very, very different setting, a very different model, that this rat strain, a genetic rat strain of Wistar audiogenic rats, show increased responses to the ACSR. So they were hypersynchronous and hyperexcitable. And also we have this example of Dravet syndrome that has, the patients have impaired responses. So we wanted to evaluate the hypotheses that we would find abnormal ASSRs related to the seizures onset zone or the epileptogenic brain regions. And this could be either in the form of enhanced ASSRs due to those epileptogenic neuronal circuits being prone to entrainment, or we could have reduced responses due to dysfunctional central auditory processing. Or we could, another hypothesis, of course, is that there's no change, or it's hard to evaluate what's an abnormal ASSR. And a secondary objective went to assess the distribution of the ASSR beyond primary auditory cortex. So the methods are quite, the task itself is very simple. It's a very passive task. We elicit the ASSR with AM sounds with 2 modulation rates, with a white noise carrier. We just ask the patients to rest with their eyes closed and play the task. And we quantify the SSR by the phase locking value between the stimulus and the response. And we assign for each contact whether it's a seizure onset zone contact based on clinical criteria, and we assign it to a brain region according to a parcellation algorithm. This is one example of signals from one electrode. So we have in blue the signals. And another thing that's important is to bipolarize the signal if you really want to see where the signal is originating from. So this is one example. So in blue, we have these 2 signals of neighboring contacts, and we have this big oscillation. However, if we want to see if the signal is really originating from that region, we just subtract these neighboring signals, and we see that this oscillation vanishes. But this doesn't happen for all kinds of activity. So this is, I think this is an easier way of visualizing it, of how this response looks like. This is a time frequency representation. So, oh, sorry, you don't see the... Yeah, so this axis is time, this axis is frequency, and here we have the different trials, either with 40 or 80 hertz modulation, and we can see a very clear response. This is a bipolarized signal, a very clear response on the modulating rate that we're given. Again, either at 40 or 80, and we have some harmonics also for both cases. So this is the first main results, that on this axis we have the different brain regions according to parcellation algorithm, and this is 40 hertz SSR. And in orange, so the orange dots mean that it's a seizure onset zone. And this, we have only a handful, only a few contacts that response, so this is not looking as expected. These are the only ones that would be in line with the first hypothesis of a really abnormal activity that will be in a region that doesn't display the SSR normally, and this one, that's a seizure onset, it has a huge response. However, on a closer inspection, on these specific two contacts, they are not, there was a wrong parcellation by the algorithm, so they are actually in here. There should be a transverse temporal gyrus. So this is primary auditory cortex. It should have a high response. It's still the highest response that we have, but on this case, I think we still can't claim that if it's an abnormal response or not. And this shows the distribution of the response for all the participants. So we have 25 participants in total, and this axis is the brain regions, and the percentage of the contacts in each region that shows the significant SSR. So in this case, for instance, this is brain region, the frontal region, that shows only a handful, only a small fraction of contacts that has the SSR. So the bottom line of this is that we have greater response, greater share of responses. These are first, I'm going to show first the monopolar and then bipolar primarily temporal in hippocampus, insula, putamen, and thalamus. But when we bipolarize and actually see where responses come from, we have precentral, superior temporal, transverse temporal, as expected, hippocampus, but that's only in some cases, and insula that have more robust responses. And another final result is that comparing 80 and 40 hertz SSRs, there's a tendency of having an increased 40 hertz, and that's expected for especially cortical structures. However, in insula and transverse temporal gyrus, we didn't find this, so we're still not sure what to make of this result. So in summary, we have greater responses in temporal, as expected, and postcentral and insula. We have inconsistent responses in middle temporal gyrus, in hippocampus, and putamen. And the main results is that we have very, very few contacts within the seizure onset zone that display the SSRs. So we have these limitations, of course, the patient heterogeneity. One important point that also involves other projects that I've been involved with, the passive nature of the tasks really limits the spread, the kind of activity that we can see. And another big limitation, the sound presented with speakers instead of headphones. With future possibilities, one can evaluate the SSR change prior to seizures and see if this can be a hallmark of impending seizures. We can contrast with similar results that we're running with a collaboration of ours with radio frequency thermal calculation that we have before and after intervention. As Chekaya mentioned, this top-down influence on entrainment is also a big topic. And we also have EEG that we can compare. So this work was conducted during my PhD at the Center of Nuclear Neurosciences in Belo Horizonte, Brazil, and at Mass General Hospital in Boston. Thank you.
Thank you, Vinicius. Very interesting talk about the also clinical relevance of neuroentrainment. So are there any questions in the audience?
Thanks, that's really interesting. I just wondered whether you've thought about venturing away from the 40 hertz stimulation frequency, because primary auditory cortex loves 40 hertz, but as we move away, at least in the auditory system, as we move outside of primary auditory cortex, the brain regions tend to resonate, so to say, at different frequencies, often slower frequencies. So I wonder whether you've thought about mapping more thoroughly by varying the stimulation frequency as well.
Yes, this is something that I think I regret not doing earlier. The rationale for choosing the 40 hertz was the first that's a higher frequency, so it's more salient. But on the other hand, it's also salient because it's of the roughness of the sound. So yes, I would. If I would do this today, I would make shorter, for sure, shorter trials, and pick more frequencies. Yes.
Thank you. Excellent question. I saw there was one in the back.
Thanks. That's very interesting. Do you plan to continue doing this work? Do you have access to patients?
I'm still not sure. So
okay.
we have this at the. So this data is from Mass General Hospital. We also had data collected at the hospital from Brazil, and this is a possibility of doing of gathering further more data. So yes, that's a possibility.
Okay. So question, have you looked at the actual phase at the different sites? Not just the phase locking value, but to see the phase and if you can see anything about different phase delays, for example.
Yes, that's something that I did some preliminary studies of. So there's a lot of work that I did, and either ended on dead ends or I just dropped for other reasons. But yes, that's one thing that I started doing, but eventually turned to other. But the point is, I don't have any strong conclusions about this.
But did it not seem interesting, or is that why you stopped, or too noisy, or just
yes, I think the reason that I stopped it was to focus on on the very simple. On the very simple in relation to the initial hypotheses. Yeah. But yes, doing the directionality, so a more network analysis and interacting. So this is something that I would be interested in doing. Yes.
And just one more tiny thing. When you looked at that harmonic of the 40 hertz stimulation, it was actually above 80 hertz, like 82 or something like that.
Oh yeah, it's not exactly 40. It's
okay. I just wanted to find out if there's. Okay, so it's truly a harmonic.
Yeah.
Okay, got it. Thanks.
Thank you, and thank you, Vinicius. We need to
thank you.
continue with the next talk. An applause for Vinicius.
hitting that. Yeah.
Okay, so our next speaker is Sandra Solli, and she's also working at RITMO here at University of Oslo.
Hi, I will present an ongoing project with the preliminary title Periodic versus Aperiodic Temporal Predictions, Shared or Separate Mechanisms. So we know that attention is a limited resource, and we use temporal predictions to orient our attention selectively in the environment. We dynamically select where and when to pay attention. For example, you will probably not have the same level of attention throughout this talk. It will maybe look something like this. But temporal attention can also fluctuate on a smaller time scale. When we listen to rhythms, we can align our attention to the beat as proposed by the dynamic attending theory. And this has also been linked to neural entrainment models, suggesting that oscillations in the brain synchronize with external rhythms and in turn align neural excitability to the rhythmic stimulus. This has been proposed as a possible mechanism of temporal predictions. When listening to an isochronous rhythm, as the one showed here, we can easily predict the timing of the next event and thereby allocate our attention and processing resources to the predicted time points. So this entrainment theory works best when attention, prediction, excitability are all in unison and in phase with the periodic predictable rhythmic stimulus. But some rhythms aren't strictly periodic, but they could still be predictable. It could, for example, be repeating patterns with a beat of unequal length, or it could be rhythms with a gradually changing tempo, such as in music where we have accelerations and decelerations. The entrainment model, at least in its most basic form based on oscillations with a constant period, fails in explaining aperiodic temporal predictions. So it's still an open question whether neural entrainment is kind of only accounting for periodic rhythms and predictions conveyed by them, or whether entrainment models can be more flexible than in its strictest theoretical sense and we need to update them, or whether neural entrainment does not play a functional role in temporal prediction. So we conducted an experiment where we aimed to disentangle prediction from periodicity, and we wanted to know, can sensory performance be modulated by both periodic and aperiodic rhythm-based temporal predictions? And if so, are the underlying mechanisms shared or separate? And then we also wanted to have a special focus on this dynamic attending theory and entrainment theory. So in the experiment, we presented 3 different rhythmic conditions. First, the isochronous periodic predictable rhythm. And second, we presented an accelerating rhythm, which we then call the aperiodic predictable. And last, as kind of control, pseudo-random rhythm called the aperiodic unpredictable, which is different for each trial. And the last interval is always the same for all the conditions, and after the rhythm, a target can occur at different phase positions. So either in phase, which is then the predicted time, or slightly out of phase or in antiphase. The aim is then, of course, to see if the target detectability or the task performance is modulated by phase position. And in the periodic predictable case, we aim to see if detection performance fluctuates with the preceding rhythm, as suggested by the entrainment theory. And this rhythm has been studied a lot before, but the existing evidence for this is not conclusive and it's still under debate. And then for the aperiodic predictable, we wanted to see if also here we could see a difference in phase, because we were thinking that you might could since it's still predictable, you could also allocate your attentional resources, but then to see if there is an effect of predictability without periodicity. And in this unpredictable rhythm, which is not without any predictable cues, but it's unpredictable in the rhythm sense, but it's still, I mean, in case you use the last interval only to form a temporal prediction, you can still have it from here, or whether you use the position of the targets from early trials, or so it still contains some predictable cues, but therefore used there as like a control condition, as it doesn't have the predictable rhythm. And then to the results. First, we look at the difference between these rhythms when the targets occur in phase. And here we see that people perform better for the periodic condition than the aperiodic condition, and better for the predictable conditions compared to the unperiodic conditions. So it seems like both predictability and periodicity enhance performance. And then we look at the performance and how it's modulated by phase position for the different rhythms. And then first, for the periodic predictable condition, the performance is best when it occurs in phase, and significantly worse before and in antiphase. So this is in line with what to expect from the entrainment theory. And then for the aperiodic condition, the accelerating rhythm, the performance is, maybe a bit surprisingly, not best when the targets occur in phase at the predicted time. And this shape is similar to what we see for the unpredictable condition. So my guess for this kind of shape could be that it's more related to the hazard rate, meaning that the temporal prediction is based on the probability of an event occurring, given that it hasn't occurred yet. So since if you probably have more attention when you don't heard it yet, but at some point you kind of give up and expect that you just missed it. Yeah, and since we see the same shape and we think that this kind of shape might be related to other processes than the kind of the rhythm, we use this aperiodic and predictable as a baseline and look at the other ones relative to this one. So then it looks something like this, and then you see that the shape of the periodic predictable is very in line with the enhancement of the in-phase condition. So in phase, both the periodic and aperiodic rhythms cause better performance, while the benefit from the aperiodic predictable rhythm is not that phase dependent and is better than the unpredictable rhythm also out of phase. So it could be the case that the predictable rhythm enhances the performance, but not with a very precise temporal resolution. And in addition, periodicity enhances the performance and with a narrower temporal resolution. So this might be evidence for entrainment in the periodic case, which then maybe not only enhances the perception in phase, but also suppress the antiphase targets. And yeah, probably forgot to mention, but this was also an EEG experiment, but we only have some preliminary results here. And we looked at the intertrial phase coherence, and we see that the intertrial phase coherence is enhanced for periodic condition compared to the aperiodic conditions. This is then analyzed in the window between the last sound of the rhythm and before the target. So this could be in line with the behavioral evidence of entrainment in the periodic condition only. Yeah, but here, of course, I don't know whether these ITPC differences actually comes from endogenous oscillations, that they could also be related to evoked activity, but we don't find any difference between conditions when we look at power. And then to sum this up, we see that both periodic and aperiodic predictable rhythms enhance sensory detection compared to a less predictable rhythm. But we only find evidence for entrainment and phase dependence in the periodic condition. So then trying to ask the question that was actually in the title, whether there are shared or separate mechanisms, we we could assume that there are separate mechanisms and that entrainment is the mechanism underlying periodic predictions and something else for aperiodic predictions. This is also in line with a couple of previous studies where they look at periodic prediction versus this pattern-based aperiodic predictions. But we could also assume that there are a shared underlying mechanism of rhythm-based temporal prediction, but that periodicity adds something more. Periodicity affects sensory performance, but it's not necessarily related to prediction or attention. So, at least for now, I would suggest that periodicity adds a temporal processing benefit in addition to predictability. But hopefully we'll find some more evidence for this when finishing the EEG analysis and also trying to relate the EEG activity to the performance. So, thank you.
Thank you so much, Sandra. That's very interesting and good presentation. Are there any questions? I see one in the back.
Hi, thank you. This is really nice work. Just a quick kind of clarifying question about the method, because can you go back to your kind of method slide with the three conditions? So in the aperiodic predictable condition, you're kind of indicating in the figure that you take the last duration, and then the target tones appear in relationship to the previous duration, but that duration, that duration should be becoming shorter, right, or briefer?
Yeah, it is. So I didn't, I forgot to make that clear, but the green line, the kind of definition of the correct there is the as if it would continue. So you're also instructed to predict it to continue to accelerate.
Okay, yeah.
And we also did a separate test where we actually tested where they predicted it to occur, and that was slightly later than what we define as, based on the kind of mathematical model, as on time. It was slightly later, but not as late as being the next position. But
Okay, thanks. So that, then the, what is it, purple line where people performed better, could that be evidence of kind of the periodic, like the entrainment capacity? Because I guess due to the speeding up there, the purple line might align better with the previous duration, if that makes sense.
Yeah, of course, that could happen. So, but then I think if it was, would have continued to be, if you kind of predict it to stabilize and stay at that tempo, it will be somewhere between what we has a zero phase and as the next phase position. Yeah. So, but yeah, so that was also my first thought, that since they performed best there, if that's actually where they predicted to occur, but since we also saw the same in the random condition, that's why I was thinking it might be something else. But of course we can't know that for sure, and ideally we should have sampled every time point here, but
yeah, I mean, unless it's kind of you're in training with just two events essentially.
Yeah.
Right, and then the same mechanism could explain the performance in the AP and AU conditions.
Yeah.
Yeah. Okay.
Yeah.
Thank you. Any other questions from the audience here? I'll check also the YouTube chat. Okay, but there is one here.
Thanks for the great presentation. Maybe I have missed something, but could it be that the aperiodic predictable stimulus is longer than the other ones, and could that have an impact on the results?
Yes, of course it could be. So I choose to have them similar in terms of number of events, but of course that one is then also longer. So of course if you use some kind of other statistical, then you could also predict it to occur a bit later if you're more like using the average interval from the previous tones or something like that. So yeah, that could be affecting, yeah. Yeah. Yeah, yeah. Yeah.
Thank you. Since we have a little more time, I would also like to take the opportunity to ask a question. So, because you mentioned in your conclusion, you mentioned that there have been also some studies showing that there's a different type, maybe mechanism to this periodic versus more interval-based predictions, this more memory-based. Do you think the aperiodic is like there is a similar mechanism to this interval-based that they found before, or do you think maybe it's another different maybe mechanism in play?
Yeah, so the other studies, at least that I've seen that compare like the periodic and aperiodic, they use this kind of pattern-based where you have some unequal intervals, but which is predictable because they are repeated. And they find, like, at least some of them report like a C and V effect for to be like a neural correlate for that kind, and that might be related to the more like memory-based kind of predictions. And I think that at least this accelerating and decelerating rhythms is maybe something else then. So then that's also why I choose to look at that, because that's kind of another example which is still kind of beat-based. It's still kind of a beat, but not in the periodic sense. Yeah.
That makes sense. Thank you. Okay, let's give a hand for Sandra and continue with the next speaker. Okay, so then we have the last speaker for this session, Sabine Leske, and she's a postdoc at RITMO here at University of Oslo. When you are ready, Sabine, just start.
Hello, I will talk about the prediction of the beat bin, and this is a study, EEG study that we conducted here at RITMO to investigate how the brain predicts the temporal precision of a rhythmic event. So neural entrainment offers a very parsimonious explanation how temporal prediction of events that are periodic could be performed. And this concept is visualized here in this schematic figure, how the phase of the oscillation resets to the external input. But actually, most environmental rhythms are not strictly periodic, but rather quasi-periodic. And
For example, a speech, a syllable could be stretched out in time, or a musical note, and then it is more beneficial to widen the window of the perceptual processing. And since the regularity of rhythmic events are quite variable in the environment, it is crucial for the brain to be flexible and to be able to dynamically adjust sensorial temporal predictions. And this could be realized via a top-down drive, as is also in the schematic figure visualized here, as a top-down drive on the oscillation. And actually, research in human rhythm research has already investigated this, as studies by Anne Danielsen et al. So they already show that the perceived precision of a beat is actually, it varies systematically with the acoustic features. So you can measure the temporal precision via the perceptual center. It's also called the P center, and this P center concept is known from speech research, and it depicts how a sound is localized, perceptually localized in time. So it doesn't coincide necessarily with the onset of the tone as it is depicted here, and it can vary and it can have a range. So this has been put forward by music research to also that in the perception, or that the perception of a beat is also actually not defined as a point in time, but rather as a probability distribution, or better defined as a probability distribution, as it is visualized here on the right side. And this concept has been referred to as the beat bin by Danielsen et al. So if you ask a person to localize a sound in time, then it will be more precise when it is a sharp sound that has a short rise time. And it will vary a lot more when the person is asked to localize a sound in time that is more smooth and has a longer rise time. And you could say the person is rhythmically more tolerant, or you could say the perceptual precision is lower in that case. So in this study, we are interested in how the prediction of the auditory stimulus shape affects the temporal prediction of sounds. And we want to understand how the brain predicts rhythmic events with varying temporal precision, and if this mechanism is under top-down control. So the question is how the brain predicts the temporal precision of a beat. To investigate this, we used the cueing paradigm, and we presented sound cues that informed the participant about the acoustic shape of a target sound at the end of the sequence. So thereby, we induced two different levels, a high precision prediction and a low precision prediction of the target at the end of the sequence. So we make use of these results that already have shown how these acoustic features influence the precision of beat perception. And the participants had to detect the delay of a target sound at the end of the sequence, and the sound cues were, in most of the cases, the sound cues were valid. So the acoustic shape of the cue matches the target sound. I will play some examples to you so it gets a bit more easier to understand, but it's actually a quite simple paradigm. In the invalid case, the cue does not match the target sound. So you could also say, in this case, the listener predicted the wrong temporal precision. I would play a valid high precision prediction condition, an example. And an invalid low temporal precision prediction. It has its own life now. Okay, stop it. Maybe by selecting the slide. Okay, we got out. And the behavioral results show that the information of the cue is indeed used by the brain, and it modulates the delay detection performance. So the anticipated temporal precision affects the perceptual sensitivity for the high precision target, as you can see here. So if the listener actually expects a low precision sound, but the actual presented target was a high precision sound, then the delay detection performance decreases. And we don't see this effect for the low precision target, which is not affected by the cue. Or the performance is not affected by the cue, and this might be a ceiling effect since the temporal precision of the target is already low. It's not detrimental to prepare for a high precision target sound. So that might explain this result. And in the classic sense, as we have seen in other talks and also in the first slide, the phase of reset of an ongoing slow oscillation is considered to be the mechanism underlying neural entrainment to external rhythms. However, it has been proposed and shown that the motor system is also recruited during rhythm perception, even during passive listening, and that temporal predictions might be encoded in the beta activity, which entails higher frequencies between 13 and 30 hertz. So the idea is that external inputs could also be linked with rhythmic motor activity that resets the neural activity in sensory areas. So this has been referred to as a covered form of active sensing. So the motor system might be more flexible in predicting temporal dynamics at a small time scale of tens to 100 milliseconds. So here you see beta power activity between 15 and 25 hertz, and during the entrainment period, starting with the first entraining sound here until target presentation. And for some electrodes, we see that this beta activity seems to align with the entraining sounds, at least for the high precision prediction. So in red, you see that all the trials where a cue was presented that predicted a sharp sound or a high precision sound. And in the last entrainment interval, before target presentation, this beta power is significantly increased for the high precision prediction. So this is in line with other studies that have shown that that beat perception and also temporal prediction is related to beta activity, as for example the work by Fujioka et al. Or Morion. And we also were interested in to see if there's a spectral modulation of this beta power time series. And interestingly, there's a peak in the delta range between 0.6 and 3 hertz, which coincides with the entrainment rate. And it is significantly higher for the high precision prediction. And in addition, we also found higher phase locking. So
a higher intertrial phase coherence. And this was in the beta range, but also in the alpha frequency range. And the beta power also correlated positively with behavioral detection performance. So here you see beta power in the last entrainment interval, but it correlated negatively with the P-center variability. So we also measured the P-center variability to all the sounds. So this shows this tight relation between beta oscillations and perceptual temporal precision, as we think. So we think that we were able to show that beta band oscillations subserve neural mechanisms that are responsible for top-down predictions regarding the temporal precision of sounds, and that are embedded in a beat sequence. And these beta oscillations might be involved in the active top-down control during neural entrainment to rhythmic events. And the results so far are in line with the active sensing framework and studies relating beta activity with beat perception and temporal predictions. There's a preprint online on bioRxiv, and I would like to thank you and my colleagues who are involved in the study.
Thank you, Sabine. So now we have time for questions.
Thank you very much for the presentation. Have you done or are you planning any source estimation on the EEG data?
Yeah.
What would you expect?
Yeah, of course, it would be very interesting to see if this really originates from motor and auditory regions. So we could, so with the data we have, we could try to sociolocalize the data. It might be a bit tricky since we don't have the individual sensor locations. So it would be more like a first impression of where this activity might come from. So yeah, I think, yeah.
Any other questions? I find it really interesting, the study that you've done. Could you also maybe say a bit more about the relationship between the EEG and the behavior? You show that there was a correlation there. What was it, the meaning, in a sense?
Yeah, so we correlated beta power in the last time interval with the D prime measure, so with the perceptual sensitivity. And this positive correlation means that the higher the performance, the higher the beta power contrast. So yeah, maybe I did not explain this well enough. So we correlate actually the difference between the high precision and the low precision condition. So this is the beta power effect for each participant correlated with the behavioral performance of the participant. So it shows that the more it's modulated, the better they perform in the delay detection.
Yeah, very interesting.
You can also check the YouTube. Is there a YouTube ID?
Do you know if can we see the YouTube chat? There's no questions there. No. So if there are no other questions, then I think we can end the session and go. I guess we go for break. Is it? Group photo. Okay. Yeah. Great.
Yes. So if yes.
So if you would be so kind and follow the directions of our lovely photographer Annika in the back. And of course, if you do not want to participate in this group photo, that's also fine. You can make a run for it. But otherwise, please follow the instructions by Annika. Have 2 minutes until they arrive.
Come in, gather.
Welcome back to the Entrainment Workshop. Up next, we have Laura Bishop and Finn Upham, two local Ritmoians, presenting Bodies in Concert. Take it away.
Thank you. That makes it sound, well, anyway. Okay, so Bodies in Concert. This is about a project that we conducted in February. It was a collaboration with the Stavanger Symphony Orchestra. They performed a series of children's concerts, and we measured the conductor, the performers, as well as the audience throughout these several sequences of performances. This talk is going to be sharing some of the patterns that we're observing as we dig into this data. This is a lot of different measurements at once, and we'll be focusing mostly on the performers in this time round. So here we see, for example, we have the conductor being measured, the body position, as well as eye tracking, and then the performers were wearing these physiological measurement devices that also capture body sway. So underneath their concert clothes are vests that were fitted to them, and the audience was also being tracked in their hand motion using infrared recording. But today we'll be focusing on these. So we also, by the way, for some sections of the orchestra, we were measuring the cellist and first violinist's bowing hand motion to be able to get very close to the action of playing for them as well. So first, let's take a little bit of a look at what the coordination is across the orchestra over repeated performances. So this is just a quick plot of the body sway of each performer during the repeated performances of a specific piece. This is the Rudinsky March, and you can see per section we've got each person's body sway in time. And each row of these indicates sort of how much movement they're showing in time. And there's a couple things to notice in this kind of tartan pattern that we get in these plots, and that is that there's a lot of consistency in which sections are active when, which you would kind of expect, right? It's related to the action of playing. But there's also, particularly after the dress rehearsal, a lot of consistency in time as well between repeated performances. And that's because this is a professional orchestra playing music that they know, for the most part. And so their audio output, as well as their sort of physical action of performance, is very consistent from one performance to the next, which is fabulous, because that means that we have it almost like a control against which to measure fine changes and differences, and also internal systems that may or may not be quite as consistent as this. So one of the systems that we want to look at in relationship to performance is respiration. These are plots that are sort of the same nature as I showed before, but here yellow indicates when a particular performer is inhaling versus exhaling. And we have a different piece of music, and we see there's like a huge range of textures here, but there's also moments of alignment in particular sections that are repeated across performances. And that, for example, this is the brass players, and so yeah, we expect the respiration to be pretty well aligned to the music. But what is happening with everybody else? One way to look at this in combination is to actually, as opposed to doing this macroscopic thing, to focus in on how people are actually breathing as we watch it, to see what kind of patterns there are within sections, what kinds of alignments might be related to the musical action, or whether, for example, for string players, do they really need to be breathing in any way that's consistent at all? So here is a little visualization to help share with that. It's just the first part of a very interesting piece of music that we commissioned for this. And here, purple indicates when they are breathing out strongly. Green is when they're inhaling. And this visualization pours the present out is in the middle, and it carries the last 3 seconds of respiration. Indicates the sections going counterclockwise, so the conductors are the only one, and then the violin ones and around. And the little dots indicate who is actually playing. Black dots, who is playing, gray, who's about to start playing. So this will give you an idea of the breadth of information that is there in these performers' breathing as they are playing a piece of music like this. Okay, sorry for making your eyes feel weird. It's fascinating to watch this because there is such a combination of things that are clearly related to the music and things that don't seem to line up at all, because respiration is complicated like that. But there's some patterns of alignment that are important to point out. Obviously, there's the functional respiration of the winds, but in the strings and the percussion, we also seem to see instances where respiration seems to be aligned to musical actions. Entries, sometimes. And there also seems to be patterns of patches where across a section, for example, in the strings, they are aligned maybe for other reasons. And so we're interested in using this information to consider how respiration is maybe part of how people are coordinating their behavior. Now, that's across the orchestra. What about within players? Because we have all these recordings, we can align measurements from one performance to the next to see whether their bodies are in the same states at the same mind. So I'm just giving a little sampler of patterns that we're seeing here in body sway, respiration, and in heart rate features. So the body sway tends to be very consistent. Respiration for this string players, violin 2, seems to vary a lot actually from performance to performance. There isn't a locking into particular phase, but there are these striking moments of alignment in respiration phase with the music at specific. It's not totally locked the same we might see in a wind player, but it is still repeating across performances. So it's kind of like phase related to the music and then not, and then phase related and then not. When we look at the heart rate information, it's startling that there's a lot of consistency from one performance to the next in the contours, but there's a huge range here, a big difference in beats per minute from one performance to the next. And that really suggests that there's a strong separation for these performers who are expert players, who do this all the time and are playing for a bunch of kids. It's not the most stressful situation. There is still quite a range of cardiac states that they are in while still having this kind of adjustment of intensity with when they are playing or not. Last, we're trying to look at heart rate variability in a way that's related to the real-time action here. And in this case, we don't actually see a lot of consistency between performances. Yeah. Whereas, for example, for this cellist, the heart rate variability seems to have a concentration at this moment when they aren't playing. Now, we could go on about this stuff for quite a while, but just to give you an idea, this is what respiration alignment looks like in brass players. So it's a whole different category and for a bunch of different functions. Now, Laura can talk about the string players, some in particular.
You can keep that one. I have. Right, so Finn has been talking about interpersonal coordination broadly across the orchestra and also consistency within players across repetitions of the same music. At this point, we're going to narrow the focus and zoom in onto smaller periods of time and also look more specifically at individual sections of the orchestra, particularly the strings. So there's a great potential for actually very precise synchronization in the string sections, given that the people are actually playing exactly the same thing most of the time. Even though individual players, depending on where they're sitting in the section, can have very distinct perceptual experiences, both visually and acoustically. So in this part of the study, we're looking at synchronization in the bowing motion of the string players for cellists and violinists, and I'm just going to give you a little introduction to what we have been looking at with the cellists. So as Finn mentioned, we captured bowing motion data with an accelerometer placed on the right wrist of the musicians. Here we see a couple of examples of the data for small periods of time. On the left, this is an excerpt from an R-band piece, and we can see that in this case, the note density is very low, the motion is very smooth, and actually in some cases it's very difficult, if you're looking at the curve, to see where the notes actually start and end. This is in contrast to the example on the right, which is a passage from the Christofferson piece. Here we have a very different type of articulation. The notes are staccato, there's a higher note density, and it's actually very clear
with this pattern of sharp peaks and troughs in the acceleration signal where the notes are starting and ending. Overall, it's not very easy for us to define the relationship between bowing motion based on the acceleration data and sound onsets. And here I would refer to the work of Anna Danielson and others on the P-center of these kinds of sounds that have gradual onsets. And particularly in this case, the relationship between the sound producing motion and the sound onsets is further complicated by the fact that the musicians are, well, differences caused by the use of different bowing directions and also different articulations. So one of the hypotheses that we're going to be testing with this part of the project is looking at the relationship between precision and synchronization and different aspects of the musical structure. So specifically, we would predict that precision is reduced when the rhythms are more irregularly timed, or when there are longer inter-onset intervals between notes, particularly without subdivision. The piece that we had commissioned for this project by one of the professors at the musicology department, Martin Christoffersen, this provides a particularly interesting context to look at this hypothesis because the rhythmic texture changes quite a lot during the course of the piece. So how do we go about measuring synchronization in bowing motion based on accelerometer data? Currently, we're doing this in two ways. We're looking at group synchronization across the 5 cellists, in this case, who wore the accelerometer. We're also looking at pairwise synchrony between pairs of cellists, and this gives us an opportunity to look at the potential effects of physical proximity, so those who are sitting next to each other versus not. For the measure of synchrony, since we tend to have this pattern of peaks and troughs in the acceleration signal that are approximately located where we would expect note onsets to occur, we find the midpoint between those peaks and troughs. We do this for all of the different players, and then for the group measure of synchrony, we take the standard deviation of the timestamps for those midpoints as our measure of variability or synchrony precision for the group for that note. For the case of pairwise synchrony, then it's just the temporal offset between the 2 midpoints. So here we can have a look over one excerpt from the squabble measure overture. In this particular excerpt of about 20 bars, the rhythmic texture changes quite a lot. So in the beginning section, I'll play it in a second. In the beginning section, the musicians are kind of alternating between having to match 6 notes to this 4-beat meter versus playing actually on the 4 beats. And then as the section goes on, the notes become further and further apart as the music kind of peters out. So you can see this in the vertical lines are the estimated position of the notes here. I'll just play a very little bit so you can hear it. So you could hear that change in the rhythm. So what we're showing here in the bottom plot is the standard deviation per note across the 5 cellists. And we can see that there's this tendency to have larger asynchrony, so larger standard deviations in the parts like here, where you have these more complex rhythmic patterns, and also when the notes are more spaced out in the end, and it's more difficult to predict the timing. So trying to bring all this together a little bit, one of the things that we're going to be doing going forward is trying to bring these different domains of measurements together and see what we can learn from them in combination. So here at the top of the slide, we have the same sort of plot from the previous slide, but here it's data from all of the performances. And the bottom graphs refer to fin created, representing the patterns of inhalations and exhalations, also averaged across the performances.
Yeah, it says representing who is in what phase of the respiratory cycle when. And so the peaks represent when there's a particularly high concentration across performances and players of the same phase. And we see these peaks in alignment coinciding with some of these onsets. So for example, there's a peak in high flow inhalation with many of these onsets in a way that is way above what we see in other parts of the music.
And so the aim here would be to kind of test the prediction that the string musicians are using their breathing as a way of helping to regulate their timing in cases where timing is difficult to predict. So we don't have any conclusions yet since we're in the beginning of analyzing these data, but we can say a few take-home messages for you. So first of all, even though we would presume that symphony orchestras play to a consistent quality and they maintain their interpretation across repetitions of the same music. Have I been cut off? Yeah. We see, particularly in the heart rate, that physiological states are varying between performers and across repeat performances. We also see that the dynamics of cellists' sound-producing motion are more variable when the rhythmic context is more difficult to predict. And we suspect and we see some preliminary evidence that string musicians might use their breathing to help regulate the timing of their bowing. Thank you.
Thank you so much, Lauren. Finn. I'll just steal the first question here. Finn, those analyses on respiration are awfully cool. How could I ever possibly learn to analyze data like that?
Well, it just so happens that I just published a Python library specifically for analyzing respiratory phase and measurements like this. So maybe since I have a workshop happening in a couple of hours,
at 2:30 in Auditorium 1.
you might have a chance to learn more about the how and the why and the what of that kind of analysis. Amazing. Thank you.
Wonderful answer, Finn, for the very complicated question. Are there any questions from the audience here? Wonderful.
From the perspective of a string player, of course, the onset of a note is not just a change in direction of bowing. That's not required. It's a combination of bow speed and bow pressure. So I was just wondering if you have multi-dimensional accelerometers, whether you could integrate those measures into a bow pressure measure. It might be more closely correlated with the onsets than what you're describing, perhaps.
Yeah, that's a really good idea. This is three-dimensional accelerometer data, so we can try this. Thank you.
Brilliant. Any other questions from the audience?
Did you look at what happens in syncopations? Maybe breathing is important there.
This is also a good prediction that we can test because we have a lot of music here and some of it is syncopated. Yeah, thank you.
There's a mountain of data they have to sift through still. So they're doing brilliant actually because this concert just happened in February. So it's incredible, I think, the amount you've done already.
Wonderful work. Apologies if this is obvious, but at least what I know of string players is a lot of coordination happens at the phrase level rather than at the beat level. So do you have anything to say about that?
I guess initially just part of the challenge here is encoding the musical information in a way that we can integrate well with all of these measures, but that's ongoing. And do you have particular intuitions about movement and phrasing? Respiration and phrasing in string players obviously will be a question. But
yeah, I guess so from what I've looked at so far, this is already a bit of a point of uncertainty for me, how I'm going to actually look at the coordination based on this sensor data. Because whereas you can see the changes in bow direction very well at the beginning of a phrase, unless they are already in motion, sometimes it's actually hard to see exactly when they are starting to play, although maybe looking at bowing pressure would help there. So probably this is something we should look into, and also maybe, if possible, taking into account kind of the preparatory gestures.
One of the funny things in looking at respiration is that there's a big difference between players in terms of how often the respiration seems to have a kind of regular alignment with the music, and which suggests that the way in which string players use this kind of thing may be very individual and may be conditional on the role they're playing. For example, if they're concertmaster or first desk, would their respiration actually be part of a kind of communicative strategy that would then make articulation of phrase onsets different than if you're, further back and maybe don't have to worry about that this time around. Yeah.
Thank you so much. We now need to move on to the next presenter, so I welcome Ellen to the stage.
Oh, hello. Oh,
Perfect.
very
Do
exciting.
you plan on moving around?
No.
But I'm actually still going to clip it.
You
to
can
the
clip
string,
it.
maybe.
Yeah, that's fine.
Perfect.
Great. Okay, let's see if I can put my slideshow up. Yeah. Okay, I think we're good.
All right, so next up, here's Ellen with Moving in Time, the effects of interpersonal entrainment on in-group, out-group bonding, and social identity.
Hi, everyone. Thank you so much for having me. I'm all the way here from Southern California, so I've decided time is a construct that I'm not paying attention to. So I'm really happy to be here. So we all know a lot about entrainment. So, interpersonal entrainment defined as joint synchronized action, typically multiple co-actors coordinating together to a common rhythm. Again, woven throughout society in many different facets and ways, and again, theorized to create and maintain common group mentality, this sense of social glue that ties people together. We also can see ways in which interpersonal entrainment can be used as a system of credible signaling between people of different groups, either to establish coordination or hostility or competition in some way. So this lovely paper by Cross and colleagues looked at a couple different major theories of the evolutionary benefits of IPE and group formation in particular. So comparing these two theories, one is the social bonding explanation, which is on the left. And it suggests that IPE causes group formation through the increase in affiliation or overlap amongst co-actors. And this is in contrast to their second theory, which is the social identity explanation, which suggests that IPE causes changes in sociality due to individuals actually recategorizing themselves into a more interdependent identity rather than an independent one. Let's see why this is happening. Yeah, I think we're good now. Okay, so this brought up a question for me, right? Is it possible to use interpersonal entrainment? I specifically used a drumming task to change people's individual identities and pro-social behavior between people from different groups, right? So we have a lot of research that's looked at the way in which entrainment pulls people together who are already part of the same group, but there's a little bit less out there about bringing people together and bridging divides between different groups. And more importantly to me is, if this is something that we can do, can we actually utilize it as a means of improving prosociality between people from different groups? So this study aims to assess that relationship between group identity and interpersonal entrainment to determine the efficacy of it, to actually reduce divides and improve prosociality. And in addition, I also had the question of, does the accuracy, how good someone is at entraining, have any impact on your rhythmic skill, right? Does the rhythmic skill with your partner actually matter, right? Or is it just that you're having a shared musical experience together? So I did this with young adults aged 18 to 35. All of them who participated in my study could not have any sort of prior relationship with one another, so there couldn't be any sort of influence of prior group participation. Sorry, guys. Let's see if I can pull this back up. I think it's just the connection. I'm going to try a different port. One moment, please.
That's your adapter, or is this ours?
This is yours.
Okay.
Okay, that's alive again, so let's try this. Okay, sorry. Oh, no, it's okay. Part of the fun of live presenting. I think we're back in business. Okay, great. So again, young adults couldn't have a prior relationship with one another, and we had a total of 106 in the end who participated, and they were placed into two different conditions. So I'm going to walk you through the design of this a little bit. So everyone came in, they were grouped into groups of 4 for this study. And immediately upon arrival, all participants took part in an aesthetics test. So this was actually a minimal grouping paradigm, but they didn't know this at the time. So they were all given sets of paintings, and they had to list their preferences of the types of paintings that they preferred, and then they were put into groups, and they were told that it was because of having shared artistic aesthetic preferences with the other individuals. In reality, they'd been previously randomized, unbeknownst to them, into their different groups. They then were given 10 minutes to get to know each other. They formed a group name as well as a group mascot, and they wrote these down and drew them and wore them for the duration of the study, and were also referred to each other, so maybe Team Tiger versus Team Shark, for example. So after they had this initial bonding experience with their in-group member, everyone took part in a set of independent questionnaires as well as a public goods game. So in these questionnaires, they assessed their initial sense of bonding with their group members as well as with their out-group members. Oh my goodness, I'm so cursed. No, I'm like not touching it at all. It's okay.
We can also, worst case, we can pull it up on the other computer, and if you really want to do the switch now.
I have no idea what's better. Whoa. Oh my.
Okay.
I'm not even attached to it right now. It's just doing that.
Can you email me the
I'm not attached to the internet, so that's going to be a little bit challenging. We can try.
What's this?
We can try that.
Put that in there? Or like just put it in your laptop? Oh, you don't have a thing.
But I bet we can make an adaptation. This one, right? Yeah. Let's try this one. Maybe let's try that. Sorry, everybody.
Not your fault at all.
We even tested it, and it was so happy before. Allow.
Oh, that's the fast PC. Why is it not even showing that?
Yeah, it's really.
Oh, I think it's also.
It seems like it kept giving out.
HTML is working now. We're good.
Okay. Attempt number 3. Okay, so they did many questionnaires that looked at entitativity, group affiliation, perception of their identity within their newly formed groups, as well as an assessment of their own empathy. And then they also did a public goods gambling game. So in the gambling game, they were given tokens that they could either choose to keep for themselves, give to their group member, or give to a community pot that would go to everyone who was in the study at that moment. And so individuals who hold on to their tokens or who share them within their group are thought to show more in-group benefits and preferences, whereas if you contribute to the communal pot, that indicates a more community benefits toward out-group members and in-group members together. So after they did this, they actually took part in the entrainment intervention. And there were 2 possible conditions. So half of the participants were placed into entrainment where they drummed with their own partner from their same group member that they'd already been paired with, or they were put into an between group condition where they drummed with an external member, so the opposite group. So let's talk about what the actual entrainment intervention was. So I decided to use drumming, the reason being it is much more accessible. It's very easy music activity if you don't have any sort of previous musical skill. You have the ability to typically be able to grab onto a beat. And then participants also played along with their partner during this to a series of pre-recorded drum beats. We had like 4 or 5, I think it was 5 different conditions that they could drum along with. So let's just, for demonstration purposes, so let's do this one of the simple ones first. So everyone get your hands. You don't have drums, but you have hands, right? So everyone drum, clap along with me. Nice. Okay, let's do one of the more complicated ones, okay? All right, wonderful. You could all be in my study. Okay, so these were the beats that they all did with each other. We recorded this with microphones using these little drum setup, and that would allow us to also determine the entrainment accuracy of how in sync they were with their partner during this entrainment measure. So following the drumming session, they took those same questionnaires and also played that same public goods game again, so we could see the impact the entrainment had on their relationship with their partner and with the outgroup members. So this was assessed. We used a multi-level model. We used fixed effects of time and condition, as well as the time and condition interaction, and then random effects of session, ID, right, because there were different sessions that took place over multiple weeks. And then we looked at the co-varying effects of entrainment accuracy, so we split that into easy versus hard entrainment accuracy to the beats, as well as their own empathy and maybe previous music training that could have an impact on their skill level. Important thing to note, we did check to be sure that the minimal groupings worked, so everyone did feel more bonded to their in-group member after the initial minimal grouping, so that meant that we had a difference between in-group preference and out-group preference at the start. So I'm going to show you a few different graphs. We're going to be pretty quick, but on all of these, condition is on the x-axis, and then the dependent variable is on the y, and then the blue is before they entrained, and orange is after they entrained. So first things first, there was no impact of entrainment on in-group bonding, so both conditions within and between didn't really cause a difference in how bonded they felt with each other, but we did see an impact on out-group bonding for the between condition, so individuals who drummed with an out-group member felt closer to that person than they did before they drummed. We also saw an impact in terms of connectedness. So drumming with your in-group member makes you feel more connected with them. Same with drumming with an out-group member. So this effect of having this shared drumming experience, everyone felt more connected with their drumming partner. This was also true for affiliation, as well as entitativity, so groupiness, if anyone is unfamiliar with that term. So we saw this similar effect. Everyone who drummed with the other person felt closer to that person they drummed with. In terms of self-control, this was like the identity measure. So we don't see an impact of self-control with the in-group, but we do with the out-group. So people who drummed with an out-group member suddenly had this greater sense of interdependence with that out-group member person as opposed to feeling like an independent individual. And then in terms of the public goods game, people, I'll remind you, you could either contribute to your own personal account, a group account with your group member, or a communal account. And no one really changed the amount they put into their personal or their group account, but we did see an impact of the amount of money put into the communal account. So when individuals drummed with an external member, they gave more money to that community pot. And then when they only drummed with their internal member, they gave less to the community pot. So something suggesting there that there is some level of impact that is occurring. And then two other things, well, one other major thing to note is that empathetic concern has an impact on prosociality toward outgroup members. So if someone is naturally more empathetic, there is a greater likelihood that they are going to feel a stronger bond with the outgroup members after they drum. So just to summarize, drumming with an outgroup member does have positive impacts on social bonding. It improves cooperation, and we don't see the same impacts on in-group pairs on that between condition. In addition, the drumming with outgroup members seems to shift personal identity toward this interdependence perspective rather than just an independent one. This could be because the in-group members already reached that sense of interdependence from that minimal grouping that occurred earlier. And then the results also suggest that the prosociality seems to improve with the individual that you perform drumming with, regardless if it's someone from your in-group, someone from your out-group, your prosociality improves overall. Finally, the accuracy of entrainment to one's partner doesn't really seem to have an effect. We looked at it with all of the different conditions, and it seems to matter more that you're having the shared musical experience rather than how skilled you are at being in sync with your partner. So that's something to further parse through. We also thought about maybe adding some additional challenging elements for the drumming conditions. But overall, the findings suggest that, this could be used as a means of changing social identity and prosociality to reduce divides. And just a couple limitations very quickly. This was done with minimal groups, right? So I would really love to do this in more socially relevant groups, either with people from different races, religions, socioeconomic statuses, something that actually has a little bit more social weight. I would also want to do this comparison maybe with a drumming out of sync or a simple like drumming improvisation system, and or some sort of non-musical collaborative task to see, is it just the shared experience that's having this impact? And then another step that we're hoping to take is looking at mobile EEG with drummers. So if anyone here has ever done any hyperscanning, I would love to talk to you because I know nothing about it, and that's one of our next steps. So thank you so much.
Thank you so much. Are there any questions from the get-go? And if not, I was wondering more about the, what kind of variability do you see in actual performance of entrainment? Because you said that there was no influence, so were everybody really, really good at this?
Yeah, so good question. So I mentioned that we had a couple of conditions. We had like more of that simple, keeping a steady beat versus some more syncopated patterns. So we split those into like hard entrainment versus easy entrainment. We didn't see any ceiling effects. Overall, the steady beats had higher entrainment. I think it was 0.82 or something, close to in terms of their statistic accuracy with each other, but then we had as low as like 0.5. So there was pretty significant variability.
What is that number actually?
Oh, I'm sorry. Yeah, so we utilized circular statistics to determine how close or far away they were from their partner in terms of their synchrony, and so perfect would be 1.
Okay.
Mm-hmm. Yeah, so we had a pretty wide range of variability. So
interesting.
Yeah.
Cool.
Yeah.
Since you're entertaining other tasks, what do you think would happen if you had a task that involved some kind of competition as well?
Yeah, I thought about this. I don't know. So I know there was a study that was done using fraternities and singing. I don't know if anyone's read this one, but there was a researcher who had fraternities either sing in competition or coordination with each other. And I believe they did find that when they were asked to compete, there was actually a greater disparity between the fraternities versus when they sang in coordination with each other. I don't know if the purpose, like if that intention behind it matters or not. I would guess that if you were asked to compete with someone, then that could increase divides rather than reduce.
And rather, I was thinking more that to be cooperating with someone in a competitive context where their performance matters differently and you can win or lose together, that brings another element to this that maybe too complex.
Right, so you're saying like possibly having the pairs like compete to be the best. Yeah, I kind of like that. It's a nice idea. Thank you.
Thank you for your presentation. I'm wondering, for the pre-post effect that you're seeing, how much do you think is due to the rhythmic task, or if you thought about like trying a different type of task that's non-rhythmic? Like if it's just the shared experience or the shared musical experience?
Right, that is one of the reasons why I want to add some tasks that are not entrainment-based, right? So because right now I don't have a condition that is not rhythmic. So that's why I want to add a non-rhythmic one to see if we can determine that. Right now I just don't know. Yeah, so that's in the pipeline hopefully this fall. Yeah.
Thank you so much. Okay, one final question from John.
So in the group composition, it sounds like you created empathy within groups, but you didn't really control any relationship across groups. Like I just wanted to clarify that. Was there any, this was kind of like within versus neutral, or did you create any kind of like antipathy between groups to start with?
So suggesting like when they formed their initial minimal groups, that created an empathetic bond between or within?
I'm saying it's not, you talked about creating the bond within the group. We didn't really talk about whether you manipulated the across group. connections?
No, we didn't
So-
manipulate the across group.
Yeah.
Typically, I think in minimal group paradigms, you only focus on establishing that within group bound, but that would be an interesting thing to
do,
try.
to maybe emphasize, exaggerate.
Yeah,
that.
to exaggerate the distance. Yeah, that could be very interesting, the sense of exaggerating between the two. Thanks.
You also just got some questions on the group chat,
Oh, boy,
on the
okay.
YouTube chat. So I'll ask Rainer Polak's question, which is great study. Question, while predefined group identity certainly is a very relevant factor, groups in real life are defined by not only by identity, but also by increased in-group interaction. Do you have a comment on this?
Yeah, so I think if I were to do more socially relevant groups, I would need to take into account how long people have known each other, the amount of time that they've known each other for, the amount of time they spend with one another. So those are all things that I think would have to be factored into any sort of analysis in this way. So definitely, this is why I started with minimal groups, because this was a simpler paradigm just to see, is this even possible from a minimal group perspective? And so yes, once moving into socially relevant, yeah.
And you managed to answer Ernesta Moore's question also on it was minimal group formation.
Yeah,
So you
minimal
can,
group
I'm
formation.
sure email Ellen your questions if
Yeah.
you have further ones. Thank you
It's
so
just
much.
my
Ellen.
last name.
Another
Thank
round
you.
of applause.
Sorry for everyone.
Just say Zipkowski.
Next up, we have Lauren Zibkowski with Music, Entrainment, and Social Interaction.
Wonderful to be here. Alexander mentioned when he did his introductions that RITMO was founded on a number of different centers, and one was on the musicological side, which he characterized as soft. I'll be soft today, but I'll spare you any graphs, but I'll play you a little bit of music. To the best of our knowledge, there are only a limited number of species that have a capacity for rhythmic entrainment, what is generally called beat perception synchronization. This capacity not only makes it possible for us to respond to the rhythmic movements of another, but it is behind the coordinated movement basic to dance and military drill. I would like to draw attention to two further cognitive capacities, vocal production learning and recursive pattern matching, that together with entrainment provide a basis for the way humans use patterned non-linguistic sound to shape social interactions. Part of my argument is that while rhythmic entrainment, vocal production learning, and recursive pattern matching are demonstrated by other species, the way humans recruit these capacities to use patterned non-linguistic sound to shape social interactions is unique within the animal kingdom. To understand vocal production learning, we have to begin with social learning. Social learning is a process through which behaviors are spread or maintained through an animal population. Of particular interest for our purposes is social learning that is focused on the imitation of sounds, what is generally called vocal learning. Vocal learning can take a number of forms. An animal may learn to use an innate signal in a new context, to rearrange innate signals to increase the animal's message repertoire, or to modify an innate signal after observing how a parent or peer uses signals. This last situation has come to be called production learning. The animal changes the way a sound is produced by modifying the way it uses various physiological systems. These systems include the respiratory system, the phonatory system. In mammals, that's the larynx, in birds, the syrinx, and various filtering systems, including the way the mouth is shaped to alter the sounds that are being produced. What is perhaps most striking, vocal production learning is relatively rare across the animal kingdom. It is generally agreed that only a small group of mammals, humans, bats, cetaceans, including dolphins and whales,
pinnipeds such as gray seals and harbor seals, and elephants, and 3 distantly related groups of birds, parrots, hummingbirds, and songbirds, have the capacity to modify innate signals in any significant way. What is remarkable then is that while other primates, including our closest current relatives, chimpanzees and bonobos, have significant capacities for social learning, they have at best a very limited capacity for vocal production learning. It is also known that our primate cousins have a very limited capacity for beat perception and synchronization. These 2 facts led Ani Patel to propose that vocal learning and entrainment were linked. As he observes, the evolution of vocal learning may have driven an especially high degree of auditory-motor integration in human brains because it requires a tight coupling between auditory input and motor input in order to match vocal production to a desired model. Even given that the 2 capacities might be linked, there is as yet no clear explanation for why vocal production learning and rhythmic entrainment emerged within only a limited group of species. One possibility, however, is offered by the fact that at least 3 of the species that have the capacity for vocal learning, cetaceans, elephants, and humans, are known to live in groups with complex social organizations. Within these species, the ability to shape and modify innate signals offers an important resource for negotiating and solidifying social relationships. Nonetheless, it has to be said that what we know about the social interactions of other species with the capacity for vocal learning is quite limited, and we know even less about the role rhythmic entrainment plays within such interactions. As such, we must proceed with caution. It could be that the capacities for vocal learning and rhythmic entrainment demonstrated by other species are key to the way these species shape social interactions. What we do know is that other species do not appear to use patterned non-linguistic sound with anything like the sophistication evident in human music making. To explain why this might be, let me turn to humans' capacity for recursive pattern matching and its relationship to analogical thought. The basic capacity for pattern matching, manifested both as recognizing that one phenomenon is similar to another and that both phenomena belong in the same category, is one that is widely distributed across the animal kingdom. The ability to recognize broader high-level patterns shared by 2 phenomena and to recursively exploit patterns within patterns is one that has a much more limited distribution. This ability is associated with a capacity for analogical thought, which is one of the distinctive aspects of human cognition. Let me take a moment to explore this capacity more fully, as I believe it provides a foundation for the way humans use patterned non-linguistic sound to shape social interaction. Let's start with basic similarity. A pen and a pencil, for example, are similar to each other both in appearance and in function, although the kind of marks these tools make on a writing surface will be different. Analogy takes as its point of departure similarity judgments of a more abstract sort. For example, a finger is analogous to a pen in that it is an approximately cylindrical structure that ends in a point. Unlike a pen or pencil, however, the finger leaves no discernible marks on the writing surface, and its cylinder is firmly attached to the larger structure of the hand. Making the analogy between a pen and a finger, then, involves drawing structural correlations between the 2. The cylindrical shape of the pen maps onto the shape of the digits of the finger, and the point of the pen maps onto the tip of the finger. With the analogy in place, we can imagine using a finger to write or a pen as an extension of our hand. Note that analogy is not simply about correlating aspects of one phenomenon with aspects of another, basic pattern matching, but about mapping relationships between phenomena. Indeed, it is often described as concerned with relations among relations, or second-order relations. In the analogy between a pen and a finger, for instance, the relationship between pen and finely tapered device for delivering ink, that is, the tip of the pen, is correlated with the relationship between finger and tapered appendage for guiding communication. Analogy, then, is a highly sophisticated form of pattern matching that exploits patterns within and across patterns, making it possible to correlate aspects of quite disparate phenomena and to use these correlations to guide reasoning and inference. As I've shown in other work, it is analogy that is in play when sequences of musical sound are used to represent everything from the chaos before creation to a sunrise to the dark emotions of lament to the steps of a march. Allow me to offer 2 short musical example excerpts to illustrate such representations. I said I'd play some music. One might well associate O'Carolan's Captain O'Kane with a somber emotion, and indeed it is typically taken to be a lament by the blind harpist for a friend who had fallen on hard times. It is important to note, however, that when I recorded the piece, I was not in a sorrowful mood, and it seems doubtful that O'Carolan was prostrate with grief when he composed the tune. Instead, the slow tempo, the stops and starts of the tune, and the gesture toward the relative major before collapse back into the minor mode all provide sonic analogs for contemplative, negatively valenced emotion process. Jonsson's Hegsetzer Broodmarsch, by contrast, invites rhythmic entrainment, but you may have noticed that the tread it establishes is a relatively deliberate one, suitable for a march that is both dignified and festive. Here, the periodic structure of the music provides a sonic analog for the steps of the march, while the dotted rhythms and rapid divisions in the strings offer an analog for the positive valence emotions that might be experienced on such an occasion. More generally, analogy offers a resource for rhythmic entrainment outside of the auditory domain. Just as patterns and sequences of musical sound can be correlated with kinesthetic patterns, the rhythmic patterns of the Hegsetzer Broodmarsch evoking the steps of the bridal march, kinesthetic or visual patterns could be correlated with auditory phenomena. For humans and for other species with capacities for recursive pattern matching, then, rhythmic entrainment can manifest in multifarious ways. On their own, the capacities for rhythmic entrainment and vocal production learning cannot explain why humans came to use pattern non-linguistic sound to shape social interaction, nor, for that matter, can a capacity for the kind of recursive pattern matching that serves as a basis for analogical thought. Put another way, why did humans develop music and other species did not? Questions like these lead us into the domain of just so stories. 2 facts can, however, limit the scope of the stories we tell ourselves about the development of music. First, we see the capacities for rhythmic entrainment and vocal production learning and recursive pattern matching in only a limited number of species. Second, human success as a species is based on our ability to cooperate with one another. Individually, after all, we could not hunt large mammals, develop agriculture, or bring the very planet we occupy to its knees. Michael Tomasello has made a compelling argument for a 2-stage process which led to our species' success. First, early human individuals, before the emergence of Homo sapiens, began to collaborate with one another in face-to-face interactions to pursue collaborative goals. Such collaborations led to more efficient foraging and eventually to the hunting of large mammals, and were predicated on developing skills to communicate about joint goals and ways to achieve them. Second, modern humans, early Homo sapiens sapiens, came to form distinct cultural groups, each pursuing its own collective goals within its own cultural practices. The formation of such groups helped to stabilize the communication skills that facilitated collaboration and provided a means of gathering together individuals who shared the same goals. The development of language as a tool for communication was certainly key here, but I would like to submit that making use of pattern non-linguistic sound to represent emotion processes, as well as communicative gestures in the pattern movements of groups of individuals, was important for the formation and maintenance of cultural groups. After all, as we know from our own experience, and as we've heard quite a bit at today's workshop already, participating in emotion processes that are shared with others or engaging in the coordinated movements of dance can promote feelings of group membership. As has been noted, a capacity for rhythmic entrainment has been documented in only a limited number of species. This capacity may be linked to vocal production learning, which again is present in only a limited number of species. I've proposed today that one reason these capacities may have developed is to facilitate, negotiate, and solidify social relationships. I further propose that the capacity for recursive pattern matching, which provides a basis for analogical thought, allowed humans to move beyond the basic interactions afforded by rhythmic entrainment and vocal learning through using patterned non-linguistic sound to represent emotion processes, physical gestures, and the pattern movements of dance. This then provided a resource for early humans to form and maintain cultural groups that were key to successful social collaboration. Thanks.
Thank you so much. Are there any questions from the audience for Lawrence?
I have many questions. I really appreciate this focus on the recursive pattern matching as a mechanism that's essential to the development of something like music. In your example of the guitar playing, nice guitar playing, by the way, I'm wondering about that gap between when music is genuinely expressive and when it is emotionally demonstrative, and whether you see what the transition would be between that, because there are situations in which musical behaviors are genuinely conveying, the performer state, and there's tons of examples where it doesn't really matter anymore. But that would be something that would have to develop some kind of separation within maybe individuals as well as kind of evolutionarily. So,
thanks. If I understand the question correctly, then it's sort of like music that we read out as expressive and musical performances that are really emotionally moving.
how about people using musical behaviors to express their emotions, and that somehow growing into music having a referential capacity for emotion?
Okay, I think I get that. First off, I would want to put just one little layer there, which is to say that what is actually happening is that the listener is interpreting a sound sequence as emotionally expressive in some way or another. Inasmuch as you could imagine a highly skilled performers, such as the ones you were working with, rendering a musically moving passage and maybe being kind of angry in some way. In other words, there does not have to be a direct match between that. And then there are certainly practices within cultural groups that will read emotions in pretty fine-grained ways. And Martin Clayton, who in a very ad hoc study some years ago just looked at listeners both within India and also within the UK listening to the same rag. And both listeners were able to get some of the same emotional things out. But if I recall, and again, this was a very informal study in many ways, but as I recall, the match was approximate in both cases. And I would actually, and have argued that it was analogical, that was what was happening in that way. We can talk more, because I don't think I've completely answered the question, but that was a first approximation. Martin, since I've invoked you.
Okay, we also have one in the YouTube, I'll just say it now, because it came in earlier. How would you differentiate language and music evolutionally? From Runa Ya.
I do that with a fairly crude tool, although it's a relatively new one, which is language for me involves what C.S. Peirce called symbolic reference, where you have arbitrary symbols that are correlated for reference, whereas music involves what I call analogical reference, where there has to be a conformance between the sign and the thing to which it refers. Generally, that's in the class of what Peirce called icons, but I break that down a little bit more. So language uses almost exclusively, but not completely, uses symbolic reference, whereas music uses almost exclusively, but not completely, analogical reference. That's the way. And again, it's a little bit more complicated discussion, but we can actually see that there are substantial differences there, especially because in expressing themselves, humans can use analogical reference. Prosody, there's been a lot of interesting work on that. Prosody is one place where that comes up. Martin.
Oh, my go. Thanks for the paper, Larry, and thanks for squeezing the Clayton citation into the question and answer session. But I didn't want to pick up on my own work, as it were, but try to turn some thoughts into something resembling a question. Now, when I think of human capacity for entrainment, generating social bonding, social identities, culture, etc., sort of archetypal examples I would go to would tend to involve something more like participatory musical performances, people dancing together, people playing drums together, people chanting together, whatever. And it seems to me that, so the first example you played of your beautiful guitar playing seems to be very far away from that, because in that case you have a solo performer presenting this tune, and as a listener to that music, maybe all sorts of things are working, including entrainment. And I'm following the beats somehow. It is a metrical piece. I'm also maybe thinking in terms of how that would be a song. There's something vocal behind it. Can I imagine a vocal performance behind that? All those things maybe go into my interpretation of an emotional content of that. It still seems, it seems like a very different thing to me. And I wonder, to what extent can we talk about a story of musical evolution as opposed to two quite different, or two different streams which interact in a way. In other words, people drumming and moving together and making noise together and entraining is a different thing from the solo vocal production, which is encoding emotion. And what we're really talking about in musical evolution is how those two things get intertwined with one another.
Thank you. That's a really good question, Martin. My answer would be to actually look at those. So first off, to admit that there could be two different streams. Again, I am learning a lot through this particular workshop, so I'm happy to entertain that possibility. My own thinking has been to think of those two things as along a continuum. Not the least because getting everyone to move together is one way to start to bring emotion processes into a state of harmony, and to do those sorts of things. And again, that bringing emotion processes into harmony, especially if you think of early social groups trying to bond, that would be something very important. Incidentally, all of your examples are very good, but I've also thought, well, what about the ones that are not as directly musical? But as Kofi Agawu talks about in the opening of his African rhythm book, there's all sorts of rhythms that are within daily life, and they can be with different forms of working together may involve those rhythms. And of course, we see then with sea shanties a crossover between those sorts of things. But back to the point about emotion, I'm actually there thinking that whereas there's not beat perception synchronization in terms of what Ani Patel and others have talked about with that, that's less prominent there. I do believe that there can be those same latent processes of entraining, but less rhythmically and more in terms of emotion processes within that. And so that's why I, at least in my naive state here, I'm thinking about those as being more along a continuum rather than being a sharp break. But if in fact research shows that there are in fact two streams, I will be happy to reconsider that and think about how I might better answer that question.
Thank you so much for such a stimulating discussion and talk. This now concludes this session, so give it a round of applause again. Thank you. Next in the program, we have lunch, and so that is being served downstairs in the kitchen and then outside. And then we will be back at 1:30 for the special sessions that are either happening here or in the mocap lab for the first one, and then the second one is at Auditorium 1, and there are signs guiding you. The mocap lab is through into RITMO and then that back, and Auditorium 1 is down the hall outside RITMO. Thank you. It's my pleasure to introduce my ex-colleague, because he's now gotten an awesome faculty position somewhere else, Ulysse Côté-Allard, who has developed the BioPoint, and his presentation is on unlocking comprehensive physiological data analysis through multi-sensor wearable technology.
No? Oh, sorry. Okay. Hopefully now you can hear me better. Yeah. So, yeah. So just very rapidly to present myself. My name is Ulysse. I'm from Canada, the French part, Quebec. So that's why I have a bit of a funky accent. And I'm co-founder of Sci-Fi Labs, which developed the wearable. And I'm also an associate professor here at UIO. And basically the main interest I have throughout my research from undergraduate up until now is the use of AI on physiological signal, especially in the sphere of healthcare. So basically, just to give you a bit of background of what I've been doing during my PhD, etc., I've been working a lot with muscle activity for prosthetic control. So here you have an image of the myoarmband, which is the main device I was using throughout my PhD. It records 8 channels of electromyography, so EMG, which is basically your muscle activity. And they are recorded at 200 Hertz, which isn't super great because the actual frequency band that you are interested in within EMG will be between around 520 Hertz up until 500 Hertz. So we would at least want a frequency rate of 1,000 Hertz. So there was actually a lot of paper that came out and compared the myoarmband versus more medical grade device and showed that you had much reduced performance using it. And then the question is, why was basically everyone using it? It's more or less, it's the only option that was available at the time, because something like that would cost $200 USD, and we'll see a bit later the type of muscle activity sensor, how much they cost and stuff like that. It also had an IMU at 50 Hertz, which is super useful for HCI in general. So yeah, I did my PhD basically at first just trying to control, like recognize different gestures based on that, and then we use that as a modality for prosthetic control, for human-computer, human-machine interaction, for in video game rehabilitation, etc., etc. More specifically, what I actually research is how can I leverage the information of multiple people that would have recorded their EMG signal, so that when a new person comes in, we can use less data and still get higher performance. I've also been very interested in how we can adapt the system over time. So physiological signal in general are non-stationary, meaning that if I record, for example, your EMG at day 0 and you come back a few days later, even if you're doing the exact same gesture, the same motion, etc., I will be reading different measurement, be it because the position of the sensor would have been a bit different, difference in pilosity, difference in skin contact with the electrode, and just your musculature can change over time, etc., etc. So yeah, I was basically very much interested in how can I try to adapt as the biosignal change without having the person redo some training and things like that. Then I came here to do my postdoc, again in AI with physiological signals. So I worked a lot with photoplethysmography, inertial measurement units, so actigraphy, ectodermal activity. We'll see a bit what they all mean in a tiny bit, but basically we were interested within the sphere of mental health to diagnostic people with bipolar disorder if they're going toward what we call an euthymic state, toward a manic state. So we were then using the Empatica E4, which had a PPG at 64 Hertz, which is useful to get the heart rate variability, which was very much an important features related to describing the current mood state of a person with bipolar disorder. Then the actigraphy at 32 Hertz, temperature, skin temperature, and ectodermal activity, so skin conductance at 4 Hertz. And yeah, so basically the point is you get this signal and you have to try to figure out automatically, is the top one from someone going into a manic state, or is it the bottom one? So I don't know if anyone has any guess. This is over 24 hours of time. And yeah, the reason for, I guess, no guess is just those type of signals are very obtuse, right? It's kind of very hard to actually derive some meaningful information from them just manually, and that's why we're using a lot of AI right now to do that. So just for the information, the top one was euthymic, and the patient in the manic state was at the bottom. Another big difficulty when we are working a lot with physiological signal is that there's a huge amount of variability, not only within a subject, but across different subjects. And for applications such as these, one thing that is very important is that you want the system to just work out of the gate. You don't actually want the person to have to go through a full manic episode so that you can get what their baseline manic episode would look like before you're able to predict. So again, that was, even though it might seem a bit different, it was very much related to kind of understanding the general commonality across participants, so that when a new person comes in, just from the get-go, zero-shot learning, we can predict. And this basically, throughout my studies, I've gathered a lot of frustration, let's say, with the device I've been working on, mainly in terms of transparency, accessibility, and synchronization. So from the transparency perspective, it's just the black box algorithm problem. A lot of manufacturers, what they'll do is they have these sensors that aren't necessarily super good. They'll do some processing internally and just give you the result of the processing without ever telling you what's actually happening. And then when you just get heart rate or heart rate variability, you don't have any idea how they were computed. It's very hard to figure out if there's some bias in the data, to figure out if the measurement you're getting, you can actually use them or not, things like that. So that was number one, especially that, like I said, I'm coming a lot from AI, machine learning, and I like to work with the pure raw signal so that I can do my own filtering, feature extraction, etc. So the Empatica E4, for example, the PPG, what they're giving you is the combination of the red and green sensor. They don't really tell you how they put them together. They output that, and then you're supposed to figure out what it exactly means. The other thing is accessibility. So in general, those sensors cost a lot of money. So as an idea, the E4 is $1,600 USD. I know now they release a new version. We'll talk about it later. EMG system, medical grade. There's multiple channels, but basically you're looking at least 20,000 USD to acquire this type of modalities. Which one of the big problems we had during my postdoc is we wanted to have patients out of the hospital and just follow them throughout the years, right? The problem with bipolar patients is that they tend to break them a lot, and then they cost a bit too much to just have them and replace them often. It just also makes it, in general, harder for different labs, especially for a lab that has maybe less funding to get access to these, so you can do a lot less type of experiment. It makes it harder to scale the project you're wanting to do. And there's also the accessing of the data itself. So often it comes with subscription, so the Empatica E4, the new version, I think they're selling it for like 600 USD, something like that, but then you have to subscribe for 3 years for 5,200 USD on top of that, so a lot of recurring thing. Cloud service, which, especially within the context of things like the GDPR, make it very hard to actually deploy and use these devices, because then you have to think a lot about data privacy. The actual manufacturer of the device has to be able to certify that the data will be pseudonymized sufficiently. It just adds a lot of complexity in the research. And then just, in general, getting access, if it's possible, for the raw data, download streaming, etc. The last thing is synchronization. So, in general, to have a holistic experiment, we want to often be able to work with multiple sensors at the same time. All of these sensors often are from different manufacturers, which just makes it hard to synchronize, especially when we're talking about millisecond or sub-millisecond synchronization level. At the second level, then it's relatively easy. Then incompatibility. And then clock drift, which is something that beyond any type of implementation you're going to have, any device that you're using will have an internal clock that will tell it basically what time it is. And all its behavior will be driven by that clock. Meaning that if you're recording something at 1 Hertz, it will be based in its internal clock how long it has been since the last time it recorded. After a second, it does that. So this is a perfect clock, so as the real time passes, the local time passes 1 to 1. And of course, we live in the real world, so in reality, you have the clocks that will have some skew in them. They might have some offset together, and then you also have some amount of drift, meaning that the measurement that you're getting from any type of device will be different than any other device. Even if you would start them at the exact same time perfectly, over time, if you're doing experiment over 24 hours, 48, 4 weeks, etc., even a few minutes, they will start to drift. And this problem compounds more and more as you add more sensors to it. To give you an idea of the scale of the problem-ish, the typical wearable clock precision ranges from 20 to 50 ppm, so part per million. It basically means that for every million second, your device will have like plus minus 50 seconds. So for a full day at 50 ppm, you're looking at a drift of 4.32 seconds. For some experiment, it doesn't matter. For other, when you're looking at physiological signal and you want to actually have millisecond accuracy, this is like you're completely missing everything. So this brings us to kind of the bio point, which we try to address as much as possible all these grievances, because first and foremost, we are both researchers, me and my co-founder, and we just want to be able, it all started because we wanted to use a device that works for what we wanted. And then we realized kind of rapidly that if we want to use that device, we need to have a certain amount of scale, because otherwise the price point would be too high, right? So basically BioPoint is, it's still in prototype phase, but this is it. And then we're getting electromyography, skin conductance, electrocardiography, skin temperature actigraphy, and photoplethysmography at the same time continuously in streaming. So just to go a bit over all 3 points and how we try as much as possible to address them, is that you can get direct access to the raw data, both in streaming in real time, and there's also onboard memory, so you can do a fine experiment and download it over either the Bluetooth, or you can plug a USB-C cable and upload it. We're targeting below €4.99 per device, and there's, of course, no subscription fee for the data access. There's no upload to cloud or anything like that, which, again, we're using it in our resource, and it would just make it a lot more complicated. And all the sensors operate on the same hardware platform, meaning they will all be able to share the same clock, meaning that we're not pretending that the clock we have or made is perfect, but they all will drift together, right? So even after 2, 3, 4, 5 days, they will all be perfectly synchronized within themselves. We're also using a high precision clock, so we're at 5 ppm, so we are reducing to 0.432 seconds per day of the, on average, drift. And we're also integrating with lab streaming layer, if some of you know about it. It's basically a open source software that allows you to connect different devices from different manufacturers, and then it attempts to do synchronization on the computer side or the server side once it receives the data. So here, what I thought is just to maybe go a bit rapidly into the different type of sensor that we have, what they actually mean. So electromyography is basically just when you're trying to move your skeletal muscle, your brain sends some type of signal that goes through the motor neuron and then excite your muscle fiber, which is a whole electrical process. And what we're able to do is measure this electrical signal. So the size of it is around 1 to the minus e to the minus 6. So it's microvolts level. And it's used for movement disorder, biofeedback, training, optimization in athletes, synchronization with muscle movement also. The other one is electrocardiography. So this is very well known, but heart rate variability, it can help detect different conditions. Again, biofeedback, and that's something that's emerging more and more within mental health too, to actually ask the person to try to guess their heart rate variability, and then you can have them basically tell them if they're wrong or right, and this is just a way for them to be more conscious of what's happening if they're feeling stress, things like that. And the other fun thing is that it can be used to derive indirect metric. So we'll see it a bit more later, but for example, respiration rate, which is, those are all estimation always, but basically you can more or less look at the amplitude here, and this slow drift is very much related to respiration, because when your lungs fill up with air, it will come and change where the electrode is in respect to the heart, and then you can have a bit of that measurement going through. The next one is skin conductance, ectodermal activity. This was, as you can see, you're having it go a bit faster than real time. This was during the night, taken on a forearm. So this is indicative of what we would call an EDA storm. The way we're measuring it is we basically send a very, very small signal through the skin and measure a known signal, and then we measure we measure that signal at another electrode, meaning that the resistance of the skin will affect the measurement we get, and basically your sympathetic nervous system which control sudation, when it's activated or when it's suppressed, will change the resistance that we're reading, which is basically what you were seeing. So the EDA storm that you've seen is very much associated with deep sleep. So it can be used as an indicator of emotional state, biofeedback again, monitor pain, because people that are in pain tend to have reaction within the EDA that is measurable, and also for sleep monitoring. Skin temperature very rapidly, again, circadian rhythm, sleep monitoring. This is taken over, I think, 10 or 12 hours. Sleep monitoring, health status, biofeedback, etc. And finally, maybe one of the most important, the photoplethysmography. The way it works, it's just you send a small light through the skin, and you have two types of PPG. The one you'll see at the hospital where they put on the finger. Basically, you have the light that goes here, and you have some photosensitive sensor here. So it's going through the finger, and we're measuring the amount of light that goes through. And the idea is basically when your heart is beating, it creates a pulse of blood going through and back and through and back, and so the density of the blood change, and so the amount of light that is absorbed also change. And this is what you're seeing here. This is a type of PPG that is called bireflectance. So instead of going through the finger, when you're putting it on the forearm or the biceps or torso, etc., some amount of light will be reflected back. And this is what we're measuring, is how much light change. This type of sensor is what you'll have in every single smartwatch. That's what you'll have in every single smart ring. They will tend to have either just the green, or some of them will also have infrared and red. And the reason for that is that they're super useful to make measurement of heart rate variability on a single point. They can be used for blood pressure estimation. This is a bit harder, I'll tell you a bit after. And also for oxygen saturation, SpO2. So the idea, and that's why you need red and infrared for that type of measurement, is that the amount of absorption for hemoglobin when it's filled with oxygen and it's not, is basically inverted when you add the red and when you add the infrared. So you can basically measure both the absorption from the red side and infrared. You cancel like the DC and things like that. And you can get an approximation of how much oxygen there is in the blood. Finally, inertial measurement unit. That's a super fun and useful sensor. This is also available in every single smartwatch, smart ring, etc. Probably in every single sensor that you'll get. You might not have an inertial measurement unit. You might just have actigraphy, accelerometers. But basically, it's useful to evaluate movement. So what you're seeing here is me walking. As you can see, each peak is basically a step. So that's how you can do step count on your smartwatch, or you just do, it's quite easy. And then you can do sleep studies, see when the person stop moving, start moving. We've worked a lot with it with bipolar disorder. So actigraphy is actually a very, very good indication of the actual state of the person. When I started working with it, I was imagining that the manic patient would just move all the time, whereas rhythmic wouldn't. The reality is a bit more complicated. What we're looking at for actigraphy in bipolar disorder is more the complexity of the signal. So someone in a manic state will have tendency to have more complex movements, so start, stop, etc., and not so much move non-stop. And it can be used for the orientation of the limbs. So this, in conjunction with, for example, EMG, you can start doing some very cool gesture for human-robot interaction, where you can understand where the person is. So, for example, this could do a different gesture than this, even though from an EMG side, it's the same. More is the same. And this is actually the very big thing. If it's synchronized well, and then we're talking sub-millisecond, you can actually use it to alleviate a lot of movement artifacts. So more or less, all this sensor, PPG in particular, but EDA, ECG, EMG, they all rely on good connection and constant connection with the skin. So as soon as you're doing some movement, some vibration, right, you're going to change the point of reading compared to the point of what you're reading, which will affect the signal. And then when you have access to that type of thing where you actually can see precisely when the person is moving, you can do two things. You can either do some filtering, so try to remove the influence of that signal, or if it's too intense, you can just detect that this period of time too much movement and just reject automatically the signal. Yeah, so like I said, the BioPoint is, for those who have worked a bit with microelectronic, we're extremely, extremely packed. So it was, to the best of my knowledge, there's nothing that exists right now that has all of these sensors together. I won't lie, it was very technically challenging to get those signals and not affect each other, because we're talking about microvolt and things like that. Just generally speaking, again, if you have any question, don't hesitate. The way it works mostly is that you have the charging USB-C port. It's also how you're going to measure the ECG. So for the ECG itself, you cannot make it, as far as I know, and I've researched that, you cannot have any ECG measurement from a single point. The reason for it is more or less you want to have 2 points that cross the heart so that you can have an actual difference of measurement. So in my instance, and I can show you a bit later the type of recording, and just to be clear, all the recording I've shown was directly the raw data. But yeah, in my instance, I have the ECG here, and then I have an electrode here, and then I can measure continuously through it. It is also possible to get it without that by using an electrode on the top. Something like an Apple Watch will also have that type of thing with the crown button where when you touch. That way you basically have a circuit that go 1 point here, all the way here. And that's equivalent to a V1, if I remember correctly. Wait, I fully forgot where my thing is. Okay, anyway. Yeah, so just for the spec a bit of the actual frequency rate and things like that, this is something that is very much possible to be changed. Right now, what we've done is what we think would be the most, that would make the most sense. Frequency rate will always be a balancing act between battery autonomy, the amount of memory that it will take, and the bandwidth for transmitting it. But basically, we have the PPG at 50 Hertz. We add it at 200 Hertz without problem. The EDA, the signal itself that we send, it's at, we can do it at DC, and that allows us to record at the same time EMG and ECG. We can also have an AC signal, which in general provide faster contact with the skin. EMG is at 2000 Hertz, ECG at 500 Hertz, skin temperature at 1, IMU 50 Hertz, and like I said, Bluetooth to energy, real time, etc., etc. Okay. So just to give a bit of an example of why you would want to have all of these sensors together, I want to go a bit into the pulse wave velocity. So basically, when your heart is pumping, what happens is that it's very annoying. Okay, Okay, no. Well, anyway, when the heart is pumping, you have this ECG signal, and you see this big peak here. It's called the R peak. There's the QRS signal that is a bit around it. And that's when the ventricle basically contract and send the oxygenated blood through the aorta, which create a pulse that propagate throughout the body. And then you have something like a PPG that would be on your forearm or on your finger, right? So there's a certain distance between where your heart is and where the PPG is, and that distance means that it will take a certain amount of time for your pulse wave to travel all the way to where your finger is. And meaning that when you have both, you can actually calculate the pulse wave velocity. And this is directly related to the arterial stiffness, which is a very, very big indicator of risk of stroke, for example, which meaning that it's very useful to have. It's also a very good indicator to help you compute an estimation of blood pressure in a continuous manner without any cough. So, yeah, the idea is you use the ECG to pinpoint when the heart starts the contraction, and you use a PPG to actually capture when the blood arrives at the point of measurement, which, if the signals are well synchronized, then you can get what we call the pulse transit time, and then you can get the pulse wave velocity by dividing, well, by having the distance divided by the pulse transit time. I can maybe show some example of okay. If you just give me a tiny second, I'll change the way I'm showing everything. Because I just want to give a bit of an example of how you can get the data, etc. Okay, I won't be able to do that because apparently I went full blue screen of death on my computer. So I'll be right back. Yeah, oh no, my computer just restarted fully.
Okay, so I should switch to the other computer for a moment, or?
No, I'll just restart in a second. But yeah, so if anyone has any question, you're very welcome for it right now. Yes? Yeah. Yeah.
Sorry, I forgot if you mentioned it. Is there anything?
Yes. So we are actually also working on what we call the bioarm band. Yeah. So it has all the same sensor of the biopoint, but it has 8-channel EMG at 1,500 hertz. Yeah, and I can show a demonstration, but if you, I'll have an image. So this is still kind of prototype. I have the image of more the robust final version. But yeah. And the idea of having it more in a rectilinear fashion is that then you can strap it also, for example, on the stomach, back, around the hand, and etc. So we are still a bit working on the attachment point and things like that, but okay, I'm coming back. Sorry about this time.
Could I ask a question while
Yeah.
it's loading?
Yeah.
Or no, you go ahead. If it's gonna.
No, you can ask.
I guess I know I've heard that like one of the issues with buying sensors from companies is that sometimes these companies just stop all of a sudden.
Yeah.
And I wanted to know if somebody was to invest in your product, like what kind of support do they have, and then how long do you expect it to last? Like, is there any guarantee that it wouldn't just stop, for example? Because I know with the Mayo armband, I think that stopped, or there's various other companies that have just gone under or disappeared because people buy them up.
Yeah.
Are you gonna resist like big corporations trying to buy you, or how is that gonna work?
Yeah, the reality of it is that our plan is very much to grow and to work right, but the reality of it is that we're in a startup phase. We're in the valley of death, that is called. So we have the start of the product. Everything seems to be working well. We're starting to have actual hospital using them, university, etc. So everything works very well, but if I'm fully honest, I can't give a guarantee that we won't collapse at some point. That being said, so far, every sign show that it's going very, very well, let's say.
You just got like the assistant professorship, so you're balancing both these, like, because this is part of your work, and that's more of like a job, it's a secure job, so maybe that's one way you can kind of have some kind of guarantee, because it is very relevant to your research as well, right?
Yeah, it is, and what it allows us to do, of course, if you have also questions about entrepreneurship from academia to and working with both, I'm also very happy. I'm not pretending I'm an expert, but that's something I've been dealing with for a while. So we have to go through ethical committee, of course, to be fully transparent into what the company does, what I do as research, and make sure whenever the two can overlap to declare it. But we do see a lot of synergy that come from being both in the academic side and industrial side. And like I said, the main reason why we started it is that we were just very frustrated with what was for the research we wanted to do, and we wanted to make it better, right? So at the core of it is that we're very interested in research, etc. For your initial question, I would say one of the big advantages with the system we're doing is that we provide the raw data. We don't have cloud service, we don't have subscription, things like that, meaning that even if we go under, your device still works, right? It doesn't stop working, you can still record, etc., etc. The goal is very much not to go under. So I just wanted, speaking of which, I don't know if people fancy a bit of coding, but I just wanted to show a bit rapidly one of the way you can get in contact with the biopoint. So just, okay, that thing. So this is just an example, very rapidly, of all the signal together. It's replacing, etc. You have the ECG, which is the red one on top, and also the PPG. One thing I want to kind of have you notice is if I start moving like crazy, especially on the PPG side, for example, infrared, right? What it starts measuring is actually more my movement than actually my heart rate. So that's why things like acceleration is very, very useful. The other thing is that for PPG specifically, another big advantage of having blue, green, red, infrared, one of the things they do is basically the blue one will penetrate the least inside the skin, the infrared one will penetrate the most. If you have participant or patient with different skin color, one thing that does is affect a lot the depth of penetration of the different signal. So one, having different color like that can help compensate. The other thing is that we're allowing you in real time to change the amount of intensity for all the light, and we're also allowing you to change in real time the amount of sensitivity. So we're working on kind of an real-time optimization for wherever you put the bio point and also wherever on whomever you put it. So this is one of our big focus right now. So just to show very rapidly, one of the way you can interact with it, it's not the only one, but it's, I think, something that is kind of very, very useful and cool, is that we've made what we call a command line tool. So it's basically, that file is a sci-fi bridge.x. You can have it for Linux, you can have it for Mac, you can have it in principle for Android, etc. And what it does is it's allow you to just call from any programming language, as long as they support sub-process. So in principle, you can talk to it from R, you can talk to it from MATLAB, Python, C#, C++, C, literally any programming language. You just open the sub-process, and then you're good to go. So here we would try to connect to the device. So we're just like trying to make sure, is the device on? Can I connect to it? And then as soon as you do, it says, okay, everything is good. And then here, I'm sorry, the resolution isn't super good. But here it's basically, you tell it which channel to open. So in our case, we're opening the EDA and PPG. You can decide to open all of them. You can decide to just have one. You can decide to enable the filter on board or not, so to get even more the raw data. You send the command then to start the acquisition, and then it just records. And then you can decide to send the command to stop the acquisition, download everything, etc., etc. So it's not bound to any specific software that we would be developing. You just can have the scripts you want and control it. And it's the same for the bio-armband. 5 minutes, yeah, okay, so I'll just wrap up. Yeah, I'll just wrap up very rapidly with the bio-armband, which we've been working on. Like I said, it has all the same sensor as the BioPoint, which is actually, I think, very cool, because then you can do a lot more type of experiment where you can measure both things like stress, heart rate variability, etc., in situation where the person is controlling, playing piano, things like that, and you can actually see better the different movement. It's cadence at 1,500 hertz, so we're well above the 1,000 hertz to get all the frequency information. There is, because we're using Bluetooth to energy, there is kind of a day before sending everything. We're at 7.6 milliseconds. As a comparison, the MIO is at 5 milliseconds, and the DELSYS is at 14 milliseconds. So generally speaking, as you don't want to be above kind of 50 milliseconds for gesture recognition, max. So this is well below. For some application, maybe you would need even smaller than that. One thing we're working on is to have the possibility to connect a USB cable directly to your computer to reduce that. The thing we need to do for that is we have to make sure we don't send any power through that cable, so we're looking at optocoupler and things like that. But yeah, it's in the work, and then just a very quick demonstration where we're using it to play a game or control a quadcopter. This is like from Linux and Unity, C#. This was in Windows with Rust and things like that. So yeah, thank you very, very much.
Thank you so much, Ulysse. We now have 4 minutes for questions. So if anyone would like to start here, I'll also just open up the YouTube chat. Perfect. Here,
yes.
Marc. Fellow Québécois.
Music en français.
En français? Okay.
In English for now. Music applications, like music applications for interfacing with like
Yeah.
softwares like Pure Data or MaxMSP? Or
This is something I have a bit, yes, knowledge on. That being said, RITMO got some BioPoint and things like that, and we're very much in the time where we're doing a lot of collaboration. So when we're saying we don't sell the sensor kind of to anyone, we want to have collaboration with the people. So yeah, this is something we're very interested in. This fall, we're actually partnering with a course that Dana is also giving with students from the musicology department.
Yeah.
So we're very excited to see the type of thing they'll do and also understand the specific need in music for it.
Very cool.
Yes, and actually 2 of the students are currently streaming this up onto
okay,
YouTube.
super.
So Jack and Amin, that's why I had you guys sitting here to watch this presentation, because this is one of their potential projects that they could participate in. Any other questions?
Thank you for the presentation. It's really cool to see so many sensors in such a small box.
Thank you.
I know that some wearable devices don't have the same level of precision depending on where you put them on the body. Different wearable devices have different precision levels depending on where you put them. Like I know you show for the arm.
Yeah.
I'm wondering, like, for other type of application, if you put it somewhere else.
Yes. So I think I have it. We also have like I hope I brought it. Sorry about that. Okay, anyway, we have like strap more like a meter long, so you can go torso, etc. We'll also have patch, double-sided patch with medical grade tape, so you can actually place it anywhere you want.
But would you lose like precision in one of the area if you decide to put it on the leg, for example, if you're more interested in walking, or if
yeah, so for example, with the EDA, the best position to put it is on the finger, right? So as soon as you go on the forearm, or I don't know, the torso, things like that, you'll have less precision, well, you'll have less good contact with the EDA. That's basically the only sensor with that. There's also the PPG with the different depth and width of skin, etc. But that's why we'll also have the possibility to have higher intensity for the light, etc. One thing I'm doing is trying it on my dog, who's like very furry and very black hair and stuff like that. So I'm trying to cover as much as possible.
Thank you.
All right, thank you for a great presentation. It's great that there's more hardware coming.
Thank you.
Pick from. I might have missed this, but so if I understood correctly, you only use the Mayo armband style thing for the EMG, right? Have you
in my PhD?
In this kit?
No, in this. Here.
Yeah, that one, right?
Yeah. So that's the bio armband. So we've developed that too.
Right.
Yeah.
Have you, because that's just like an armband setup, have you any plans or already tried individual ones, so more to be able to target more precise muscles, or the armband styles?
Yeah, so the idea would be that the BioPoint, you'll be able to connect multiple, so we're also working on a base station. So hopefully you'll get to connect 12, 16, a bit like the Delsys
right.
with RU to do that. And
that would be great. Yeah.
What's great is that you're both here in Oslo, so you can collaborate with him for your project, which is very related. Are there any final questions for the audience here? If not, we have a quick one online.
Yeah.
So Andriy Smikovsky has asked, could you elaborate on how, sorry. Okay, so thanks for your interesting presentation. I'm curious about your device's applications. You discussed its role in detecting mood variations as well as detecting euphemic and manic states in patients. Could you elaborate on how you established the ground truth about the nature of the data and its relation to different moods?
Yeah. For my research and during my postdoc, we didn't use the BioPoint full disclosure. We were using the Empatica E4. the way it worked is basically the patients were hospitalized, they were assessed by psychiatrists to determine they were in a manic state, and then they were asked for consent if the psychiatrist thought they were in position to consent for it, and then they wore the empathic IFO for 24 hours. Just before their dismissal from the hospital, once they were diagnosed as euthemic, then they were asked the same thing if they wanted or not. So then for some of them, we have recording of them both in euthemic and manic state. A lot of them, we just have one of them. Yeah, and then we have a journal paper I'm happy to link with all the
I
persons.
linked your SIFI Labs website into the chat so that they
Okay.
could contact you.
Yeah.
So thank you so much, Ulysse. That begins this next break. Another round of applause. Thank you. Unfortunately, we just have 8 minutes for this break, and then afterwards, Emily Carlson and Alicia will be doing their presentation here, and then there's also going to be the Respy workshop happening in Auditorium 1, which is downstairs. So thank you and enjoy the break.
the Finland contingent here. And we're both working in the area of music and autism, but particularly entrainment and synchronization. So our aim today is, if you're unfamiliar with this topic, that you come away with more understanding and maybe some ideas of your own research. And then also to give us opportunities to kind of brainstorm and think together about ways that we can address this topic better as a field.
Yes, a very quick overview. We'll first quickly do a general overview of what is autism and related to the literature on entrainment, and discuss on some of the challenges that have been arised in this research, and we'll be given then 2 case examples of how we have been trying to overcome those challenges. And we'll finish up with some discussion among all the participants so that we can also interactively discuss about these topics.
Okay, so we actually don't know what your backgrounds are about in this topic. Raise your hand if you have any familiarity with autism, practical or clinical or personal. A little bit, okay. All right, so some and some newbies, which is great. We could spend an entire hour or two just on the research and literature, giving you this background. So I'll keep it at a basic level for now, but please feel free to ask questions either now or later on. So autism is generally defined as a neurodevelopmental disorder, and its diagnostic criteria at the moment, these do change sometimes, but right now the criteria are that a child has difficulty with social communication and has a pattern of restrictive and repetitive behaviors. Now these are very, very broad categories, such that the social interaction difficulty piece could look something like a child having minimal ability to speak verbally, maybe using picture cards to communicate or sign language, but it could be also that someone has full verbal communication but struggles to read social cues. So there's a very wide range of what this can mean. And similarly with the restrictive and repetitive behaviors, that can look in some people like very, very narrow interests in certain areas. I had a client once in music therapy who spoke of nothing but air conditioners. So it can be like that, or it can be something that's a little bit more behavioral, kind of the classic sign you see in the picture here is that you might see a child engaging with toys where they are placing them in a row, only stacking, maybe playing with a toy only in a certain way, playing with the wheels rather than playing in an imaginary way. And these are just a few of many, many, many examples of what these criteria can look like. So in addition to the main 2 requirements for an autism diagnosis, we often see other things as well. Often there are sensory issues. Autistic children can be hypo or hypersensitive to sound or touch. It can change. Sometimes you're hypersensitive in one moment and hyposensitive in another moment. So that creates a number of challenges. Very, very common for these children to have sleep problems. Co-occurring diagnoses also happen very often, ADHD, learning disabilities. And the one that's interesting for us here the most is that there seem to be in most, possibly all, diagnosed people with autism difficulties with motor skills, fine motor skills and gross motor skills, and ability to time motor interactions with others, which is very interesting for us. And just to give you a sort of one language that we use for describing different levels of autism is this 3-level system, where level 1 could mean that a child or an adult requires a little bit of support or some some special training, and then level 2 is sort of a middle area, and level 3, which is the level I worked with as a music therapist most of my time in the clinical field, refers to people who need help most of the time in most areas, and usually do for life. So we have a range of people who graduate college and get PhDs and work and live with minimal assistance, although they have struggles, to people who need basic assistance for their entire lives amid one diagnosis. So the movement piece, there is more and more literature all the time showing that there is a motor difficulty in autism. There has been some debate recently in the literature about whether motor issues should be part of the diagnostic criteria. It has not been decided, but there are certainly a number of researchers who feel strongly it should be part of the diagnostic criteria. There seems to be a correlation between how severe the motor difficulties are and how severe the autism is. And both in terms of the social functioning, sometimes in terms of cognitive ability in general. There's also some studies showing that the worse the language difficulty is, that there may be a motor component there. There's understanding that although there's many different things going on neurobiologically, it does seem that the cerebellum, which is of course related to timing and precise motor control, does seem to be an area of abnormality in autism. And then synchrony, which is of course why we're all here. The literature here is somewhat mixed, but it does seem to be that difficulties with synchrony may be a marker of ASD, and there's been quite a bit of interest about that as a potential area for intervention as well. So the literature about ASD and synchrony, we have seen that struggling with synchrony may be an early sign of autism, especially in terms of rhythmic development, especially in social contexts. And as we all know, there is literature outside of autism linking this ability to synchronize, to be together in time, to our social abilities. Think of the literature showing that children who synchronize on a drum with an adult are subsequently engaging in pro-social behavior more than those who don't synchronize, for example. So there seems to be some connection here. But there are a lot of difficulties with this as well. There are studies out there that look at synchrony in autism and say, nope, there's no problem. It's just exactly the way it is for typical people. And there are a lot of issues of why this can happen. Study design is, of course, one. How we're measuring synchrony. We've talked here a bit about micro-timing and beat bin sizes, and that's something that's not been investigated, for example. Another issue, which we'll talk a bit more about, is, as I said, the spectrum is incredibly wide. So it's often much easier for us as researchers to interact with participants on the side of the spectrum who are higher functioning, who maybe have verbal capacity, who are, it's easier to get permission from them to participate. So that creates a bias in our research for who we're studying and how. And then the things that we kind of often see with research on special populations, small sample sizes, lack of blinding, and then we're not sure about whether this is something that we can use for rehabilitation.
So just to continue, no? Okay, yes. And especially also defining entrainment with this population, because as we have, as Emily was explaining, ASD is characterized by having a wide range of severity in the spectrum. Also, we'll touch upon this a bit later, but defining the population can be sometimes tricky when describing if they are at risk of ASD or other diagnoses or already diagnosed, because ASD usually comes a bit later in age, so with very young children, depends a bit on the country and culture that we're talking about, but with very young children, they might not have a confirmed diagnosis yet. Another challenge quite relevant for the topic also that we are touching upon these days is how well our movement studies of typically functioning people are actually provide a basis for movement variable in people diagnosed with ASD. Another quite important question is how to best establish and investigate a causal relationship of entrainment and social skills with people with ASD. And then we also encounter pragmatic issues, as in many other research, with ethical issues, which is specifically important when talking about people with disabilities, and what does consent mean for them, and how to make sure that we have their consent. Some also data methods such as markers or neuroimaging procedures might not be completely adapted to this collective. And also another more on a philosophical level is how to really make the research process inclusive. So how to include them along the whole process, but also how to make sure that what we are investigating is relevant for them and is important for them. So now we've been talking for a bit, and we'd like you to just quickly, like for 5-10 minutes, discuss with someone that you're sitting next to, like nearby. You're also very welcome to move around, like just self-organize. You can discuss in general terms how you would think these challenges that we've just explained, how they could be addressed in research. It can also be thinking about your own research projects. And also you're very welcome to think about some other big questions that might have come to mind while we were explaining the ASD characteristics and this research. So yeah, and then we'll just ask later for maybe a couple of comments. So yes.
Yeah, maybe just for about 5 minutes, have a little chat. And especially think about your own methods and research expertise and how this may relate. Okay, we're very glad that everyone's chatty. And we'll give you some more time to talk about these things in a little bit. Yes, let's continue. Hello, let's continue. We're super excited that you really want to talk about this, and I promise we'll give you some more time later on. But would somebody like to share a little bit what they discussed in your groups? After this, we'll share how we've tried to address these issues, but what are some of your initial thoughts? They only want to talk to each other, not to us.
One thing we were kind of wondering a bit is in relation to parents seeing their children and maybe not wanting to accept or go through the diagnostic process of them. Is that super prevalent, or?
It depends on the culture and the location. I grew up working in the US, where there's a lot of drive for early identification, early intervention. So being diagnosed as soon as possible is a big value there. Whereas now we're working in Finland, where there can be sometimes more resistance to having children diagnosed. This is especially relevant when we're talking about levels 1 and 2, where it may not necessarily be so obvious and not as easy to see that the child needs some support and help. But yes, that can definitely be an issue.
Yeah, I'm not at all familiar with the broader literature, but from talking to some people, I've heard that there seems to be a distinction between people with autism who kind of see it as part of the identity versus as like with this, almost like a disease, and maybe that gives access to support in some things depending on the country and the health system and that sort of thing. Is that something that comes under definition and population? And if it is that something that's generally now taken into account by researchers in the field? And how do you address this? Because it is maybe
that's a great question.
Ethical implications too, doesn't
it? And it definitely is an issue. Sort of 20 years ago, you were doing research on autism, there was sort of really a let's try to fix it, let's try to cure it focus, and that's really not seen as ethical anymore. And again, there's a lot of that depends both on the individual's view of autism and a lot on their functioning level as well. I would say the definition of autism is so broad currently that for some people it truly may not be a disorder, and if they don't see it as a disorder or disability themselves, I do not consider it my job to tell them otherwise. So kind of pragmatically, my approach is if you were looking for support and you want help, that's what our job is as researchers. Also pragmatically, we do have to be very careful and sensitive with how we speak about autism. I kind of interchangeably use person with autism, autistic child, autistic person. Some people very strongly prefer one or very strongly prefer the other. So speaking-wise, I use both. When we write a paper, usually we pick one and explain why. But that is another big topic that can fill an entire session. Should we keep going? Okay, so first I'll talk about my study, and then Alethea will talk about her study. So mainly to try to address the issues of having a naturalistic setting and being inclusive were my main focuses in this research project. This is a really small research grant from SEMPRE to kind of do a proof of concept of using markerless motion capture to study autism and music therapy. So the aim was to basically find out if we can do it. Markerless systems are fairly new, and most of the commercial development is looking at things like sports movement. So when we've been working on developing this for music in our lab, sometimes the people we're in contact with are a bit surprised that we're not doing 5-second trials over and over again. So no, I have 30 minutes of a child playing a xylophone with somebody else, and they're running around, and it's complicated. So this was a big technological challenge for the most part, and then also kind of a conceptual challenge of, can we show something immediately happening in a therapy session based on music? Can not attach anything to these children who are not able to tolerate sensors on them, and still get some meaningful data that shows us when something good or something we hope is good is happening. So kind of very low threshold goals, but it was tough to get there. The aim was to have 10 clients. We ended up with 6 clients who had 4 music therapy sessions. They were, I gave no restrictions to the therapists. I told them just do whatever you would normally do in music therapy for these children, rather than try to have any specific goals. They knew that we were interested in movement and entrainment, but they were therapists first. We did the therapy sessions in our motion capture lab in Uvascula, which now has these 12 Miquis Qualisys markerless cameras, which are quite expensive, and it was a bit terrifying to bring children in who are a bit unpredictable, and I feel very lucky that my university supports me in doing that. And we were successful in getting data into the computer, which was the main goal. Yeah, you can play it because there's no sound. I'll just talk over it. So from the camera data, we used the program Theia Markerless to extract the 3D data. If you want to know more about that, please don't ask me. Ask Martin, who's there in the stripes. From there, we were able to get to more familiar territory for me, which was the motion capture toolbox, which I believe there's a session coming up about that next hour. And we were able to make things work. Sometimes the clients didn't behave well, sometimes the computers didn't behave well. You can see that there was some less than realistic data collection there. But we also got some really great interactions as well, really sort of amazing moments where we had one client who wasn't very responsive in the first session and came in with their own music the next time and had these amazing dance interactions with the therapists, and left all of us in the lab going, that was incredible. And we have the data just to show it. And I'm just in the beginning of trying to make sense of the data from a numeric standpoint, and I won't belabor my attempts to do that because, again, I encourage you to go to the motion, the MCT toolbox workshop and the next session, because you'll learn a lot about that. But the crux of what this shows here is that in this video, there's not a whole lot of interaction entrainment going on. You can see that the colors, which are showing cross wavelet entrainment, are kind of flat, whereas in this one here, you see that there's entrainment going on at multiple frequency levels, which is also quite cool because they're in a seated position, so there's already some limits of what movement is possible, but we're still seeing quite a lot of entrainment, so that's good. And I believe that we have at least succeeded in the goal of showing that we can show something meaningful from this data, and I will continue to do more analysis on it, which will hopefully result in a paper at some point. So yeah, I sort of said this at the beginning, but so this was addressing the naturalism using markerless capture and define the population. What we did for this was we just asked, we recruited through parents. We said, is your child diagnosed? We assumed the parents would tell us the truth, which is fairly good assumption, but not perfect, obviously. But that was the solution we had in this case. And wasn't a design that really can address the causal relationship at all. All we can really do with this is show, here's where entrainment is happening, here is where it isn't happening. Once I get into the data, maybe we can show more entrainment in later sessions as opposed to earlier sessions, or more entrainment in clients who are less severely affected as opposed to those who are more severely affected. But there's not a possibility for causal work here. And pragmatically, I was able to include clients who were nonverbal, so they couldn't have given their own first-person verbal responses in any way, but they were able to contribute their own first-person data through movement. So I'm very excited about that and proud of it. A lot of pragmatic challenges with the markerless system. Like I said, it's new, we're learning it. The data is very, very big because we're not collecting 10-second clips of somebody throwing a ball, we're collecting sessions. And I think one client was about as much data as a feature film for every single client, so that was a lot, and we've had to work on that. And then the other question I have about markerless is how accurate is the data? As Alethea said, the baselines that we have for movement are based on typically developing populations, and particularly with markerless, the Thea system is based on algorithms that have learned on non-autistic adults. So is the data that it's giving me about these kids as accurate as it can be? Possibly not, but that's something to explore in the future.
Okay, so I'll present the second case example. This study is a study that we are currently recruiting participants, and we should be starting data collection next Wednesday, unless something happens. So I'll just mainly talk about the planning and the design. And for a bit of context, this study is a longitudinal study that will be happening during 2 years in public daycares of Jyväskylä in Finland. And the main goal of the study is to explore the effects of music and or physical education in children's social emotional development. So for this, our aim is to recruit 120 participants, and 40 of them will be receiving weekly music lessons, 40 of them will be receiving physical education lessons, and then the other 40 will just continue with their typical routine of being at daycare. We have measurements that are focusing on just the children, either between them or with an assistant, and the task involve social, emotions, and executive functions. We also have some reports by the caregivers of the children about their social, emotional development, and also by the staff from the daycare, so the ones that are every day with them. And we'll have some external observations conducted during the intervention group, so during music and physical education. So just for a bit of better understanding, and then I'll move into the more like the ASD part. Our main research question is how does participating in music or physical education training during 2 years affect children's social emotional development and children's executive function. But as part of this, and what it's more related to this presentation and to this workshop, is we'll have a subgroup of children that might be at risk of ASD. So every children will be screened for at-risk symptoms, and the main reason why we are always talking about at-risk is because these children will be 4-year-olds when they start the study, and they will be 6 when they finish. And in Finland, it's quite rare that at that age, the children will have a confirmed diagnosis of ASD. They start primary school at the age of 7, and that's usually when the formal diagnosis comes. So that's why we are mainly talking of at-risk population. But in terms of this group, our research question is how does music training affect the social development of children diagnosed or identified as being at risk for ASD? and how that relates to also their entrainment skills, if that will predict better social skills or not. So we'll have some measurements related to entrainment across the 2 years, and then I'll quickly explain how both interventions will be working with entrainment and how we have conceptualized it. So what I mentioned before was one of the challenges, how to define entrainment in naturalistic and with this population. So for the context of this group, we've established and defined a social motor entrainment, meaning that they will always first start with the whole group, and then they will move on to by pairs and training with pairs, and then with from very big, from the whole group to smaller groups, also because of the age, they're very young. And in terms of the intervention groups, we'll have music and physical education, which they have a lot of similarities. So we are also very interested in analyzing these similarity components, but also are there differentiate factors between them, and what are these factors that can affect the social emotional development. And in terms of entrainment, we have conceptualized it as that the musical groups will be focusing quite heavily on acoustic entrainment, so there will be a lot of components related to sound education during the groups. And in the physical education groups, it will be more about visual entrainment, focusing on gross motor skills and gestures. As I said, the population is defined as at risk due to the issues that I explained before. And as for the causal relationship, we'll have the longitudinal study during 2 years with 3 testing times. The measurement of entrainment, it is based on a tapping task and also on a perception timing task, so they will be tapping freely as they want. And that would also happen during the 2 years to analyze how also that changes with the at-risk and non-at-risk children. This will also be associated with the other factors of the emotional development and social skills as well. The main, as in the pragmatic level, we have, of course, need to take into account that at-risk population and with this young age, it might mean that they might not, of course, confirm the diagnosis later. It might also be showing some comorbidity with some other diagnosis or some other aspects. And also in terms of the inclusive process, this all will be happening in the daycare settings and during the schedules, during the everyday daycare schedule, also the measurements. Also, in order to encourage the agency of the children, although they're very young, but of course in the research process, all the interventions are very learner-focused. So there's the plan, but of course we need to remember their needs of every day. So.
All right, so that is how we have are currently attempting to address this complicated but we feel very important research topic. And I promise to give you some more time to chat. I'm not really sure how we're doing on time, but 12 minutes. Okay, so maybe for another 5 or 6 minutes, you can talk again in your groups. One thing we're really interested in is if you have different methods than we do, which I'm sure you do, you all have many different areas of expertise in entrainment and how we research it. How can you apply that maybe to autism research, or how might it apply theoretically? Always useful question for grants, for example, but also I really hope that you're interested potentially in studying this topic. So you can think about that, as well as we feel the causal relationship is quite challenging to tease out. If there's some thoughts or ideas that you have you want to discuss in your group, that's also interesting and important. And then we also, if you have some thoughts about defining entrainment in this kind of naturalistic context, that's another important question for discussion. So you can get back in your groups and have a little bit more of a chat, and then we'll finish up in about 7 or 8 minutes. All right, let's continue as the big group. We only have about 5 minutes left, but since there's a break afterwards, we can keep chatting if you like. Okay, does anyone have comments or of what they discussed, or ideas, or questions? Please.
I raised it inside our group a bit on the use of VR or AR as a methodological tool because you have control also over eye gaze, posture proximity, so it's easy to manipulate certain variables that might be useful and also make it more game-like or fun for a certain population using augmented reality and maybe not very humanistic like avatars, but maybe some more fun or game-like character to investigate these kind of things.
Yeah, that would be really interesting, actually, and I guess you would have quite a bit of control over how stimulating or not the visual environment was too, which can be a big issue, a big challenge for some kids particularly. Yeah, I've heard about some VR-related research for stroke rehabilitation, but not for ASD as far as I know. So, yeah, great idea. Go for it.
It's not so much a question as a comment. We were just talking about like the fact that autism is a neurodevelopmental disorder, that might just be a third variable, like later symptoms and the motor dysfunction or rhythm differences.
Yeah, I would say that it's really not entirely clear from the research where in sort of the developmental chain the synchronization motor issues happen. I did read recently that in infants who are later diagnosed with autism that there is an abnormal timing in brainstem reaction to auditory stimuli. So it may be that auditory related timing is a core issue, but truthfully we don't know a lot yet.
Thank you.
I was just wondering if there's been any meta-analysis study that doesn't involve that doesn't involve intervention of any sort, just to see if there's a correlation between kids with musical parents and incidence of ASD, with the assumption being parents of musical backgrounds have children with higher entrainment ability, whether it's nature or nurture.
Not that I know of either, but that's a really interesting question. And nature or nurture, we would have both there too, because presumably parents who are musical are doing a lot of music with their kids when they're very, very young. I sing to my daughter more than I speak to her. So not at all that I know of. That would be very interesting to explore.
I think we have 2 more minutes.
Okay.
Do you want to do a concluding statement?
Yeah.
Or
this went by really quickly. We'd love to have even more time for discussion, and please feel free to find either of us to chat more afterwards if you have any thoughts or ideas, and contact us via email as well. Anything to add? These are brilliant affiliations and wonderful support, and so we thank them and we thank you.
yeah, that's tomorrow morning, the mocap toolbox demo or tutorial. And now we have a 10-minute break before the keynote by Molly Henry, which will be here in this space.
If you can hear me, clap once. If you can hear me, clap twice. If you can hear me, clap 3 times. Can no one hear me? Why weren't you clapping? Thanks, Finn. Sabina wasn't, but just give me a little pout. Hello, everyone, and welcome back to the Entrainment Workshop. It is my great honor to introduce our next speaker. I first met Molly Henry back in 2015 or 2016.
I have no idea.
At McMaster University when she was at Western University, and we actually worked on a project together. And we've been talking about having her come to RITMO for the last few years, so it's such an honor and privilege to have you here today. Molly Henry will be talking to us about understanding neural entrainment using non-invasive brain stimulation. Please take it away, Molly.
Thank you. Thank you for inviting me, and thank you for organizing what so far has been a totally awesome workshop. I'm going to talk about many different things today, but I'm going to focus, in the end, the sort of empirical meat is going to be related to understanding neural entrainment using non-invasive brain stimulation. So I don't need to set up too hard with you as the audience, but the reason that many of us, all of us maybe are here is because we're interested in the fact that humans in particular synchronize our bodies with each other and with sounds when we're dancing, when we're walking side by side, when we're making music together, when we're engaging in sports together, and when we perform rituals. And this synchronization with each other is thought to underlie bond forming and maybe social cohesion. But my perspective is that we can't consider how we achieve synchrony with our bodies and with each other without considering that we have brains embodied in these bodies that we're syncing with, that we're synchronizing with. So the starting point for all of the research in my group is that brain rhythms synchronize with the rhythms of sounds. This is a waveform of speech, so this is a sentence that unfolds over time. And you can see that speech has fluctuations in loudness that give it a rhythm. And we know that brain rhythms, this is a cartoon of rhythmic brain activity, we know that brain rhythms synchronize with rhythms in sounds like these. By now, there's a decade or so of research showing that successful synchronization between the brain and the environment is associated with better comprehension for what's been said, better memory for what's been said, and also better success at solving the so-called cocktail party problem. So it's separating, paying attention to one person's voice in a noisy background. So by now, the field seems to have arrived at a consensus that brain-environment synchrony is good. And the explanation for why this is true is rooted in understanding rhythmic brain activity as reflecting fluctuations in neural excitability. So I'm not going to get too deep into any complicated neural analysis, but the idea here is that any complex full-band brain signal that we measure from cortex can be analytically decomposed into narrow-band brain rhythms. And we typically give these brain rhythms labels. These are the canonical frequency bands that we talk about, that we read about. This is a cartoon, let's say, of delta activity, slow activity. And the idea is that instead of having a meaningful y-axis like voltage, for example, we can put excitability on the y-axis. So what that means is that these fluctuations are fluctuations between up and down states, states when the bit of cortex where this rhythm is being generated is more excitable. That means the neurons in that region are more likely to respond to sensory information from the environment. So from the perspective of a single neuron, a neuron that lives in this sort of cortical neighborhood is going to be more likely to respond to sensory input at some times at the more excitable phases of this oscillation than others. So from the perspective of that single neuron, we can operationally define excitable phases and inhibitory phases. And it's maybe important to note here that our understanding of these excitability fluctuations comes not in the context of entrainment originally, but from measuring ongoing endogenous oscillations. So those are oscillations that are just happening when we're not doing anything or maybe not engaged in a task. So this is brain activity that's just happening. And when we talk about entrainment and the usefulness of entrainment, we make a little bit of a leap here. So our assumption is that since excitability shapes the timing of neural firing on its own, if we could align our brain rhythms with the rhythms in a sound, that would align these excitability fluctuations with the rhythmic structure of the sound, meaning that neurons are going to be more likely to fire at some time points than at others. And when a sound is rhythmic, synchrony does a good job of lining up the brain's excitable moments with moments in the sound where important content is likely to happen. So this is a mechanism for dynamic attending. We can attend, at times that we need to, but we can sort of take a rest at times where we don't need to be attending. And so this is thought to be, proposed to be, a metabolically inexpensive way to selectively attend in time. But this depends on our assumption that those endogenous rhythms that reflect excitability, that we know reflect excitability fluctuations, can become synchronized with the sound. That's a little animation mistake. So how do we typically test whether entrainment is happening? This is a stimulus rhythm. This is an amplitude modulated sound. It fluctuates in loudness every 300, it has a peak every 333 milliseconds. So this is a 3 hertz oscillation in the stimulus. And we can transform that stimulus into the frequency domain. So now we have frequency on the x-axis, amplitude on the y-axis, and you can see a peak at 3 hertz that corresponds to that 333 millisecond fluctuation in the sound. These are EEG data that were recorded during listening to that exact sound, and we typically transform those data also into the frequency domain, and we look for the presence of a 3 hertz peak that corresponds to the rhythmic structure of the stimulus. And this shows us that brain activity is synchronized to that stimulus. So what this means is that if we were to filter the brain activity so that we were only looking at 3 hertz activity, we'd find that it would be aligned with the temporal structure of the rhythm. And there are many different ways to do this. I'm talking about transformation to the frequency domain. You can transform to the time frequency domain. You can also use a narrowband filter and calculate something like coherence, for example. These are all methods that lead us to the same conclusion, that brain activity is synchronized with sound rhythms. And when we observe that synchrony, we usually label it entrainment. So one question the field has started wanting an answer to is this synchronized brain activity truly entrained? So we know based on our analysis that it's synchronized to the rhythm, so what's the difference? What do we mean when we say that a brain rhythm, or any rhythm, is entrained? And your answer to that question depends a lot on your definition of entrainment. I'm going to be pretty strict during this talk, but I don't necessarily apply that strictness when I'm reading papers or discussing with you, for example, but for the sake of thoroughness, I guess, I'm going to give you my strict perspective. So what we mean is that rhythmic neural activity, is generated by an oscillator. And that means that rhythmic brain activity is governed by the same mathematical and physical principles as any oscillator, like a pendulum or our circadian rhythm, for example. For a neural oscillator, we tend to adopt a certain set of criteria. Not that I don't have beef with these criteria, but I'm going to come back to that later. So these criteria tend to be these. First, the oscillation has to exist on its own. It's not created by the stimulus. It exists already, and it just becomes synchronized with the rhythm. In the presence of a stimulus, so this is what we mean when we say ongoing or endogenous activity. This is, like I said, the activity that's just going on. In the presence of a stimulus, the oscillation has to adjust. This isn't arguable, this is definitional for entrainment. The oscillation has to adjust to the stimulus rhythm. So any two pre-existing rhythms that have the same period, that have the same frequency, will be synchronized with each other, but that's arbitrary, right? There has to be some adjustment of the adaptable system to the environment. Then, once the stimulus is gone, the oscillation continues. This is the self-sustained property of oscillators, and we'll come back to that. So why does this distinction matter? Why does it matter whether a synchronized brain activity is really entrained or not? This is actually a mechanistic question with implications for attention and for cognition. So here's an example stimulus rhythm. One option, the entrainment option, is that an endogenous oscillation becomes entrained by that stimulus rhythm. But there's a second option, which we would call evoked activity, which we also know exists in the brain and is a huge contribution to our MEG and EEG signals. The biggest contribution, I would say. So here the idea is that a stimulus event happens and the brain responds. Another stimulus happens and the brain responds, and so on. So these are like event-related potentials, or ERPs, that we typically analyze in EEG data. The difference between these two options is that entrainment is predictive and evoked activity is reactive. So what do I mean? I mean that because entrained oscillations are in principle self-sustaining, they can go on when the stimulus stops, or when you can't hear it because it's being masked by another environmental sound, for example. So when a future event occurs that's in line with the rhythm that we have been listening to, an entrained oscillation will have us ready for it. But the evoked activity won't, because it's not being driven by the stimulus anymore. It's not being created by the stimulus. So it's going to cease to exist when the stimulus ceases. So we need this predictive sort of function for things like dynamic attending. And evoked activity by itself isn't going to support that. So from a cognitive perspective, it does make sense to try to tease these options apart. So how can we do that? How can we tell the difference? I've already showed you that a common signal processing technique is to transform a time domain signal into the frequency domain, or something related. So if I transform this entrained oscillation to the frequency domain, we look for the corresponding peak in the frequency domain, and we say that the oscillation is synchronized to the stimulus rhythm. Here, the stimulus rhythm arbitrarily has a rate of 1 hertz. The problem is that with evoked activity, since it's being driven by the same stimulus, we also will still have that same peak, because something's happening periodically. Here, every 1 second, it's just a different something. So you might pick up on the fact that the harmonic series in these two frequency domain representations look different. That's not helpful, unfortunately. The only time that we'll ever have this single peak situation is in the case of a pure sinusoid, and that's never what brain activity actually looks like. This inability to rely on the harmonic series in a frequency domain representation is especially problematic when the stimulus gets even a little more interesting than an isochronous pulse train. So now imagine alternating between strong and weak beats that give rise to some kind of hierarchical structure, like a very simple meter. So this would be back and forth between strong, weak, weak. And if we imagine then that we have nested oscillations, so two oscillations at the same time, one entrains to the sort of subdivision and the other entrains at the meter or the emphasis rate, we're already introducing harmonics into our assumed oscillation. So signal processing alone is not going to save us when we're trying to separate entrained from evoked activity. So how can we tell the difference between entrained and evoked activity? The simple answer to this question is we can't. At least not in human MEG, EEG data. It's not possible. So what can we do? It's not dire, I don't think. Can be frustrating, but I think the answer is in integrating across converging methods, and there's no one study that's going to by itself solve this issue. We're not going to talk about it, but there have been some recent modeling efforts that are quite good along these lines. Non-human animal data can actually be quite informative here, and we can get a long way with creative experimental designs that incorporate human behavior. And I'm going to spend most of my time talking about non-invasive brain stimulation today. And I will, at the end, emphasize how important it is, since oscillator models make very specific predictions. We can mathematically sort of derive predictions that we focus on theory and we derive testable hypotheses for ourselves. So I'll spend the rest of my time talking about these. I'm going to start by talking about the informativeness of non-human animal work for this dilemma. So I'm going to talk about macaque work using specifically recordings that penetrate the cortex. So this is an electrode, and it has those little black dots are contacts. So those are recording sites on this electrode. And this is cortical depth on the y-axis from superficial, the surface of the cortex, to deep, so inside. And cortex has different layers, and we can group them into categories. So we have supragranular, granular, and infragranular layers in the cortex. And the reason that these are different from each other is that these cortical layers have different types of neurons, and they also have different connectivity patterns to each other and to different parts of the brain. So for example, some layers, the deeper layers, are more likely to respond to stimuli from the environment, and so contain evoked responses. But other layers, like the supragranular layers, for example, might have more what some people say is computational functions. It's hard to say exactly what that means, but basically more top-down drive in these supragranular layers. So this is a plot of current source density, and I'm going to give you a super quick primer about the different signals that we can measure in an experiment like this. So current source density is a lot like what we measure in MEG and EEG. It contains slow activity, that's because of the way that it's filtered. So oscillations, if they're present, and evoked responses, if they're present. It can be measured in supragranular, granular, and infragranular layers. And the important part is that slow oscillatory activity is present in supragranular layers in the absence of stimulus. So we measure endogenous, ongoing oscillations in the supragranular layers. There's another signal that we can measure, which is called multi-unit activity. Multi-unit activity really is thought to be a quantification of neuronal spiking. So this is evoked activity. These are neurons that are responding to stimuli in the world. Multi-unit activity is measured in granular and infragranular layers, so these deeper input layers. And neuronal firing is only present in response to stimulation. Other than spontaneous background firing, we know that's present, but this kind of organized firing where you have a pattern of not firing, the dark red is where there's lots of neuronal firing, and the yellow is where there's very little neuronal firing. That kind of organized pattern of firing you only have in the presence of stimulation. So the paradigm in this experiment that I'm going to tell you about is to listen to two rhythms at the same time and to pay attention to one of those streams. So that sounds like this. Okay, and the monkeys are paying attention to one of these streams. We know that because there are infrequent targets in each stream, and the monkeys have to indicate when they heard a target in one of the streams and ignore the targets in the irrelevant stream, so you know that they're selectively attending. You probably could hear that there's a big frequency difference between these two rhythms. So that was, in this case, a 2-octave frequency difference, and that's going to be important in just a second, but let me orient you to this plot in terms of the paradigm. So now I'm plotting two tone onsets on our plot. I've just taken a sort of, a snapshot of the sequence. And you can see that the neural responses are structured and reflect the rhythmic properties of the stimulus. So I'm going to zoom in here on one bit of the supragranular activity, and you can see it's alternating between positive and negative. So that's an oscillation that's entrained by, well, we would say entrained by, I'll show you evidence for that in a second, by our stimulus. And the strength of neuronal firing, which I've already shown you, is also coupled to those fluctuations, as we would expect if, first of all, evoked activity is being driven by the stimulus, but second of all, if evoked activity is being organized by fluctuations in excitability that are represented in this supragranular slice. Here there are tones evoking activity, so we can't tell the difference between those two options. So here's the trick. Auditory cortex is tonotopically organized, so that means that any specific neuron or group of neurons will like and respond to one tone frequency, but won't like a frequency that's far away from that. And that's organized spatially in primary auditory cortex. So any neurons we record from are going to have a best frequency. They're not going to like frequencies that are 2 octaves away from that. So we can record from neurons who really like the stimulus frequency of one of those rhythmic streams, and we can record from another group of neurons that don't like that stimulus frequency. So when we record from neurons that like that frequency, this is multi-unit activity. So unsurprisingly, they fire a lot when a tone is presented. That's their favorite frequency. This makes a lot of sense. And if I plot the current source density, we can see what looks very much like an oscillation with evoked activity added to that. And we can't separate here in this signal between the two. When we record from neurons, different neurons, that don't like that same frequency though, they don't fire. They don't like that frequency. However, current source density fluctuates in exactly the same way. So we see slow oscillatory activity from supragranular layers is entraining to the stimulus sequence, even though that sequence is not evoking responses in the neurons in this area. So invasive recordings like this allow us to see entrained oscillations even when there's no evoked response. So I'm going to switch now and talk a little bit about behavioral work. I'm going back to our speech example. So again, the idea is that excitability fluctuations become coupled to the rhythmic structure of sound. That means neurons are more likely to fire when important stuff should be happening. I'm an experimental psychologist, so I don't know when neurons are firing or not firing. I don't have access to that information, so I wanted to approach this question behaviorally and provide another angle onto this distinction. So the idea that we had, and others of course also had, is that if we could sort of zoom in on these neural excitability fluctuations, and if we could present near threshold targets at different phases of that neural excitability fluctuation. So what I mean by near threshold targets are little sounds that you hear 50-50. Half the time you hear them, half the time you don't. And so we suspected that those times when you hear them are more likely to be when that bit of cortex is excited, and the times when you don't hear them are more likely to be when that bit of cortex is inhibited. So we thought if we could sort of probe all the way around the neural excitability fluctuation, we'd be able to see a pattern of target detection performance that mimicked that. So in high excitability phases, our brains are more likely to respond to, we're more likely to perceive and become conscious of targets. This behavioral prediction is not made by an account based on evoked activity. It has been pointed out that maybe it could be, but maybe a lot of things could be. This falls out really nicely from a neural excitability perspective, but it's a tougher one to derive from an account based only on evoked activity. So here's how we did that experiment. This is our sound. This is a constant amplitude sound, and you can see that there are little gaps here. Those are our targets. They're just little silences that we leave out of the sound. The participant's job is to detect those little silences, and we adjust them individually for each person, so they're right at 50-50 for you, duration-wise. The rhythm here is communicated by fluctuations in frequency, and that's important because the rhythm has a constant amplitude. It's on the same amount all the time. So we can put those little silences everywhere, and it's fair in terms of detection. What you can see, let me play that for you real quick. And there was one of the little silences. I made it really big so you could hear it. They were never that big. So what you can see here is that we have gaps at two different phases of the stimulus rhythm. So one kind of in the trough here, one kind of in the rising phase here. And over the course of the whole experiment, we presented many gaps at many phases that were spaced around the cycle of the stimulus rhythm. And the idea was that if brain rhythms are synchronized to the stimulus rhythm, we're also probing detection performance at different phases of the entrained neural oscillation. So first, we have to show that the brain was actually synchronized to the sound. I'll do that in exactly the way I've already described. So this is a frequency domain representation of EEG data that were recorded during this task. And you can see that there's a peak here. In this experiment, the stimulation rate was 3 hertz. So we know that brain activity of some sort is synchronized to the sound. And now I'm going to show you behavioral data for the gap detection task. This is just for a single subject. So on the x-axis here, we have stimulus phase. The black thing is a representation of the stimulus. So here gaps would have fallen in the peak, here gaps would have fallen into the trough. We can also plot brain phase here. So we can do an analysis where we look for each gap, what was the brain doing right before that gap happened? And we can sort every single gap into a sort of phase bin and plot the data that way. It looks the same. So we can plot this in terms of stimulus or brain phase on the x-axis. And hit rates on the y-axis. So what you can see is this person's ability to detect gaps depends on where those gaps fall with respect to the phase of the stimulus rhythm and the entrained brain rhythm. This is just a single subject worth of data. We've now replicated this over, I don't know, I would say 200 subjects, sometimes over multiple sessions. We've done many, many experiments like this. This is also reliable, so if you measure this for a participant and bring them back on a different day, their data look the same when they come back. So this is a reliable signature, a behavioral proxy of entrainment. These are just to show you a couple examples of other subjects. So here what I want to tell you is that behavioral patterns are consistent with entrainment of endogenous neural oscillations, so with entrainment of excitability fluctuations. So I'm going to switch now to the sort of meat of the talk, and I'm going to talk about using non-invasive brain stimulation to study entrainment. So in my lab, we've been using transcranial alternating current stimulation, or TACS. TACS works by applying a weak alternating current, electrical current, to the scalp of a participant. And we know that this weak electrical current is capable of entraining endogenous oscillations. We know this from animal work, and we know this from work even stimulating groups of neurons that live in a dish. And depending on the electrode placement, sorry, this microphone is driving me insane. Depending on electrode placement, we can target specific brain regions. So you can see we have a specific electrode montage here for this participant, and this is an electric field simulation showing how much current is getting where in the brain. And here we're targeting primary auditory cortex. This was a target that we functionally defined based on an fMRI study that we did with the same subjects. So what's the advantage of using electrical stimulation? Why am I interested in this technique? We know that both auditory stimulation and electrical stimulation are capable of entraining neural oscillations. In addition, auditory stimulation evokes neural activity in response to sounds. And in any EEG, MEG signal, these signals are all mixed up. And as I said, no signal processing technique is going to take them apart. The important thing is that electrical stimulation does not evoke neural responses that weren't present to begin with. It's much too weak to do this. There's lots of work also showing that TACS can only interact with a brain state, a brain rhythm that's currently active, that's present. So this is satisfying the assumption that the oscillation already exists. We can't create a brain rhythm out of nowhere and interact with it. It has to be there first, and then the electrical stimulation is capable of picking it up. So we know we're interacting with endogenous brain activity, whether it's entrained or not. So we're using the same behavioral paradigm that I just described, so this gap detection and frequency modulation experiment. Here what we did was we have a sound rhythm, and with respect to the sound rhythm, we varied the lag, the temporal relationship of the electrical stimulation to take on one of 6 values, and I'll plot those here on a circle. So you can see the 0 phase lag condition is synchronized perfectly with the audio. The out of phase stimulation condition is anti-phase to the stimulus rhythm, and we've got conditions in between. We also included a sham condition, so this is where we turn the stimulator on for 30 seconds and then we turn it back off. So that initial ramp up is when people are most likely to feel that they've been stimulated and know that they're in a stimulation condition. After about 30 seconds, they don't feel anything anymore. So when we turn the stimulator back off, this gives us a baseline condition. And we did this in 2 sessions. We can only stimulate for 50 minutes per session. So we brought the participants back twice. So I'll show you both sessions of data. So here we wanted to understand, can TACS in principle interfere with oscillations that are already being entrained by a sound rhythm? And here we wanted to ask what the nature of that interference would be. And this has implications for how TACS might be used. There are a lot of ideas that brain stimulation might be used as an intervention, that maybe we could improve entrainment and improve listening success, especially in older adults or in noisy environments, for example. So we have to know how exactly we're interfering with those entrained oscillations. So we like to talk about 2 general families of hypotheses. These are not mutually exclusive. They're just our sort of 2 endpoints. And I'm going to describe those in terms of the behavioral dependent variables that we're going to be interested in. So we have two dependent variables. This is, again, the single subject, single participant gap detection hit rate data that I already showed you. We can quantify that in two ways. One is what I call behavioral modulation depth. That's how tall this modulation is. So for some participants, their behavior matters or depends a lot on the stimulus. And for other participants, their behavior doesn't depend very much on the stimulus. So that modulation depth, we think, is a behavioral proxy for the strength of neural entrainment. Another dependent measure is what I call preferred FM phase. So if we find the peak gap detection performance, what's the phase of the stimulus that yielded that? That's that person's favorite stimulus phase. That led to them doing the best in terms of the gap detection task. So the first family of hypotheses is that TACS might rewrite what the brain is naturally doing. So what I mean is that TACS might actually be capable of dragging the entrained neural oscillation into a new phase relationship with the stimulus. So when we shift the phase of the TACS relative to the audio, we'd be shifting the phase of the brain relative to the audio. So here I'm plotting cartoons of what that might look like. So in the 0 phase lag condition, the pink one, we expect alignment with the stimulus. This is hit rates, I should say. This is our behavioral proxy that I'm plotting a cartoon of. And as we dephase the electrical stimulation with respect to the audio, we're expecting to drag the brain into a new phase relationship, and that's going to change the preferred FM phase. So this hypothesis is tested based on looking at this preferred FM phase dependent measure. The other option is that TACS might interfere with brain activity. So the brain might keep its own natural phase relative to the audio stimulation, and in that case, dephasing the electrical stimulation relative to what the brain's doing would actually mean, think constructive versus destructive interference. So if we line them up together, we'd be able to boost the strength of entrainment, and if we cancel them out, if we use the electrical stimulation to cancel out the brain rhythm, we're going to reduce the entrainment strength. So when the TACS is aligned with the stimulus in the 0 phase lag condition, we're expecting an enhancement of that behavioral modulation depth. And as we dephase the electrical stimulation relative to the brain, we're expecting destructive interference. So this is a hypothesis that's tested based on this behavioral modulation depth parameter. These are just a few single participants, so you can see the type of data that we're working with. This is 3 participants in 2 sessions each. Gap detection depends on the phase of the stimulus into which the gap fell, so you can see these are fluctuating with the stimulus rhythm, as always. And you can already see, just by eyeball, that if there's any shift in the preferred phase of the stimulus, it's going to be really, really minor. So we will start there. I'll show you the phase data first. So I'm going to plot circle plots now. So each plot is going to be for one of the phase lag conditions. Color is session 1, gray is session 2, and then you have 2 resultant vectors, one in color, one in black for the 2 sessions. And remember, if the TACS is dragging the brain into a new phase relationship, we expect these resultant vectors to rotate their way around the circle, and that's absolutely not happening. So TACS is not capable of dragging the brain into a new temporal relationship with the sound, at least in this paradigm. So that doesn't mean that any entraining rhythm wouldn't be capable of being phase shifted, but here we've basically set up a competition between the audio entrainer, which is very, very strong in this situation, and an electrical entrainer, which is very, very weak. So it's not necessarily the case that in every experiment you're not going to see that phase shift, but we didn't see it here. But now we'll ask whether TACS is capable of interfering with entrainment. So we'll leave the brain in its natural phase relationship to the stimulus, and we'll expect to see constructive and destructive interference depending on where we're putting the electrical stimulation. So first, I'm plotting the data for the sham condition. So this is when we're not stimulating. This is our baseline. And this is behavioral modulation depth on the y-axis. So remember, that's the tallness of that behavioral function, behavioral modulation. And just a reminder that what we expect to see is a sinusoidal modulation of this dependent variable. So as we phase shift, we expect constructive versus destructive interference and in between. Ideally, with respect to the sham condition, we want to see a strengthening and a weakening of this behavioral modulation. I would point out that in the literature trying to use TACS to change listening behavior, it's very common to see that you can make performance worse, but it's very uncommon to see that you can actually make performance better. And that's really important to show if we're actually going to talk seriously about this being used in an intervention kind of capacity. So here are the empirical data. This is exactly what we see. So we see this sinusoidal modulation of behavioral modulation depth. And again, we did that in 2 sessions, so we internally replicate this effect. Here I'm just sort of brutally binarizing the data to show you that when we have, this is our sort of positive half of the cycle, and this is our sort of negative half of the cycle. And all I want you to notice is that we did significantly improve or strengthen, I should say, and weaken that behavioral proxy of entrainment. So here we found that TACS interferes with entrainment of neural oscillations by a constructive and destructive interference, at least in this case where we set up a competition between a strong auditory rhythm and a weak electrical rhythm. I'm going to talk about one more TACS study, but I'm going to pause real quick to talk about another property of oscillators. And this is preferred rate and the associated entrainment region. So preferred rate's called lots of different things, depending on the literature that you're reading. Preferred rate, preferred frequency, preferred period, natural frequency, eigenfrequency. You may have seen any of these names. The idea is that an oscillator has a preferred rate of oscillation. All oscillators do. So for our circadian rhythm, for example, the period's 24 hours. Oscillators have a bit of flexibility, so they can go faster and they can go slower. This is a necessity for entrainment. They have to be able to adjust to some extent. But they don't like getting too far out of their own comfort zone. So here the x-axis is the rate of a stimulus with respect to the preferred rate of an oscillator, which is right in the middle here. On the one side, the stimulus is too slow, and on the other side, the stimulus is too fast relative to the hypothetical oscillator. So what we predict is something like a tuning curve around the preferred rate. So we have entrainment strength on the y-axis here. When the stimulus rate matches the preferred rate of the oscillator is going to entrain very easily and with a lot of strength. The farther and farther we get away, the larger our detuning, you could say. The larger the difference between the preferred rate of the oscillator and the stimulus, the weaker entrainment's going to be. And the sort of width of this thing, the space in between here is our so-called entrainment region. So within this region, entrainment is possible. Outside of this region, entrainment is not possible. So an oscillator has to be flexible, definitionally, for entrainment to occur, but no oscillator can be infinitely so. So we're doing now the same task. It's a gap detection task in a noisy stimulus. But here the stimulus is not rhythmic. So we don't have an auditory rhythm. So we're not entraining anything. The electrical stimulation is our only entrainer. So the way that we set this up was instead of placing gaps into different phases of the stimulus, we placed gaps into different phases of the electrical stimulation. So here's a schematic of that. This is TACS phase now, electrical phase on the x-axis, and this is just a schematic of the electrical stimulation, the actual, the amplitude of that. We probed gap detection at 6 different gap locations. So again, if the electrical stimulation is entraining endogenous now, because they're not entrained to the audio stimulus, endogenous oscillations, then we expect to be modulating neural excitability, and we expect to see gap detection hit rates changing sinusoidally as a function of TACS phase. That's our prediction. We applied the electrical stimulation at 4 different rates, and we sort of roughly sampled the so-called delta band. And for each frequency, we're going to look at how strong this behavioral modulation is. In my lab, we're focused a lot on individual differences. So here we're not actually interested in differences between these stimulation rates. We didn't have any hypothesis that one rate was going to do a better job than another, but we were interested in whether different stimulus rates, different electrical stimulation rates, worked better for different people. So the idea here is, or the question, I guess, is whether we can capture an individual's preferred rate of endogenous oscillations and then use that to look for an entrainment region and test a critical hypothesis of oscillators. So remember this pattern. This is what we're predicting. And again, this is exactly what we found. So we have TACS phase on the x-axis and gap detection hit rates on the y-axis, and you can see that these middle points are better than these outside points, no matter what the stimulus rate is. So that's significant for all of the stimulation frequencies. And here again, I'm just going to brutally sort of binarize the data as an illustration. I'm going to group them into the best and worst phases, just to show you that there's, for each frequency, a significant difference. Hit rates are better in what we call good phases and worse in what we call bad phases, and the magnitude of that difference does not depend on the stimulation frequency. But again, that's not what we hypothesized. What we're interested in here is individual differences. So the idea is that one person might have really been strongly affected by this particular stimulation frequency, and another person maybe less so, but maybe a different stimulation frequency worked better to modulate their behavior. So as an initial analysis, so here on the y-axis, I'm going to put TACS effect magnitude. You can think of this as a kind of best minus worst. So just how strong, you can also think of it like the behavioral modulation depth parameter I already explained. How strong is that behavioral fluctuation? And this is a noise floor that we created using something like a permutation test. The details are not important. In that band or below means that the behavioral modulation was not greater than one would expect by chance. And these are individual data, individual participants in the dots, and then the summary is in the box plot. You can see that there are some individuals for each frequency who had a behavioral modulation that's greater than we would expect from chance. The interesting thing is that these are all different dudes for each frequency. So each of these groups these are not overlapping. So some dudes were very strongly modulated by the lowest frequency. It's different dudes that are very strongly modulated by the highest frequency. And so to try to summarize that, we submitted these data. So these, it's 4 data points per person, the TACS effect magnitude as a function of TACS frequency. We submitted those to a cluster analysis. And that cluster analysis revealed 3 patterns. So these are 3 groups of participants, 3 groups of dudes. So in our first cluster, we have a sort of, we have this group who were really strongly modulated by the slowest electrical stimulation, and progressively less so as the stimulation became higher frequency, as the rate sped up. In this third cluster, we have the opposite. So we have people that were very strongly modulated by the fastest electrical stimulation frequency. And in the middle, we have this sort of bandpass group that were most strongly modulated by the frequencies in the middle. And to try to interpret that, we implemented a computational oscillator model. So this is a Kuromato-like model, where we have a single oscillator that we assume different preferred rates for, and then we stimulate it with a fake TACS signal at all of these different frequencies. And by assuming an oscillator with a slow preferred rate, a medium preferred rate, or a fast preferred rate, we're able to exactly recreate, well, exactly. These look a lot nicer than our behavioral data, as always, they're model data. But we're able to qualitatively recapture these 3 patterns. So the low frequency likers, the middle frequency likers, and the high frequency likers. So the prediction of these 3 clusters actually comes out of an oscillator model if we give it different preferred rates. So different TACS frequencies entrained individuals' neural oscillations to different degrees, and behavioral patterns were predictable from an oscillator model for which we assumed different preferred rates. So what's next? Right now, we're in the process of re-recruiting participants from these 3 clusters. And we are testing them on an EEG version of the gap detection task where we use the rhythmic auditory stimulus at these 4 different rates. And so the question is whether using TACS we're actually identifying the preferred rate of an endogenous oscillation, and we're able to predict at what frequency they're going to best entrain to a driving stimulus in the world. So, to conclude the sort of empirical bit, non-human animal and human behavioral work can help us to separate neural entrainment from evoked activity. TACS interferes with neural entrainment via constructive and destructive interference. And TACS at different frequencies reveals preferred rates of endogenous oscillations in the auditory system. So the second point shows us the specific way in which we can expect for electrical stimulation to interact with oscillations and informs our designs going forward. And based on this third point, we think we can leverage this technique to test hypotheses of an entrainment, the presence of an entrainment region, which would be further strong evidence for entrainment of oscillation or of brain rhythms that are generated by an oscillator. I'm going to abuse the few minutes I have left to come back to this cartoon that I presented to you at the beginning of this very simplistic set of criteria for what it means for an oscillation to be entrained. So at the beginning I said the oscillation exists before the stimulus is present. Really what I mean is that the oscillation exists in principle. It can exist. It's not quite nuanced enough to say that it must exist. We must be able to see it in silence, for example. And without nuance, we might be hunting for something. We might be hunting for a prediction that, without justification, I guess. So an oscillator might be damped. That means without input, it decays to a fixed point. So when we stop stimulating it, the oscillation goes away. It follows from that that there's no oscillation before the stimulus starts. So if it decays back to a fixed point after the stimulation is over, before the stimulation starts, you wouldn't expect to see any oscillation. That doesn't mean that the activity generated during stimulation is not being generated by an oscillator. It just needs some external energy to produce its oscillation. So this might be problematic, for example, if we hunt endogenous activity during resting state, for example. If we want to know about the endogenous oscillations of the auditory system, silence might not be the best option. We might need to put a little noise into the system, for example. The auditory system it's not naturally very peaky in terms of a frequency domain representation. It's not very easy to see anything that looks like an endogenous oscillation during silence, but actually the entire spectral profile of what the auditory system is producing changes as soon as you give auditory input. So as soon as you give a bit of noise, for example. We also tend to assume in some of the literature that in order for entrainment to music, to the beat of music to be a thing, that we need to see this, endogenous 2 Hertz oscillation in the auditory system, and that must exist on its own. And again, what I'm trying to emphasize is that we might not expect to see this depending on the situation in which we're hunting. This also has implications for how we use electrical stimulation. So I said already that TACS can only interfere with active existing oscillations, which is why in the experiment I explained to you, we're stimulating with noise, even when we didn't want to use a rhythm. We're trying to activate those endogenous auditory oscillations so that we can actually talk with them. The second part, I think, is a bit less controversial. So the oscillation adjusts. That has to be true, but it's not infinitely flexible. I think that this has implications for randomly choosing a stimulation frequency in a one-size-fits-all way for all of our participants and expecting to see entrainment to the same degree. We've already talked about this, but the last study that I explained, what I'm trying to emphasize is that preferred rates and entrainment regions might not look the same for everyone. And so in my lab, we've been working on techniques to try to estimate these preferences a priori and then target each person's preferred rate and look for their own personal entrainment region. The last is my pet peeve assumption. So that's that the oscillation continues. There are three possibilities for how this might happen. The one I see in the literature most often is that the oscillation continues with the same properties as the stimulus that was just being presented. So we tend to look for self-sustained oscillations in silence after the stimulus has ended as evidence for true entrainment. But there are two other possibilities. One I've already explained. That's the third one. I'll say that next. The first, which I'm showing you here, is that the oscillation continues, but it decays back to its own preferred rate. And you saw this in Edge's talk this morning. Another possibility is what I just explained a few minutes ago, that the oscillation is damped, and it decays to a fixed point, so it decays to no oscillation. And in reality, these latter two options are metabolically less expensive, and so theoretically more likely to be what's happening. So the oscillation, I would say, can't be expected to just keep on going forever with the temporal properties of the auditory stimulus unless it has a reason to. So now we're back to talking about creative experimental design. If we give the oscillator a reason to try to predict something that's coming up in the future, for example, we might expect the system to internally generate, we might say top down, we might say attention, but internally generate some energy to keep that oscillation going rather than decaying in either of these more natural ways. And I'm happy to discuss this more, and I'm sure we'll talk about that in the panel tomorrow. So I'll go back to my empirical conclusions to end so I don't leave you on that sort of, I don't think it's pessimistic, I think it's realistic, so I don't leave you on that theoretical note, but I'll go back to my empirical conclusions, and thank you for your attention, and I think I have time for a few questions, I hope.
Thank you so much, Molly. In the great words of a wonderful neuroscientist, Molly Henry was such a killer choice, dude. This talk has been awesome. And that's come in all the way from Montreal from Connor. So thanks, Connor Speech, for your input. I think we already have a first question.
Okay,
so Peter.
Let's do it.
Thank you very much, Molly. That was really impressive. And it makes me wonder, so you were focusing on the auditory system.
Yeah.
So auditory cortex, trying to manipulate and measure what's going on there. But I think some of the issues that you touch on, they raise questions about connections with the motor system.
Oh, absolutely.
So if you're talking about preferred tempo, there are ideas that this is somehow related to the motor system. It influences, and motor capacities might do that. And also the idea of some self-sustained things. You could imagine a loop going on where it kind of reinforces one another. So I'm wondering if that sort of fits into your big picture, and if so, kind of how, and if there's evidence for it in the line of work that you're doing.
Yeah, it 100% fits with what I'm talking about here. So here today, I've concentrated on the auditory system. We also do some work in the lab bringing our bodies into the picture. When I talk about oscillators and when I talk about preferred rates and entrainment regions and things like this, I'm not thinking of I don't actually believe that any part of the brain or the brain itself is an oscillator, but this is a sort of a way to describe. And what I think is that the oscillator that we're trying to characterize depends on the system that's in play. So here we're talking about auditory perception, and the stimuli that I'm using are not even beat-based. We don't have to internally generate anything. But when we bring our motor system into play, or we start using musical rhythms, for example, where we might have to impose a structure, we're talking about a different system. And some of the work from my group has shown that preferred rates differ. We can't predict preferred rates for all things from all other things. So there are some relationships between preferred rates for perception and production, for example, but bringing the body in tends to slow preferred rates down, at least in what we've seen. But the task has to be really similar. So if you then move to try to predict preferred rates for listening to music or tapping to music versus a spontaneous motor tempo task or a sensory motor synchronization to a metronome, for example, these systems actually tend to have different preferences. They have different preferred rates, and I would predict they have different entrainment regions. We also think about the width of that in terms of adaptability and how flexible a person is. So I think it's 100% in line to say, you know, now we're talking about a system that's a network and incorporates connections between the auditory and motor system, the brain and the body. Yeah, same principles apply, but I truly believe that we have to characterize those systems differently because it's a different network now, and we can try to relate them to each other and see what kinds of predictions we can make, you know, across these systems, but we sort of have to look at it with fresh eyes, I would say. Does that answer your question?
Yes, it does. Thank you.
Thank you so much. We'll try to balance the in-person questions with the online. We have one in from Connor, actually. So any plans to correlate these endogenous neural and behavioral oscillators with participants' spontaneous motor tempi?
We actually have collected spontaneous motor tempo data for every person, for every experiment we've done in the last 5 years. We also tend to re-invite participants over and over again, so we can look at their preferred rates across different paradigms and in neural stuff versus behavioral stuff, for example. So we have, we have spontaneous motor tempo for everything we've ever done. It's not a great predictor of very many preferred rates. It predicts preferred rates for tapping to metronomes super well. Again, I think this is because of the system that we're talking about. You know, spontaneous motor tempo, you just tap your finger at a comfortable rate. That predicts how you like to tap your finger to a metronome. It does not predict how you like to listen to music, what kind of frequency modulation you like to listen to, what endogenous frequency we're able to pick up using TACS. Those things are not related to spontaneous motor tempo in our hands. But again, the tasks have to look like each other because the system needs to be similar. You know, so what's the neural network underlying what you're doing? What's the body contribution to what we're doing? What are the cognitive demands for what we're doing? That all changes the system, and the farther away you get between systems, the less likely they're going to predict each other. And so spontaneous motor tempo it does work in some cases, but it's really specific actually.
Do you then have like a hunch of where these preferred alternating current rhythms then are coming from within the participants you've had?
Those, I believe, are endogenous, sort of preferred rates of endogenous activity that the auditory system would spontaneously generate when you're listening to sounds. It doesn't have to be a rhythmic sound, but when the auditory system's being driven in some way, when there's energy being put in from the environment to the auditory system. I have, you know, speculate like crazy, but every single person's auditory system looks different. So we have different gray matter concentrations, we have different connectivity strengths between the auditory system and different parts of the brain in terms of, you know, white matter tractography. There's different amounts of myelination, there's different cortical folding patterns for each person. Like, no two people's auditory systems look the same. And so, I mean, a dream scenario would be to actually understand why there are differences. I mean, I think it's clear that there are differences between people, but where those come from in a sort of structural or like a real sort of brain way, I don't know.
Mm-hmm. But I mean, even if we don't know where they're coming from, it sounds like, I mean, this reminds me of personalized medicine with the examples you gave in applications. That's really cool. Are there any questions from the audience again? Here you go.
Thank you very much. You were hinting or saying that it's not reasonable to think that the oscillator would continue spontaneously unless there is a good reason. Can you elaborate on that? I was thinking maybe a gap in the stimulus and then return to the stimulus would drive the system to continue. But maybe you can elaborate on what you were meaning.
That's exactly what I mean. That's exactly what I mean. I think if we're stimulating, and then we stop the stimulation, and the participant, whether it's a human or a non-human animal, knows, okay, sequence is over. I can quit doing my task now. There's absolutely no reason that we would assume that that would keep going. I mean, it might in the case of, in the visual system, alpha oscillations are very much more measurable during silence and measurable after a stimulus. It still decays back to its own preferred rate, actually, but so to answer your question more precisely, that's exactly what I think. So if we would create a situation where you have a rhythm and then there's a break and then you have to do a task. I mean, some of the tasks we've seen presented today already would be good candidates for something like this, where you have a break that you have to extrapolate through. That's actually the task. And then I saw a recent talk from Fleur Bauer, who did something like this, where there was a sequence and then a break, and then you have to judge something about a tone that happens in the future. And there they actually did see a peak at the stimulation rate during the silent bit, because you have to operate on something that's coming up and you have to predict the timing of that thing. So yeah, I think it's all about experimental design, actually, to be able to see that.
I'm so sorry to cut this question answer period short, but we have only a 10-minute break until the next presentations, and I will send Emily Graber and Roger Moore's questions to you over email and connect you with them, if that's okay. Thank you so much. Another round of applause for Molly, please.
Thank you.
And we actually have a 15-minute break, so please enjoy the coffee and the snacks at the back. Sorry, everyone. We'll be back at 4:45 for the last 3 presentations of the day. Thank you. Okay, great question, Carolyn. So the plan is that basically you guys are going to watch the presentation on YouTube. The YouTube stream is like 30-second delay. So if you could come back into the Zoom room a minute before your presentation ends, then we're certainly certain to have you. And then if, do you want to do a waiting room or should we just do? Yeah, so what we'll do to make sure that you don't interrupt anything here is we will put you in a waiting room and we will admit you one by one into here. So when a person asks a question here though, what might happen is that, at least what happened in the last presenter, is that we could actually hear the person here through the speakers of your, like the person, you, or the remote person's computer. So if you have headphones, it's maybe better to just at least have them ready in case we're getting this feedback, which is happening due to like faulty Zoom damping of the person on this end. And then that way it doesn't have this like delay effect that makes it challenging for the person here asking the question. Is that possible for you guys? Thanks, Dan, Carolyn, and Alexander.
Yeah, I gotta check
No
for headphones.
headphones.
Can you hear me now?
Yeah, it's about the same level. It's a little quiet, but maybe we can turn it up.
I'll try to switch
maybe it's
mic.
just me then. It's just some like background noise here. So yeah, it could be good, and we can actually adjust the audio from the computer here. So that's fine if it's the best you can do. Thank you so much. And Carolyn, no headphones? Okay, no worries. I'm sure it'll be fine, and people were just fine earlier. So yeah, it'll be good. Anything else we have to say? Okay. So first is Dan Cameron, and then we have Carolyn second, and then we have Alexander Demos third. No, it's sorry, forgive me. Carolyn and Alexander, should you both be admitted in the question answer period during the second talk, which is analytical models of synchrony and entrainment in larger groups? Are you sure? Okay. Sure? Yes. Okay. Yes. Are you getting feedback now? Feedback as in microphone. Bad. It sounds bad. Oh. Yeah, a 30-second delay. Okay, well, but you see you're watching on YouTube. That's cool. So we're gonna put you in a waiting room so you won't be able to hear anything here. And then this is why there's a 30-second delay coming in again. But if you muted your YouTube, there shouldn't be. And the way you do that is you in the video on the left bottom. Oh, and Jessica Grau's entering. Amazing. Exciting. Okay, so Jessica and Daniel are in the first talk. We'll admit both of them. And then Carolyn and Alexander in the both of them in the second talk. And then just Alexander Demos in the third talk. Because Alexander, we're not expecting Zachary, are we? Okay, perfect. Sounds great. Thanks, you guys. Amazing. How to mute audio on YouTube. That is in the bottom where you have the play controls. There's a speaker button. If you click it, then that will block the speaker. And Jessica is out again, but Daniel, maybe you can, Oh, are you watching on the RITMO Entrainment Workshop page? Well, you know what? How about this? I will put you into the waiting room, and we expect that the audio to stop being an issue, and then I am going to, perfect, awesome. Okay, we'll see you guys soon then. Take care, and see you. All right, this next session is 3 remote presentations by people that are joining us from North America. So, first up, Daniel Cameron is going to present on comparing neural and behavioral entrainment to musical rhythms across cultures.
Okay, thank you to the organizers, and thank you everyone for your attention. I'm interested in musical rhythm and the fact that we feel a beat and we move our bodies to the beat, and that we have neural responses that occur at the rates that are associated with the beat and can entrain to those rhythms. I'm also interested in cultural differences. So cultures vary widely in the kinds of rhythms that they tend to use in their music, and these rhythms have different metrical structures, different beat rates, etc. We also see cultural differences not just in the rhythms that people use, but the way we perceive rhythms. And so if you have two different cultural groups, they may hear the exact same rhythm in very different ways. They may feel a beat in one way for one culture and in another way for another culture. So with this talk, I'm going to talk about some data about how neural and behavioral entrainment relate to each other in the context of cultural differences. Okay, so what did we do? We had two basic experiments that are very simple in very similar in their design, but they had different samples. So in the first experiment, I compared an East African sample from Kigali, Rwanda, to a North American sample back home in Canada. In the second experiment, we compared two cultural samples from Botswana, so the San cultural group and the Humbokushu, and also another sample from North America. And what we did was have people do two tasks, at least there's a couple others that I'm not going to talk about today, but a passive listening task while we recorded EEG. So this was just listening to rhythms. I'll play some examples for you in a minute. And their task was to stay awake and listen to those rhythms. What we measured in EEG was neural entrainment, or what I'll call neural entrainment, at the different beat rates associated with the rhythms. Now, this is using the SSAP, or steady state evoked potential method, or frequency tagging, as it's called sometimes, as has been developed by Sylvie Nozaraden. I want to just make clear here that I can't separate the evoked and the endogenous kind of fluctuations within this signal that I'm capturing. So with SSEPs, I don't truly know that this is neural entrainment if we're thinking of entrainment as an underlying internal oscillation. The other task was a beat tapping task. So we had people listen to the same rhythms that they heard in the passive listening EEG task, and we asked them to tap along with their sense of the steady beat. And we tried to make clear to people that they should not tap the rhythm, but tap the steady beat that goes along with that. But besides that, we did not guide them about what beat to tap. So you can see some pictures here, collecting EEG from this participant in a Humbokushu village, and Jessica's collecting beat tapping data from a participant in a San village in Botswana. We used culturally informed rhythms as stimuli. So for the first experiment, we used rhythms that were derived from traditional East African music and also from Western music. And here's an example of one of the East African rhythms. And here's an example of one of the Western rhythms. And in the second experiment, we had rhythms derived from traditional music of the San culture, the Humbokushu, and also Western music. Here's a San rhythm. Here's a Humbokushu rhythm. And a Western rhythm. So if you have any questions about the rhythms, why we use two voices, how I transcribed these, the tempo variants that we used, I'd be happy to answer questions about that, but I'm going to skip over it for now for the sake of time. So just to summarize again, we wanted to compare the patterns of neural entrainment to the different beat rates and the patterns of behavioral entrainment to the different beat rates from these different cultural samples while listening to the same rhythms. We wanted to look for differences across the cultural groups and effects of culture, so a bias towards culturally familiar rhythms, but also looking at brain behavior relationships. Okay, so in the first experiment, I'm going to show group differences in the beat tapping data. So this is a graph showing the beat tapping bias. So this is the proportion on the y-axis of trials overall in the experiment in which participants selected this particular beat rate or these particular beat rates to tap. So we can see some clear group differences, for example, most notably at this slowest beat rate, for which East African participants were much more likely to tap than North Americans. Another thing about the beat tapping that differed between these cultural groups is the what I might call flexibility. So the East African participants used more beat rates over the course of the experiment than North Americans did. So this is listening to all the exact same rhythms, the two groups, the East African participants tended to use more beat rates. Now, what about the neural entrainment, the EEG measures? So what I'm plotting here, this is the North American participants on the top, East African participants on the bottom. And this is the normalized EEG spectral power. So this is how much neural entrainment, I'm going to call it here, is occurring at these different beat rates indicated by the black circles. You see that they correspond to the beat rates that I was talking about earlier. And you can see some clear differences between not the groups just yet, I'll get to that in a second, but the different types of rhythms. So the East African rhythms, entrainment to the East African rhythms is plotted in blue, and entrainment to the Western rhythms is plotted in red. So you can see for both groups, at some beat rates, there's much more entrainment to the East African rhythms, and for other beat rates, much more entrainment to the Western rhythms. Now, what we didn't find is an interaction between the type of rhythm that people were listening to, the beat rate, and the group. So there isn't this clear affective culture in which people were biased in their neural responses toward one type of rhythm over another, depending on their familiarity to that type of rhythm. We also don't see a one-to-one correspondence between the beat tapping distribution here and the neural entrainment distribution here. And I'll show another graph in a minute to better demonstrate that. There were, however, group differences between in neural power in the slowest frequencies and in the fastest frequencies. And it's this pulse level frequency kind of corresponding to the underlying fastest level of the metrical hierarchy or pulse that I'm interested in. So I'm going to come back to that pulse entrainment, but first here is just the same neural entrainment data, but broken down into bar graphs to show collapsing over the two types of rhythms, how much entrainment there was for the two different samples, East African participants and North American participants, for the different beat rates. So here this allows us to really directly compare the behavioral entrainment and neural entrainment. And we don't see a clear correspondence. There isn't the same pattern. That's, I think, fairly straightforward. However, I'm interested in this difference in entrainment at the pulse. And what I was curious about when I explored this data was whether this might relate to the behavioral difference that we're seeing in beat tapping flexibility. It has a kind of surface level correspondence that the East African group is greater than the North American group. And just to my mind, there was some intuitive sense that it's this underlying pulse that's really important in tracking rhythm and in tracking the different possible beat rates. So the fact that one might be more entrained at the pulse level, that makes sense to me that could correspond to greater flexibility to tap at and consider different beat rates. It also, this group difference or this entrainment at the pulse level might correspond to the kind of distribution, these kind of more rich data that represents something about beat tapping flexibility. So where might we look for that kind of relationship? We might expect that tapping is better for those who have more entrainment at the pulse level. We don't find a significant association, although it's going in that kind of direction. But another way we can look at this is this distribution of the beat tapping data is to look at the kurtosis of that distribution. So if we plot the kurtosis, and I'm putting negative going up, this is basically an indication of how flat the distribution is. A higher bar here, more negative kurtosis, is indicating a flatter distribution, and a more positive or lower on this graph, kurtosis is indicating a more peaky distribution. This measure of what I would call beat tapping flexibility corresponds in this kind of surface level to the pulse rate entrainment. Okay, what about experiment 2? So now we've got 3 different samples that we're comparing. We've got the San in blue, the Hamkushu in yellow, and the North American in red. I accidentally gave you a little preview of the brain data there. These are the beat tapping data. So these are the proportion of trials in which the different groups tended to tap given beat rates. So again, we can see some clear group differences. The Hamkushu were much more likely to tap this slower rate than the other groups, and much less likely, by some margin, to tap this second to fastest rate than the other 2 groups. You can see other group differences across the different beat rates. What about in the brain? We see group differences, most notably in this kind of fastest pulse level, and a couple other marginal effects or a significant difference here. But overall, we do not see, again, in this second experiment, a correspondence between behavioral and neural entrainment. But I want to now follow up on these ideas I was mentioning about pulse level entrainment. So this is just the same data made bigger here. One thing that this does correspond to in this sample, as it did in the previous sample, is this measure of flexibility, that is kurtosis. So the kurtosis of these beat tapping distributions for each of the groups is plotted here. More negative going up, again, is indicating a flatter distribution. The flatter distribution, I consider that tapping flexibility, and it corresponds in this, in terms of the pattern across groups, to the neural entrainment of the pulse. So this is some kind of like ongoing evidence that maybe there is something to this, that the neural entrainment of the pulse maybe affords beat tapping flexibility. I should say that we did not find the same, even the direction of the association between beat tapping stability and pulse level entrainment, neural entrainment. We also didn't find the correspondence between pulse level entrainment and the number of beat rates tapped, as we found in experiment 1. Okay, I'm going to summarize. So we found that cultural groups differ in their neural and behavioral entrainment, but that these group differences don't necessarily correspond. Brain and behavior are not readily explaining one another in these kind of measures. However, I'm kind of putting out there that it could be that neural entrainment to the underlying pulse of rhythms supports flexible beat perception, and that's reflected in these cultural differences that we've seen. Why would that be? I mean, as I was explaining earlier, it makes some intuitive sense to me that internal tracking of the fastest underlying rate of a metrical structure would support perception and behavior for those other beat rates, which are multiples of that pulse. And it also corresponds to what I think a lot of musicians hear and know anecdotally, that we subdivide the beat. So if we're counting along to music, we don't just count the beats, but we sub-vocalize the pulse. So this might be totally silent. We're doing this internally, but we're counting the kind of fastest level of or tracking the fastest level of the rhythmic structure. And that's a strategy. We do that intentionally to keep better time and to more precisely produce rhythms. So a next step I'd like to do is to put this idea forward and do an experiment where people learn culturally unfamiliar rhythms. And as they learn them, we can see any shifts in their perception or their tendency to tap one beat rate over another, and the extent to which they readily learn these rhythms and new beat rates might be predicted by the kind of baseline entrainment to the pulse of the rhythm. So with that, I want to thank you for your attention, and I'm eager to hear your questions. Thank you.
Thank you so much, Dan, for that amazing talk. I'm going to turn to the audience we have here in person. Would anyone like to start the questions?
Okay, hi Dan. Thanks for a great talk. 2 questions / comments. I just wonder why, I find it a bit interesting and perhaps surprising that you don't find like in your strong neural entrainment to the pulse layer that they actually tap in all cases. How do you explain this? That's the first one, and the next one is that it would be very interesting to see the same thing done with a polyrhythm, and if you could see like find the same thing regarding flexibility there with different cultures that are very familiar with the polyrhythmic structure and cultures that are not. Yeah.
Thanks. Yeah, that's interesting. In terms of the first question, why do we not find this kind of one-to-one correspondence? If someone's listening to a given rhythm and in one situation they're tapping along with their sense of the beat, and then another situation they're just listening passively. I think it's that these weren't recorded at the same time. It wasn't the case that people were tapping. I think in the work that's out there that has shown these things, it's not shocking to me that if you have someone tapping along and you record EEG, then you see a strong entrainment at that pulse that they're tapping. I think it has to do with the task that they're doing right then. So I think when we're listening passively, in some ways this is less controlled. I don't know what every single listener, what every single participant was doing, how engaged they were, what they were paying attention to. But it's also somewhat naturalistic. When we hear music, we're just hearing things. We're hearing all these different periodicities. They are all present in this rhythmic structure of the music. And so I think what this is maybe more getting at is just the kind of bias of our neural dynamics and what they're entraining to on their own without kind of doing some overt task of trying to tap along or to count the number of beats or emphasize certain beats or that kind of thing. So that might be one reason we're not finding this one-to-one correspondence. In terms of polyrhythms, yeah, I mean, the rhythms that I use that were derived from, especially the African traditional musics, tend to have more of a polyrhythmic structure. There's kind of 3-2 structure overall. I think that has to do with this flexibility. I mean, flexibility is one thing when it's like either I tap the 8th note or the quarter note. That's not that interesting. That's not that hard to go from one to the other. It's really different to be able to hear a 12-unit rhythm in 4 groups of 3 or 3 groups of 4. I had to take out of the talk for the sake of time a kind of demonstration of this, but some of the African timelines that are kind of like clave patterns people might be familiar with, you can feel in multiple ways, and both of them fit. I think this has to do with that music. So you might predict then people who are familiar with that music are going to be more generally flexible. If that's not what I saw necessarily. So there's different African cultures. They have different musical traditions, and they differed in terms of how flexible they were. And North Americans were not necessarily always less than all the African samples I compared them to. I hope that answers your question.
Yeah, great. Just can I follow up just shortly? Because did you see more flexibility in the participants coming from the parts of Africa that have more polyrhythmic structures in the music?
It's difficult. So I haven't done, I'm not a musicologist, I'm not an ethnomusicologist. That's a big limitation of what I'm able to do here. I did my best to kind of transcribe some ethnographic recordings to make these rhythms, but I don't know the musical culture super well. So I don't have a good I'm not confident in saying that African culture has more polyrhythmic structure than that one. To my ears, all three of the African samples that I tested, their musics have some polyrhythmic structure to it, and more than Western music traditionally does. But we didn't see uniform, flexibility. This measure of flexibility of how distributed their tapping was differed from one African group to another. So it's not fully explained that way, I don't think.
Thanks. And we also have a question from an ethnomusicologist or musicologist, Rainer Polak online. Fascinating study and data. Any idea why African groups showed strong sensory motor synchronization or tapping on the dotted quarter note in experiment 2, but not experiment 1? And there's a follow-up. Did you take some measure of relative familiarity, confirming that, for example, San participants felt more similar with San their own rhythms than other rhythms? Sorry, I cannot read it properly. Did you catch all of that, Dan?
Yeah, so I hope so. So in terms of familiarity, I didn't report all of the data that we collected in these experiments and all of the results. So we published some of the behavioral data for the East African compared to North Americans, and we do find some effects of familiarity there. So people were tapping a little bit more accurately for the rhythms that we think are going to be more familiar to them. And they reproduce those rhythms when they tap the rhythm back a little more accurately when it's the rhythm that we expect was familiar. This is difficult because for the second experiment, especially because there are only 2 rhythms associated with each of the cultural groups. These were my kind of transcriptions. So I don't have a lot of confidence that these should be equally familiar to each of the groups and independent of the other ones, in the sense that, yeah, so this isn't, perfectly controlled for familiarity in that way. I'm trying to remember the first part of the question. Why did we not see as much
and why
dotted quarter tapping?
Why they showed stronger tapping on the dotted quarter note in experiment 2, but not experiment 1 in the African groups?
Yeah, I think it depends on which groups and which rhythms. I think one thing about experiment 1 and 2 is that they're different sets of rhythms. Even the Western rhythms rather, were even a different set of rhythms that I made for that experiment compared to the first one. There may have been some overlap, but mostly different. So, this isn't, I'd have to look at which rhythms corresponded to which type of tapping in which group. So that's a finer grained analysis than I was reporting here. But Rainer, I'd love to talk to you more about it sometime and get your feedback. I think this is one limitation I have, is not being an ethnomusicologist and not being as informed about the rhythms that these groups are working with. So I think I've tried to focus on, okay, just like the group differences, and not interpret too much why one group versus another might differ in some kind of behavior, although I think that's really interesting and worthwhile and ultimately important. But if we can explain group differences in terms of brain and behavioral measures, I think that could be a path forward, and that's what I've tried to do here.
Amazing. Thank you so much for joining us, Dan. We're going to move on to the next presentation for time. All right.
Thank you.
Cheers. See you. Next up, we have Carolyn Palmer and Alexander Demos on the analytical models of synchrony and entrainment in larger musical groups.
Hi, I'm Carolyn Palmer, and today I'd like to talk with Alex Demos about analytical models of synchrony and entrainment in larger musical groups. We'll start with some terms. By synchrony, we're referring to the alignment of individuals' behaviors in time within the same sequence or time series. An example is musical ensemble members. Group synchrony can be intentional, as in most large ensembles, or unintentional, where there's no intention to synchronize or an intention to not synchronize, as in Steve Reich's phase shifting among musical parts. Entrainment usually refers to a coupling of rhythmic brain activity to external and internal rhythms. And we're going to focus today on the term coupling. Coupling usually refers to information shared between players, a mathematical function that describes precisely the interaction between the players, the groups, or the system parts. An example is how a performer's phase coupling describes how their beats are accelerated or decelerated by other performers. A famous example is Glenn Gould, Canadian pianist, who was interpreting the Brahms piano concerto at a much slower tempo when he played with the New York Philharmonic, led by Leonard Bernstein. As Bernstein put it, this was the Glenn Gould Brahms concerto, which asks the question, who is in charge of being the leader, the soloist or the conductor? And as Bernstein put it, usually it's a meeting of the minds, but in this case, the orchestra had to overcome normal coupling to perform correctly with the soloist. Now this is an extreme example. Most examples are more nuanced. So for example, this Schubert's octet starts with a single tone, an F major, that all of the 8 players have to perform together and to blend. But within the first 2 minutes, they reassume various combinations. So the clarinetist pairs with the cello and bass to carry the melody while the strings bond and blend and the horn and bassoon blend. About 15 to 30 seconds later, those subsets reform so that the clarinet is playing with the violins while the viola, cello, and bass form a group and the horn and bassoon form another group, and so on throughout the performance. Deckert provides a note-by-note analysis of this piece that's very interesting. But what this example shows is that coupling must be very flexible. Each performer has to engage and disengage within a few seconds with different players. And this is not limited to Western tonal music. We see it in many different styles and genres. So how do we measure synchrony, and in particular coupling, in these larger musical ensembles? Well, pairwise comparisons were the first approach in the smallest group, duets, and were based primarily on autocorrelations and cross-correlations at different lags between the performers. When the first larger ensembles were measured, pairwise comparisons were also applied to all possible pair members within the groups. Granger causality, transfer entropy, and relative phase were additional techniques. There are many advantages to pairwise comparisons. They permit comparison of how one pair behaves in a larger group context with how that pair behaves on its own in duets. And pairwise comparisons help identify asymmetries in influence between pair members. For instance, how pair member A influences B more than B influences A. There are limitations to pairwise comparisons when they're applied to larger groups. They assume equal access to information about each partner in order to generate some measure of coupling with each other partner in a larger group, which often exceeds perceptual and attentional capacities. Pairwise comparisons also assume additive influences of each partner or pair. They don't address 3-way or 4-way interactions seen in groups like these octets. So we look to other domains for guidance on how can we measure group synchrony in larger groups. 2 areas, social group dynamics and nonlinear dynamics, make predictions. In social group dynamics, team performance is studied across a wide array of goals and tasks. In nonlinear dynamics, coupled oscillators are analyzed across a wide array of timescales, from single cells or neurons up through groups or populations. So we'll start with social group dynamics. Group dynamics refers to understanding the patterns, roles, and structure of groups. And an important factor is group size. The increased size expands the number of interpersonal relationships per individual. And findings in social dynamics indicate that as the group size increases, the perceived self-contributions to the group behavior decrease, and the perceived self-workload decreases, sometimes referred to as social loafing. So think of a duet, a quartet, and an octet. The comparisons here indicate that group size alters the number of possible subgroups and their relationships to each other, those coupling terms. So if we combine group size and subset size, where group size refers to the total number of individuals in a group and subset size, in the octet example here, is 2 or 3, you can see that there's a trade-off between these factors. The group size and the subset size have an inverted U shape on the number of possible combinations that go beyond the realm of perceptual and attentional capacities. So what do group members do when they look to synchronize with others in the group? They could use the best odds to synchronize, or they could use strategies that reduce the number of comparisons. Another factor in social dynamics is group roles, that is, the tendency to behave or interact a certain way in a group context. Examples include task roles such as conductor or soloist that can change throughout the course of a performance. Findings here indicate that asymmetric influences of person A on person B increase as individuals assume roles. Roles can increase the predictability of the group members' behavior. They can increase the ease of coordination with other members. So consider a trio that has no roles versus a trio where there's a soloist and two accompanying parts. This raises implications for musical ensembles. Individual solo behavior may not be indicative of that individual's behavior in a group context. And another example is that leadership also needs some measure of followership. Not everyone can or is willing to follow. So there's a variety of group roles that might influence coupling. Group roles can reduce challenges. Consider the presence of a leader role, such as a conductor, that reduces the number of comparisons that performers must make to decide when or how to synchronize. So on the left is a graph of the number of possible pairwise comparisons that increases as the group size increases, shown in the black line. Consider when a leader is present in each pairwise comparison. The set of possible combination is now greatly reduced. On the right is the same graph but for n-wise comparisons, such as threesomes or foursums. Again, the presence of a leader within each subset reduces greatly the number of possible comparisons that each performer must make to decide when to synchronize. There's a tenfold reduction in the bars indicated in red on the left and a 100-fold reduction for the bars indicated in red on the right. So the point is that group roles may benefit larger groups more than they benefit smaller groups. Okay, so we've covered two factors in social group dynamics, and now I'd like to turn to what nonlinear dynamics has to say. And this refers to coupled oscillators. The Kuramoto model is the most popular nonlinear dynamical model based on weakly coupled oscillators that synchronize over time. And this famous example is of coupled oscillators that start by putting metronomes on a board of wood. They're all clicking at different phases, but because the wood allows the transfer of information between the oscillators, they are able to couple and reduce their phase over time. Same models have been applied to musical synchrony. So here's the model in the Kuramoto oscillator model for an individual oscillator. And what's important is the circled model parameters. So kappa is shown by the K. That refers to the coupling strength from one oscillator to another. And it's a function of the sign of the mean phase of the other members of a group. The group of oscillators is represented by this formula, which points again in the circle to the coupling term and the number or group size. So the circle on the right here, you could think of as one musical beat, and each of the dots refers to a performer in the group. Their phase is scattered, so they're not perfectly synchronized. Over time, the Kuramoto model predicts that the oscillators will, with coupling, will force the synchronies to be more aligned. So the findings from nonlinear predictions for synchrony are that they're sensitive to group size in the number of oscillations and group mean, and to roles, kappa, or coupling between oscillations. A final point from the nonlinear dynamics, it refers to emergent behaviors, interactions among oscillators that arise from unique or nonlinear parameter combinations. So consider an uncoupled trio, like a bass, a guitar, and drums. Perhaps they're all playing, but at different tempi, because they aren't trying to, or perhaps can't hear each other in order to synchronize. We can plot the model parameter predictions, in this case for tempo, where G, B, and D refer to the intrinsic frequencies, or tempi, of these different performers. The amount of energy that it takes to change tempo is shown on the y-axis, and you can see that it takes quite an amount of change in energy for one performer to shift to the tempo of another performer. Now let's take that same group and couple them so they can hear each other and they are playing together. So here, the pattern shows a new model parameter, the energy of the trio, at one point, and it's a function of the other three intrinsic frequencies of the performers, but it's a non-linear function. So the energy required for each of those performers to shift to the trio rate or tempo is much smaller now. So where does this leave us? We think there are some proposals we can make for going forward in musical group synchrony applied to larger ensembles. First, we would apply individual synchrony indices of how likely performers are to assume group roles in order to predict asymmetric coupling between them with others in the group. Second, we would apply a group synchrony index that incorporates group size and subset sizes in order to predict how that changes with the size of the subsets. Some of these metrics already exist. Finally, we would examine group desynchrony, both intentional and unintentional, to try to predict how people desynchronize at transition points of weakened coupling. So I'd like to take this opportunity to thank the organizers, and I look forward to your questions.
Can you hear me?
Yes.
Yay, welcome. You are
Thank
up on
you.
the big screen. Thank you so much for that wonderful presentation. I'm wondering if anyone in the audience would like to start the questions. And, oh, sorry. Oh, I see there's a question from Laura Bishop coming right to you.
Hi. So I'm wondering about leadership in the case of an orchestra and the role that the conductor has in the moment of a performance. How would you go about mathematically and reliably distinguishing between what is practiced, leading and lagging between the conductor and the musicians, and kind of leadership that's emergent in the moment? So I guess quantifying how much effect the conductor is actually having during a performance and distinguishing this from the practiced relationship that they've had with the orchestra.
That's a great question, Laura. There's a lot of parts to it. So we only have some information for some parts of your question. So I'll start with the inverted U-shape relationship between the group subset size, so let's say the string section or the first violins, right? And the total group size, the entire orchestra. So I think you could actually make predictions about the interaction between the subsection in which a particular performer was and the total group size of the orchestra to tease apart how many people could be coupling at the same time. But you raised some other issues that we have less information on, I think, like what information in their practicing do they bring to the group performance that influences the hierarchical relationships? And that's where we've been interested in using the social group dynamics to get a better measure of, for each individual, how likely are they to assume certain roles? Are they happy being one in a set of 10 in a group? Or are they better adapted to being just 2 of 3 percussionists? So I think if we use different methods, we could tease apart these factors better.
Okay, thank you.
And a question coming in from Finn Upham.
Hello. Really interesting question. I mean, that you're tackling. Not about me. That's you get to choose how you feel about that. Thinking about the experience of playing in ensembles, particularly in ensembles with different instruments in play, the opportunities to influence each other really depends on the part that you're playing. And so I'm wondering how you're thinking about parts in their arrangements for the kind of influence that's possible. I've been in a lot of ensembles where, as somebody who plays in the bass range, my opportunities to influence the group varies a lot because I don't always get a lot of onsets. So, how are you thinking about the music's contribution for the opportunity for leadership, and then the sort of consequences socially about who gets to play what, when that is partially determined by what you play physically rather than who you are in other domains? Thank you.
Thank you. That is a great set of questions, Finn. So we chose the octet on purpose because the composition, the rhythms in the parts of the composition lended itself to ensemble members having to repair with different groups of ensemble members. So certainly we would have to acknowledge that the musical composition and the rhythms involved are going to influence who's having to bond with whom. But at the same time, I would say many non-compositional forms show that same kind of repairing of individuals. So for instance, improvisational jazz. Do we know how much success they have resynchronizing in these different genres? Probably not yet. There's some really nice work on improvisational jazz among small ensembles. I haven't seen as many studies on large ensembles, so you might have some suggestions for that. Thank you.
And thank you so much, Carolyn. Are there any final remarks or questions? Okay, in the sake of time, we're actually just going to move on to Alexander Demos' talk. So we will see you, Alexander, in just one moment. Well done, thank you. So Alexander Demos is presenting here, Headbanging to the Beat, How the Synchrony and Identity Relevance of Gestures Affect Musical Identity Perception, by Zach Melton and Alexander Demos.
Hello everybody, I'm excited to present to you today the work of my first graduate student who's now graduated and gone off to do UX research at Google, Zach. Zach is a bassist and a rock musician. So you'll see how this work is inspired by his background. So let's say Zach took me to see a metal concert. At this concert, you can see here a bunch of high identifiers with rock and hard rock music. They have all sorts of cymbals and devil horns and all sorts of ways of indicating their rock fandom. They're probably also headbanging and moving their bodies with the musical beat. So let's say Zach drags me there, and then we spot two people. The first person we spot looks like a typical headbanger. They have the wristbands with the spikes, the long hair, the black t-shirt, and they're bopping and they're headbanging to the beat. And over in the corner, there's this weird guy who's just air tapping to the beat, not moving in any other way. This individual has likely had their brains melted by attending too many entrainment workshops. So the question is who's the bigger rock fan? Well, with very few exceptions, most of the literature on synchrony and gestures is often devoid of social context. We often pair strangers together, people who have no shared social or musical identity. We just tell them tap or move to the music. But in this particular case, I don't think anybody would disagree with me that clearly the guy on the right is a little weird, and the guy on the left is clearly a huge rock fan. They've kind of structured the whole identity around this, right? So how do we make that determination? So as a lot of social psychologists do, we're going to borrow from Gibson's affordances. Well, what's an affordance? An affordance is a possibility for action, which depends upon the experience and abilities of each individual. So let's take a young athletic person. They see this tree affords to them climbing and affords to them exercise. If you take an older individual, this tree affords a place to rest. So these ideas are then connected to what we're going to call social affordances. So let's go back to this example and understand a social affordance, right? So let's say I am now perceiving the people around me. Well, I'm going to see Zach, he's going to be wearing black and all sorts of things and probably geared up for this concert. I'm going to see a metalhead. I'm going to see someone who can help me negotiate this event and not get lost, beaten up, or just trampled over. And further, I'm going to see these people around us as potential research subjects, because isn't that how we all see the people around us? They're just all subjects waiting to be analyzed. I'm going to see that fellow person there who's tapping as both a potential fellow synchrony researcher, or at least someone as socially awkward as me, and someone I could probably get along with. They afford camaraderie and someone to talk about with what's going on around us. Zach, on the other hand, would perceive this totally differently. He would see us as poser nerds, and he would be like, oh my God, they're gonna drive me crazy, and Alex is gonna go off and talk to that weirdo who's tapping in the air. Instead, he's gonna look for this other guy, he's gonna say, that's my mosh pit buddy. That's the guy who's gonna protect me when we go into the mosh pit, and he's gonna have my back, and we're gonna have a great time. So these social affordances lead to specific hypotheses. For example, if gestures afford musical identity, expertise of the gesture and the perceiver will matter, and they're going to affect the perception of the target's musical identity. So if you yourself are a hard rock enthusiast, you're going to perceive the movements of the individuals differently than someone who does not have that expertise. So musical identity is a concept often wrapped up with the idea of social identity. Social identity is a way of indicating to others your group membership. People can express and reinforce these through discussion of musical preferences and wearing symbols. But we don't want that in this study. We want to go purely based on the gestures. So in the stimulus we create, it's going to be devoid of this kind of information. So what we're going to look to see is if gestures afford musical identity, performing an identity-relevant gesture, in other words, something like headbanging, should be perceived as higher in the target's musical identity. So if you're headbanging, you should be someone who likes hard rock and metal. This also could relate to synchrony research. And in previous work, we've shown, for example, that the degree to which you yourself move in synchrony with the music, regardless of what your partner does, helps you form bonding relationships and positive feelings towards that other individual. And it turns out that when people synchronize together, when two people are doing something, others perceive the group as being more together. People think that they like each other more, and they're more efficacious as a group, especially for things that related to social action. So the hypothesis here is that the more synchronous the gesture with the music, the stronger the affordance of the musical identity. So there are 3 studies. I cannot take you through all the details. The first one is basically just to figure out which gestures are the best, examine the reliability, and it doesn't have music. The second study also doesn't have any music. It's purely based on the gesture. And the question is, does the identity of the perceiver and the target matter? In other words, is there an actual social affordance happening here? Or is it really just based on what the target is doing and has nothing to do with the perceiver? And finally, does the synchronousness of the gesture afford musical identity? In other words, does it act as another cue to help someone determine someone's hard rock identity? So the main question will be, do synchronous musical gestures afford hard rock identity? Well, first, we're going to measure the perceiver's hard rock identity, the person viewing the videos. Second, we're going to look at the gesturer's hard rock identity, and we're going to have 2 extremes here, someone who's a rock musician and someone who's a classical musician who doesn't know anything about rock music. And then we're going to have the hard rock relevance of the gesture they're performing. I'll show you those in a second. And whether the gesture is performed synchronously to music or not. So these videos were created through motion capture figures, and they were wearing bodysuits during the recordings. Both of these videos are of the expert, Zach. And here you're going to see an identity-relevant gesture, head banging. You can see he's moving in a particular way. It's measured at, I think, 60 hertz. And then you can see him doing what we call twisting, which could be done at any kind of musical concert. I preferred the name dad dance, but I lost on that one. Right? Looks like a dad dance. I don't think it's twisting. But anyway, so in this particular case, we see these 2 types of gestures. These are the ones that won out from other gestures that we had looked at and tested. Now we're going to use key social measures that were previously developed and we just adapted. We tested their reliability, and basically we're asking, to what extent is your hard rock fandom central to the following? And those usually revolve around reputation, building relationships with others, and signaling to others your group member. And that had high reliability. And for the 2 gestures, the selected gestures that we have, it's the same, but it's asking about the person in the video. So they answered this question every time they watched the video about that person's reputation, their feeling with others, and do they signal to other group members. So it's a 2x2 within design, no music in the first study, and a 2x2x2 or asynchronously. So, for example, Zach, the expert rocker, is going to headbang synchronously to the music, or he's going to headbang asynchronously to the music, which would be 15% faster or 15% slower, counterbalanced across the various repeated trials of each of these videos. And then my other grad student, who knows nothing about headbanging and nothing about rock music, was taught to headbang, which was extremely funny to watch her learn. And then she also did the twisting. And we actually did not have her watch Zach perform them. We instructed her on how to do them so she wasn't mirroring him too much. That's going to be interacted with the perceiver's hard rock identity, and each study was well powered to detect small effects in a fully within subject experimental design. Now, the summary comes down, let's just go quickly through the main effects. There was a clear effect of gesture relevance. In other words, headbanging clearly affords rock fandom. It's much stronger than the twist. Synchrony also affords higher rank rock fandom, though there's some interactions there, which I'll come back to. And the clearest effect in the study was that the higher your own, the higher the perceiver's rock identity, the more they perceived the movements of the other person as a rock musician, and that also had various interactions to deal with. Now, the expertise was a little bit more complicated. There was a main effect, but there's also a bunch of interactions which we need to unpack. I'm going to have to go through this quickly, and I'm cutting a lot of results out just to get to the main point. First, and most importantly, in just viewing the gestures, you can clearly see the hard rock identity effect. Low identifiers are less likely to perceive them as hard rock, and that's high identifiers do. And there's an interaction for expert performers. So the experts, when you're a high identifier, perceiving an expert, it doesn't matter which gesture they're moving, they just perceive them as an expert. But when novices perceive, they're actually looking at Zach and saying, well, when he's headbanging, he clearly looks like a rocker. When he's not headbanging, and he's just twisting, he doesn't really look like a rocker. Whereas for the novice performer, we see a much more balanced and just a main effect kind of effect. No interaction there. So for experts, low identifiers use relevance to determine hard rock identity, where high identifiers really do not. It seems like they're just relying on expertise or something else. Now, in study 3, when the music is introduced, what we see is that the interaction was not where it was expected. We expected it to be more relevant for experts, but that's not what happened. It actually became more relevant for novices. So high identifiers actually look at the novice and distinguish. When the novice, who's probably not moving exactly right, but when they're moving in synchrony, they get a little bonus. When they're moving out of sync, they get a little bit of a detractor. Traditional social theory would have said that people who identify as experts would be more critical of other people who are claiming to be part of their in-group. That's not at all what this shows. We'll come back to that in a couple of minutes. Basically, sync matters when you're a novice, but it seems to be driven by these high identifiers. So they're perceiving these outsiders differently, but positively. As you can see, the means are almost identical between the two. And finally, sync only seems to matter when you're not doing the right thing. So in other words, if you're moving irrelevantly, that's when sync matters. But as I showed you earlier, there's that kind of complex three-way interaction to deal with. So it's a little hard to unpack. So in summary, as we start to think through building larger theories of synchrony, especially with the interest growing in social mechanisms, we need to think carefully about the social context in which we do these studies. We need to think about the social and musical identities of those individuals that are involved. Bringing random strangers may not always be a good idea, or we should at least try to connect the random strangers through some shared identity when we have them do these tasks. And that the gesture that they do matters. We should stop relying on just finger tapping and rocking chairs and circle drawing, and actually move into gestures that make sense given the musical context which we're putting people in. So we want to think through these issues as we build a larger theory, but there's some really interesting things that distinguish us from social theories. And there was this curious finding that social identity theory really has a clear prediction about what should have happened in terms of experts rejecting posers. And that's not what happened. Posers were not rejected. In fact, what came across was that these people that identified as high in hard rock identity were more open and accepting of even the novice when they were performing weird gestures. They didn't seem to reject them and write negative things in the qualitative portion. So it may be that musical identities are themselves more open and inviting to than other social identities. But the question is this only true for rock music, and is that because rock music's older and necessarily not as hip as some of the other music that's pushing more counterculture themes as it once did in the 90s? So I want to thank everybody for listening, and I'm excited to take your questions. And it may be that Metallica was right in the 90s that posers can't headbang, but it seems like in 2023, posers can headbang and rock musicians seem okay with them. So thanks, everybody.
Alex, can you hear us and are you with us? Sorry, Alex, are you here? Can you hear us and are you with us?
I'm here.
Yay, amazing. Oh my goodness, that was so wonderful. Thank you for making the last talk of the day a comedic one, and I'm sure that Zach would be super proud of you despite your, poser self status. I wanted to start us off because just in order to understand the results a bit better, do you happen to have the videos of your other student who was actually headbanging and twisting? Because I think that could help us visualize what this poser really looked like and understand maybe why the rock musicians, or I don't know, just get a better perspective. If that's possible, if you share your screen, let me make sure that's okay. Yeah.
I will do that. I should have them here. Let me just... I can play the music. I was worried about playing the music because of copyright strikes from...
Oh,
all right, here we go.
But we can cut it out. If they flag the video, we can probably cut it out to next week when we post it.
Okay.
Or you can not share your sound as the other option.
I can mute the sound.
Amazing, thank you.
So here's the expert syncing to music. So this is Zach. And he's pretty in time with the music. And one of the things you'll notice is, one of the things we noticed is that he really does look like a rocker. And watching when the other students started doing it, it took a while to get her to do it correctly. She's a little fast here from the same beat, but she doesn't look like a rocker. In fact, it was really interesting is that when we first, posed this idea, this is what would be happening, people said, no, they can't determine it. But there's actually a lot of Gibsonian research that says people determine from point light diagrams the differences between groups pretty readily, especially if you're an expert. And when we watched more and more videos of the two of them doing it, it was pretty clear that the effect was there.
But did you ask the participants what they thought of those people too, or how well they were performing the headbanging gesture?
Yes, so there was a questionnaire there was an open-ended questionnaire as to try to get at what the aspect of the gestures and cues they were using to make their determination, and there's a kind of qualitative analysis at the end. In general, they were not very well descriptive, and I think that's the trouble with sometimes unpacking affordances is what is it the aspect of, and you kind of have to isolate it piece by piece to determine it. But there is something in the specific way there's that gesture there about the way they're moving specifically the whole body, which seems to indicate that part. But again, it's hard to unpack.
Super interesting. It kind of reminded me of a study that Persephone Tsanaki presented at one point where people were in training or tapping with people, and then they were actually tapping with a computer, and then the computer was doing weird things. And the people were, she interviewed them afterwards to ask what their experience. They were saying things like, oh, yeah, even though it wasn't synchronized, I still thought they could have been a good person. Just because they struggle with it doesn't really, maybe they, had an issue or something. And I, just the way, the arm was shaped in that video made me think, maybe that could also be a thing. You can appreciate that's a person trying to get groove to the music, but I don't know. That's my take. Are there any other questions here? Sorry.
Thank you. I was waiting for you to say that synchrony didn't matter, and I feel so justified. I mean, it's good that it matters to the novice, but it doesn't matter for the expert. And I think that's consistent with the environments in which this kind of behavior is performed, because if you go to concerts, you see people fall out of sync all the time. And it's also an acoustic environment where people are very distant from each other if you have a festival crowd. And so you can't judge people based off of the synchrony of your hearing of their motion. You know, that comparison just doesn't work. So there's just all kinds of physical and contextual reasons for the synchrony to be way less important than the quality of the movement. But when we take synchrony out, how do we encode the quality of their movements otherwise?
And that's, yeah, that's the question from the Gibsonians. They spent a lot of energy trying to get at, for example, how you determine expertise, for example, the ability to detect someone who's muggable and who's not muggable. And it has to do with the sound of the footsteps, the speed of the walk, and there's a lot of information encoded in just the sounds of the way people are moving. Here in the motion, again, it's one of these very difficult ineffable qualities. It's just, you see it and you know it, and it happens in movies all the time. When old Star Trek, when they're picking up rocks to throw at the alien, you know it's a rock that weighs 1 pound. You can see that all of the body movement picking up that rock doesn't match. So the question is, where does that expertise come and evolve from? And it's got to be through the training and through being around others who do it. But in terms of the synchrony, you're right. We didn't think it would be a strong effect. We did think, however, it would. So the results came out backwards for the experts. They were expected, as they gained expertise, they would be more judgmental of Zach and say he's not a real expert, and there would be more distinction. And that's not what they showed. And we thought there the separation would occur, and no, not there either. So it seems like your point that they're actually welcoming people into their fold is much more likely.
I think that's also tying it back to like the genre, sociocultural context of like how precise those things are. Maybe a beat bin study might go along well with this. Yeah. Are there any further questions? Amazing. We are actually at the end. We're a little over time. So next up, we have some finger food downstairs. We wish we could share it with you, Alexander, but next time you'll have to come over and hang out with us at RITMO. So thank you so much for the wonderful talk. Have a good rest of your day. Bye.
Thanks.